manual visual inspection has been a method in the manufacturing industry to ensure quality that has been prevalent for decades. It has relied on human judgment and human capability to detect defects, as well as deviations from standard specifications. Even though it has been prevalent for such a long time, it does have some of its limitations, specifically subjectivity of decision-making, inconsistency, as well as fatigue-related manual errors and faults. Now, due to the advent of advanced technologies like machine learning and computer vision, the landscape started to change several years ago. Many companies came up with systems to automate the manual visual inspection process with vision-based systems. Started initially with classical computer vision, but in the last couple of years, with the advent of machine learning and specifically deep learning methods, the performance of the systems has significantly increased. Now, even though these systems have been deployed in production and are available, still, if you look at the larger picture of manual visual inspection, we've only displaced or replaced, let's say, a fraction of what is possible. And a large part of this is because some of those visual inspection tasks are very complex. And the complexity may come either from the fact that some of these products need to be visualized from or inspected from multiple angles. It could be that the specifications for quality are very, very stringent. It could be sometimes that these defects are rare or they appear after a longer period of time. So you don't have that in the training data. Or sometimes it is really difficult at the image level to differentiate between what is a real defect and what could actually be not a defect, could be a smudge or anything that can be cleaned away. So there are multiple reasons and for these challenges, why these systems are still not so easy to build and deploy at scale. In this workshop, we are hoping to hear from the experts who are present throughout the day via invited talks, but also in the panel discussion about some of these challenges. Now, as the industry grapples through many of these technical challenges, on the other hand, very often what we hear from the academia is, are we really working on the right problems, the problems that are really bottlenecks in the industry towards deploying the solutions, or is the data that we work with representative of these complex problems or not? So part of this, the reason for this workshop is to bridge this gap between industry and the academia. And initially I thought by the size of this room, we are doing a great job to bring together people, but apparently there's still a lot of space here. So hopefully more people are going to join us soon. Now, before we dive into the workshop itself, I have a couple of why it's muting. Yeah. Okay, then let me back up a bit. Okay. So, if you take a look at the submissions, paper submissions during this workshop, we had 51 submissions from highly diverse 18 universities, 12 companies, 9 countries, with an acceptance of 27 papers. And the panel decided the best paper or best inspective paper award goes to Segment Anything is Not Always Perfect, an investigation of SAM on different real world applications. We are going to hear from the authors of this paper later today. The team also, prior to this workshop, ran a competition and actually two challenges. The first track was on data efficient defect detection. So you can think about this as more a few shot learning approach. There were 46 registered teams, 12 companies and 20 universities. And we have our top 3 winners from that, as well as the most innovative solution. And likewise, there was a track 2, which focused on synthetic data generation for defect detection. 29 registered teams, 11 companies, and 10 universities. We also have our top 3 winners and the most introspective or innovative solution there as well. And we are going to hear from all of these 8 teams later in the day. They of course get some nice prizes from one of the innovative companies in the world. So yeah, really looking forward to this workshop. And I would encourage everyone to participate actively and yeah, make the full use of this day. So thank you very much.
Okay, thank you, Rahul. Our first session of the workshop is a keynote from the distinguished speaker, Professor Shi, who will delve into the importance of machine vision enabled in-process quality improvement in smart manufacturing. Dr. Shi is a professor at the School of Industrial and System Engineering with joint appointment in the School of Mechanical Engineering at the Georgia Tech Institute of Technology. He is renowned for his pioneering work in data fusion for quality improvements and is the founding chair of the Quality Statistics and Reliability Subdivision at Informs. Let's give a warm welcome to Professor Shi.
Thank you for the nice introduction, and it's really an honor to be the first speaker in this first machine vision workshop. So my topic today is machine vision enabled in-process quality improvements in smart manufacturing. We all know machine vision has been widely used in the manufacturing system to monitor the product quality, the process variables, provide very important and effective information. And also we know lots of research has been done to improve the machine vision capabilities, to improve the reservations, the detectability, improve all the performance in the machine vision. However, there are few research to integrate data from machine vision with other production data for quality and the process improvements. Because machine vision is very important to check the product quality, to monitor the machine conditions. However, that's not the final objective. If we see the product has defects from the machine vision, the question is what we can do to eliminate that kind of defects, to do the defect prevention. We monitor certain tool conditions through machine vision. We know the conditions changing, but how big impact of this kind of change to the final product, to the productivity, to the quality, this is something ultimately we care about. So the important things is desirable to use machine vision as an essential tool to enable in-process quality improvements. So basically, we want to achieve in-situ process monitoring, root cause diagnosis, predictive control, and finally, product defect prevention. So those integrate all the information from machine vision capabilities and all other variables to have ultimate control for the manufacturing process and make the defect not happen. So that is something we like to do. So in order to do this, there are lots of research need to be done. First, we need effective algorithm in anomaly detection, feature extraction using machine vision. This has been done for many years. And for given product, what kind of features are meaningful to the product? Not all the information from the machine vision we obtained are important. And also we try to modeling the heterogeneous data, such as images, video signals, 3D point cloud data from machine vision, and also the functional curve signals, text data from the manufacturing system. As you can see from this 3D printing process, we can have a laser scan to measure the dimension. We can have the thermal cameras to measure the distribution of the field. We have the material properties, which is the text data. We can control the volume of the printing, the speed, which can be regarded as a functional curve. All those variables will impact on the quality of the 3D printing. And we need a model from the machine vision, the temperature distribution, the dimensional 3D plot data from the dimension, and the multi-layers propagation from the first layer, second layer, third layer. And all these qualities are interrelated. All these machine vision signals are interrelated. So how to model prediction and control of this 3D profile propagation based on machine vision signals and integrate those signals with all the process variables are very important for quality improvements. So in this talk, I'm going to give a few examples our research group has been done along these directions, which is the red color here. And I will focus on the concept, why we work on this one, and what are the results. When we implement this in the industry, what kind of impact? I will skip the mathematics, but you can, if you're interested, you can read the papers I put on the slides also. So the first one is sequential high dimensional data analysis for anomaly detection and system monitoring. So why we want to do this one? There are different common characteristics from this high dimensional streaming data. So the right top is measurements from semiconductor manufacturing. There are 130 sensors from one chamber generate that kind of functional data, and lots of image data also for the quality inspection. And the second one is for the composite parts. Third one is steel rolling. Those are all real data, which is a high dimension. And also the speed generated data is very high velocity. And also they have a complex spatial temporal structures. And one thing is when anomaly occurs, we don't know when this occurs, where's the location, and what are the shapes of these anomalies. So objective is how to do unsupervised feature extraction and anomaly detection from this. Why emphasize unsupervised? Because try to get labeled signals very difficult. Try to get specific types of shape and defects, try to label them even more harder. So how to do this? We propose this SSD type approach. So here on the left here is a video signal. You can see there are multiple images like video signal. So based on this sequential video signal, we use one-step decomposition to decompose this one into 3 components. The smooth background information, which can be time varying, and also the sparse anomaly, the next one, we can detect it, and also the noise signal. So on the right, you can see, so basically we have one signal from the machine vision, we decompose into background, anomaly, and noise. How to accomplish this? We try to change this anomaly detection problem into this estimation problem. So basically, from the engineer knowledge, we can get the typical basis of the background information, the basis, and also what kind of anomaly bandwidths may occur in the process. So we do such kind of compensation, estimation. So we try to solve this optimization problem to get the background estimation, anomaly estimation, and also the noise. We also developed a fast algorithm to make this calculation in high speed. So this one simulation result using this one. On the top left is a video signal we obtained. Based on this one, we do the decomposition. We get the right top background information. If there's an anomaly occurs, it show up on this screen. And over there, send alarms. So this simulation, we also tried use the industrial data. So this hard rolling
data from hard eye from OG Technologies. And here is the original video signal. When there's an anomaly occurs, we can quickly detect this anomaly, and also we can filter out its background. The alarm will be sent out also. So this is from the real data, real production data validation. So using this one, after developing this one, we also realize there are some limitations in practice because like in the aerospace for the composite parts inspection, they have a piezoelectric to generate vibration and use a laser beam to pick up vibration magnitude, generate this kind of image. So how to detect this one defects takes a longer time because of the low sampling frequency to pick up this. As the middle one is also related to take samplings. Each dot is a device on the top. And this one is in Oregon to measure the earthquake of the volcano in Yang Mountain. So there are about 500 points here. And each one driven by the battery. And when battery died, this device died. So you can imagine if all this one works simultaneously, they cannot last longer. So the question is, can we use some subset of this one to monitor this one if needed? Only wake up a few sensors on the neighborhood. The right side is the satellite, monitors the solar flare of the sun. In the real time, in the sky, I mean in the orbit, they can measure this one in real time, but they cannot transfer the data to the Earth. So the question is, can we measure less points and then monitor the process and detect the anomaly? So conceptually, we have this exploration. So basically, we use a few points to cover all the space. If something detected, for example, here, we add more samples to do exploitation to detect the shape of this. And we design algorithm to accomplish this automatically. And here the example, we have 250 points total budget for the measurements. And this small circle is the anomaly to be detected. On the top are the two algorithms we proposed. On the lower part, this one is a random put the points, over there put the grid. You can see after 250 points used up, our algorithm on the top, we can cover pretty much all the anomalies, detect very nicely, where is it, what are the shape, and the lower part is hardly effective to detect this. So this is anomaly detection with limited samples, how to do automatically. And we do a real case study with aerospace company inspection. So the setup is over there. With before we work on this one on the right, the standard procedure over there, they have a 27,000 points and takes 2 hours to measure this 1 square meters sample composite parts. With our algorithm, we can use about 300 points. With 2 minutes, we can accomplish similar performance. So this is how effective by using our adaptive sampling can significantly reduce the industrial inspection of the defects of composite parts. So in early examples, we treat one image at a time to do the anomaly detection. But many times it's not information not only in one image, but in a set of images. How can you use that kind of information to develop more effective detection algorithm? So we propose this additive tensor decomposition. So this one is a real example for the arthrotic root. So basically measure this one to see if any, the CT scan. CT scan is one slice at a time. So even we see this image is one after another, but they have a interrelationship among them. Basically, this slice all linked together is one after another. If there are some defects occurs on this one, then maybe continuously we can show up in the next one. If we only focus on one image at a time, we may miss the information. So how to consider this multi-image relationship? We formalize this tensor and focus on the tensor structures. So we defined a typical tensor like this one image at a time. We have 3 types of tensor structures. Could have smooth one, smoothness among this one. Could have a sparsity, you can see the dot, only a few on each slice. And also we have limited variation patterns. You can see on this one, between these different slices, we have this pattern and could be piecewise consistency. You see, a few like this, a few slices, a few slices. So these have different types of structures. And the question is, how can we automatically extract such kind of structure from the tensor? So we define this optimization index to represent such kind of structure. And to accomplish this one by solving the optimization problem over there, and then we can get the background smoothness on the top and the lower 3 index corresponding to the continuous property, sparse property, and the error. So by input this one into the early data, we show we can have we can detect the middle one is our approach. We can detect this one much better than the benchmark on the right. So you can see the lower left and lower right, they miss a lot of information because they only treat each image at a time. But we treat multiple images are interconnected. In the middle one, we can get a much more effective detection results. So this was anomaly detection. Another work we are saying the machine vision signal should be linked with other process variables. In this way, we can accomplish 2 things, multiple things. One is if something wrong in the manufacturing process, we can anticipate what kind of defects may occur. If some defects occurred, we can say, what are the potential root causes? And also during the manufacturing, if we make some adjustment on the process variable, we can impact on the quality to do the defect prevention. So the key is how to link the machine vision signal from the product with the process variables. So we do this multiple tensor regression in multi-stage manufacturing process. So in this case, on the far right, Y is here is machine vision signal, and then here is different types of process variable signal. Could be an image, could be functional curves, could be a number, could be 3D point cloud data here. And we have a training sample. We already make multiple products here. And based on this one, we develop a model by using this tensor regression. We translate the modeling problem. Y is product quality information. Xj is process variable information. We estimate this coefficients B by using a tensor decomposition. Solve this optimization problem. After we have this model, when we have a new data of the manufacturing process, we can predict the quality before this quality is the product fabricated. Or if something fabricated has defects, we can go back find out which variable changed responsible for this, which is the root cause diagnosis. So this is tensor regression. We further expand this one to consider the interactions of the variable, process variables. So this one is real production data from the rolling process. Here, use machine vision to inspect the quality, which is the different like diameter, the size of the product, and the manufacturing process has temperature, current, force, and so on. So in each station, and this one is a multi-station manufacturing process. So the question is, if something wrong in the final product, what are the potential root causes and what are the variables responsible for this? So we use this model developed tensor regression, consider interaction effects. These 2 variables could be interacted. And then we do this case study. From here, as an example, we can see the quality index Y6, which obtained from machine vision, is related the stand number 8, and the diameter of this, the diameter of the quality more related with the speed of stand 8. And over there, see the quality Y6 is not related with that two variables, stand 3 and the temperature. So basically, we can see some quality issues. What are the potential interactions, responsible, not responsible, by doing that kind of regression using machine vision data. Another work we have done is image-based feedback control using tensor analysis. I think most of us, if you learn control theory, you'll know the feedback control can be a variable, vector, position, temperature, and so on, and then feedback to the actuators. But what if the variable to be controlled is an image, multiple pixels, high dimensional signal? So this one is really important in reality. For example, in the semiconductor manufacturing, we generate the wafers, we care about the profile of this. And this profile can be regarded as a machine vision image. And the process variables here, we make adjustment, will impact on this quality. The question is, I got this image, what kind of process variables I can make adjustment to improve the quality? And over there is the machining process. We can have a 3D point cloud measurement of the shape of the cylinder. When this depth of cut and the speed change, this cylinder should be a nice cylinder, but could be different shape and different dimension. So response is image, machine vision image. The control variable is the machine setting. How to find this one? So we developed this control theory to address those kind of challenges. One is high dimensionality of the problem, spatial temporal correlation, and also the noise is not IID. And we have this tensor-based time series modeling to this. Basically, this 1-2 tensor address the first two challenge, dimension, temporal relationship. And time series model emphasize address the 3, the data is autocorrelated. So how to do this work? From the historic data, we did multiple manufacturing with the process variable, machine vision response, we get historical data. And based on this, we can develop this tensor-based autocorrelation model. This YT is a tensor, is a tensor or image, it has an autocorrelation. And this xt minus n are the input variables can impact on this quality. So we develop modeling technique. And also after we have the model, during the production, we have the output from the machine vision through the model. We develop control strategy to adjust the process parameters to make output on the target. So this one is control strategy. So this is work we have done. And then we use validation of this, use a simulator, which is jointly developed with a major semiconductor manufacturing for lithograph. So different process variables adjustment can impact on the quality of this through this simulator. What the quality measure is on the right. Here you can see on this one, on this image over there, they have small errors, and error have different orientations. The error, longer error means large error. The error length becomes 0, so that will be perfect. So that's a quality measure. And we measure this quality response, make adjustment of this product variables, and try to improve the performance. So this is the simulation results. And over there, after a few steps, already 0. It's a 0. It's still like a step by step. This one is without control. You can see without control, the error length orientation is changing from 1 to 1. And after control, this become very good. So this is another thing we say, the in-process quality improvements through automatic compensation. And another thing we have done is in situ product quality prediction based on 3D point cloud data. And also this also motivated by a real demand from a company. This one is a medical medical device application. In this manufacturing process, the current practice is horizontally, what are the process? They manufacturing the gear, the gear manufacturing. So after you get the gear, in the middle, the red color is the gear, they have inline metrology, basically use machine vision to inspect the dimension of this tooth, dimension of this. And based on this dimension, if it pass this quality, they go to the warehouse, they do the selective assembly, basically try to find the best match and assemble them together. And this gear used in the tooth drill, a drill for the dentist. So the problem is, and then they do the final check over there. The problem is, if this tooth match not very good, this one will generate vibration in the end for the drill. And this vibration is very hurt for the patient and for the dentist's hand, I mean, after a long time, use it. So typically in that time, they use the manufacturing process on the top. They have up to 40% of drill throw away after they assemble because they did not pass the quality inspection. This is the reality. And then after we heard this one, and also we know they have the machine vision signal in the middle, this machine vision measurement device. They have this data already. They do the product inspection in this stage. We said, if you have this data, you have the process checking information, they have the match one by one. Can we use this data to develop a model? And after you have this model, we can have the measurements of this one, and through the algorithm, which the antler is the name we give to our algorithm, we can predict the vibration and the performance. So in this way, once in the middle, we have this one, before final assembly, we say this gear is acceptable, not acceptable based on our model. If this model is accurate, I can decide, keep moving to the final product, or this one not good, throw away. If I throw away these parts in this stage, it's much, much cheaper than the final one. Okay, so that was the motivation. We talked with the plant people and try out this. So in order to do this, we develop a set of algorithms. To start with, we have this unstructured, varying size 3D dimensional data, like here, the dot in the middle. And then we translate this one into a voxel representation. Basically, all the red dot is 1, all these empty ones is 0. So we can get that kind of representation. And here you realize we have a much more zeros, empty ones, than the ones with the data. So we try to have a balanced sampling tensor. So basically, for each one, this one is a cup. You can see the cup is a 3D point cloud. On the side, we put this one into another color. I mean, and all these empty ones, white color will be dropped off from our modeling. So we have balanced data. After this, we try to do a base tensor decomposition to find the key features, which is UI. And then we do the nonlinear regression from the response, which is a pass, no pass in this case. Vector response, Y, with this. So right now you can see we developed the concept step by step. But for the final optimization, we do a simultaneous optimization to find the meaningful features, the response, and solve this optimization problem. So this one have several nice properties. We can simultaneously optimize the regression and the low dimensional representations. Basically, what are the features meaningful for this response? And also, there are some other properties. The sample size is small. The test data is small. How can we develop this model more effectively? So those are the different properties. The paper here is available, and Dr. Cao can post this one with others. So after we have this algorithm developed and verified, they changed the manufacturing process in the middle. They inject this yellow color place. So basically, after they have the machine data, I mean machine vision data, they use our model, make a prediction, and based on this ordered prediction, we either reject the parts or keep moving. And in this way, they reduce the total scrap by about cost by about 61%. That's feedback from the manufacturing process. So here the example you can see. Machine vision is very important, but how to use the machine vision data effectively to improve the manufacturing process quality, reduce cost, improve productivity. That's need additional work on top of excellent machine vision capabilities. So this is the message I like to pass. The last topic, I like this very much. It's new, it's just accepted now. Is detonate, basically try to model nonlinear dynamic evolution of time-dependent three-dimensional point cloud data. So what is the motivation? Why this could be good? So motivation here, you can see here, this one is a landslide. So you can have a drone and measure this slide, and then you can see, assume May 1st, you get this landslide. And during this time, I mean, these measured points. And then next month are weather conditions, the rainy and so on, temperature and so on. So next month, the first day you measure again, they have a new point cloud, which is a function of previous months plus additional input. Same thing in the 3D printing. You print one layer, you scan it, you get the 3D profile cloud data. And then you have additional input here, and then print the second layer. The second layer, the dimension 3D point cloud profile is a function of last layer plus additional input. And another example is the detonation. So like a bomb. Once you have explosion, this one, time one, you have this one, depending on the design, the material, next time slice will be another 3D point cloud. Next one will be another one. So here has a 3D point cloud propagation again. So the question is how to model this is a very challenging issue. The common data, dynamic, nonlinear, temporal data is the original data, and the data is unstructured. It has a specially temporal spatial relationship with heterogeneous input, different types of input to impact the profile. And we are not only care about the profile propagation, but also reverse, because we want to know what the root cause. So in this way, we solve this challenge by using this method. Basically, we use Kuhlmann operator to address the nonlinear problem and study the encoding propagation, the forward and backward. The forward, the data to the next layer, and backward to this. And those are the input, heterogeneous input, table data, functional curve, image data, impact on this. Merge them together, we can get the model. Again, like I said, we have the paper published for this purpose. And we did one case study on the 3D printing. So basically you can see this heterogeneous data. We scan the parts layer by layer, become a 3D point cloud data. Based on, we print about 150 parts. Based on this, we get this model. And after you get this model, we print this layer and make a predict. And this one is our method. You can see quite consistent. Over there is a benchmark method. You can see the layer 10, layer 20 is a little not so accurate, more like a large bandwidth compared to this. We also try this one. We also try this one in the real experiment in the lab for the 3D printing for the control. So basically, this one, the layer by layer manufacturing. And we print one layer, and then based on print and our model, try to see what kind of adjustment we do to the control over there to make this layer smoother. And so we get a quite good result. So this is my last slide. I like to say machine vision has been widely used in smart manufacturing and provide very effective tools for process machine conditions and
product quality. And also machine learning and the data fusion are key components to link all those heterogeneous data together. And machine vision provide very important method and generate some impacts already. And the last thing I like to say is we need very close collaboration from the machine vision expert with the manufacturing expert and with data fusion, data science, and we all work together can make this happen more effectively. Thank you. If any question? Okay. Thank you. Thank you.
Okay, so our next session. So continuing our exploration of data-driven manufacturing, we transition from Professor Xi's session to the next captivating topic from Professor Colosimo, a professor at Politecnico di Milano and co-founder of the ADME Lab, a research lab on novel solutions for additive manufacturing, who will enlighten us on video image data mining for zero-waste additive manufacturing. Her expertise in industrial data modeling and control guarantees an insightful discussion. Let us warmly welcome Professor Colosimo as we explore deeper into the realm of cutting-edge research and innovation.
Thank you for inviting me, and I'm honored of staying in such, let's say, an interesting, workshop, because I do believe that this is going to be the future for many perspective in manufacturing and also in data mining for complex data, let's say. Just a few words to introduce myself. I'm in Politecnico di Milano, which is a technical university that has a very good, let's say, position in rankings, in international rankings, especially in the manufacturing and engineering side. We are in the top 20 worldwide according to the QS. And as you will see in a while, I've been always spending my time between the blue and red. Let's say this is my short CV. The red stuff staying for manufacturing part. So at me, it's a additive manufacturing lab in Polimi. While the blue side of my CV, it's on data mining and data science. So IC lab means industrial control, or IC in terms of in situ monitoring, and you will see some example. The same is true also for my editorship commitment. Some are related to additive manufacturing and some of them are more related to data mining and data science for quality. And my commitment, let's say, in Europe and in the US in terms of trying to foster and see what's going to be the future of manufacturing. And I've been recently received some awards. This year was quite nice year for my award. And again, they're going in the interplay between manufacturing and data mining. I will start and basically I will remain in all my talk on additive manufacturing. And if I can just bring you some picture of what is additive manufacturing, it's just shown in this example of parts. As you can see, there are parts from many different, let's say, materials, size, shape. Some of them are more in the automotive and aerospace. Some of them are biomedical. Some of them are even 3D printing of pasta, or as we will see in a while, bioprinting, which means 3D printing living tissue. And what do they have in common is basically complexity in shape. And I will just use this as a driver of many conclusions that I'm trying to, at the end, arrive to using additive. Because let's say the way in which the process works, it's quite easy, but it brings a lot of new perspective in manufacturing. This is just an example on how we can produce a turbine blade with additive. This is the well-known process called powder bed fusion. I'm discussing now about additive manufacturing for metal. So there's a thin layer of powder that is melted in each layer. And then after second stage, another layer of powder is spread and it's melted selectively. So it means I'm just melting the powder where I need the solid at the end. And this allows us to arrive at the end with a very complex shape. Why additive is so interesting for many different perspectives? It's clear from the, let's say, graph that is shown over there, in which there's on the x-axis the complexity of the part I'm producing, and on the y-axis, it's the manufacturing cost per piece. Usually the blue line represents traditional processes in which you can achieve very complex shapes, but it means a lot of cost for the single part. So you need to spend a lot of money for each single part. While the green line that you see, it's flat, it's the cost per part as a function of complexity of the final part for additive manufacturing. As you can see, it's almost flat. So at least in principle, it means that I can reach complexity for free. It doesn't mean that I need to spend money for having complexity in terms of shape. Clearly, you need to take advantage of this complexity. Complexity, it's not, let's say, an advantage in itself. These are just some examples of parts that you can produce, let's say, in the aerospace. You can see that if you want to move green, I mean, at least in Europe, we have all this idea of the twin transition from one side digital, on the other side green. And so, I mean, if you think about the weight reduction that you can have with such complex shapes in the aerospace sector, the few examples are showing significant reduction of weight and waste and cost. Reduction of weight in aerospace means reduction of CO2 fingerprint, reduction of the fuel you're using. So it means a lot of advantage in terms of green transition. The same is true if you are dealing with machinery and tooling. The example over there, it's a mold where all the channels that you see are just internal channels with such complex shapes. These internal channels allow you to subtract heat where you need. Unfortunately, with traditional manufacturing, channels can be done only with an axis that is a straight line. So thanks to these complex channels inside the part, you can have an extended lifetime and improve, let's say, consumption of energy while you are doing tooling and molding in this case. And you can enjoy also the complexity in biomedical implants. The well-known example is the hip implant, in which you can customize the implant for the patient. Since complexity is for free, you can just change the design in the CAD file and then go to print a very different hip implant for my body, let's say for my bones. And so this is going to create an additional advantage of complexity. And the oil and gas sector is also a similar job if I can improve, let's say, the performances, the thermomechanical performances. This is just the new frontier. I've been just starting a new lab that it's called, let's say, with some co-author and co-founder from the biomedical department of my university, that is called 3D Cell Lab. In this case, what we are mixing in the 3D printer, it's bioink plus living cells. And we have all the free type of process you can see on the bottom. I will not provide additional detail, but I can just say that printing skin and printing bones, it's easy. I mean, we cannot really say that we are able to print organs as everybody would like to. I mean, it's a long, let's say, long research needs to be done. A lot of research needs to be done for arriving to organs, but at least in principle, this is a news for the New York Times last year that is showing that the first 3D bioprinted here was printed, let's say, and installed on a patient. And this has a lot of advantage. Clearly, bioprinting is going to provide additional advantage in pharmaceutics, in life sciences, in biological research, because I can test the drugs on some living tissue that are not coming from real people. What is, let's say, what all this type of stuff needs, what is the connection with, let's say, image? This is clear if we start thinking why additive manufacturing is called a digital manufacturing process. So you can start designing a product on the CAD. So it means that you can start, for instance, enjoying image and video image also if you are dealing with the virtual world in some sort of, let's say, digital twin of the part that I'm going to produce. Then you can even simulate the process, but then I will spend more time in the part when we are start producing the product. And in this case, thanks to the fact that additive is an open process, you can have a lot of images, a lot of information, a lot of video, and I will discuss what type of information you can gain. I'd like to say that I will focus my talk on additive, but the same type of information are really well available in welding. A lot of processes that are related to laser or electron beam. You can exactly go in the same direction of having all this video available. And then the end of the story, it's that you need to qualify. And again, this is a digital, let's say, analysis of the part done by X-ray CT, computer tomography, in which all the dots means that there are some pores inside the part. So it means that you have not been doing a good job. And so you can go back redesigning or changing the process parameters. The issue is that there's a lot of attention, and as you will see in a while, there's a huge literature increasing on the idea of, let's say, using let's say, in situ data. All this left-hand side of my part, it's showing some in situ data. In situ data can come from camera that are mounted inside the machine and then can take image at each layer or video image, and I will spend some example on video image. And there's also the possibility, oh, sorry. I don't know, it's coming from here. Let me just show. And that some image that is coming also from thermal camera. So it means that you can even enjoy information about temperature. Let me see if I can just show this video, because one additional direction, it's what is called a coaxial. So I'm following, as you will see in a while, the laser. And so I will be able to follow what's going on. These are just image of the melt pool where the laser is hitting the powder and is creating the melt that then solidifies. And this is just simple, and it's available in many processes and in many machines, just following the laser that is going down, hitting the powder. And then I'm keeping back the information from the radiation. And just by a splitter of the beam, I will be able to have an image of what is going on while the laser is melting the powder. And this allows us to have a lot of information on this, let's say, condition of melting, which is what we are interested in. Here it's a beam splitter, and here I can have a camera or some photodiode that is taking advantage of the in situ information. Okay, why do we need to spend a lot of times with all this data instead of waiting to have the final part? The reason is that I can see the defect as soon as it happens. And so it means that I can reduce the waste of energy, material, and so on. All these information are, at least in principle, free. I mean, there's no additional cost, because if you can put a camera, most of the machines have a camera mounted on, it's just a matter of taking advantage of all this data, and so being able to analyze all those data. And the other issue is that I can even in principle understand better what's going on, so improve my knowledge of the process, but obviously also controlling, which means avoiding, or as soon as I see some sort of trend of deviation, I can act on process parameters in situ and inline, and so I can go in a feedback or feed-forward control. So it means, at least in principle, avoiding defect at the end. So if you think about the literature on in situ monitoring on additive manufacturing, there's huge amount of papers coming out, a lot of patents also, and startup that are just trying to, let's say, combine the, as the sentence is saying on the top, eyes that the machine already have, all this video that you can take, with, let's say, intelligence, which means I should have a brain also that is able to take advantage of all those data. And the idea is that I should, at least in principle, arrive to first-time right production, so no need to repeat over and over the same type of process. But I can, at least in principle, make each part different from the previous one, because I'm in real time taking information that I need for understanding how to manage the process, and clearly reduce waste and reduce defects. I will just provide some examples. I will not go in deeper detail on the type of analysis we have been doing, but there's all the papers that we have been writing. I will start with some example on images for in situ monitoring in AM, and I will start with free forms. So these are images that are captured while I'm producing the part at each layer. Then I will just spend a few words on a complex shape that is called lattice structure, that is also, let's say, very used in additive manufacturing. And one example on textured surface. So here the random texture, it's going to create problem in our image in detecting the defect. So this is why I thought the 3 examples are quite interesting for showing what are the challenges we are facing when we deal with image in AM, in situ monitoring. And then I will move to video image, so it means the dynamic, and I will spend a few words on how to detect hotspots thanks to the video image. And the second example, it's focusing on sputtering. So there's a lot of interest also, not just in looking what's going on while the laser is hitting, but what is coming out from the melt pool that is called sputtering, because this can be related to porosity at the end. So image, first of all, usually we are used in the lab to produce very, very simple specimen, cubic part. This does not make any sense with additive because we want complex shapes. So we start thinking about complex shapes. An example I'm showing is referring to a real part produced for space, Thales Alenia space. As you can see, the part is quite complex. What you see here, it's just that we are taking image at each layer of the melted zone, and we can kind of reconstruct in situ and in line, so make an inspection layer-wise of what is the shape that we have been printing with respect to the nominal shape to detect a defect at one layer as soon as the defect is there. And the way in which we did this type of, let's say, approach, it's just taking an image, create some sort of image detection, edge detection, thanks to some active contour. And thanks to, this is something I really like to mention, the knowledge of what we are doing. We are not observing nature. We are observing a process, and we decided what should be, at least in principle, the shape at that specific layer. We have a lot of information that we can embed in our edge detection algorithm. And then here it's just the comparison of what we have been printed with respect to the nominal shape, because again, we know the nominal at that specific layer because we ask the machine to print on that path for that specific layer. So we can compare what it's at that layer, the real with respect to the nominal, to detect deviation. The problem is sometimes that we have a lot of randomness and uncertainty in this reconstruction because of the lighting condition, because of the strategy, because of the material, and because of the machine. And so what we have been developing is some sort of uncertainty quantification. So we have been working with some order statistics, so taking the max deviation at each layer, being able to estimate the unknown randomness of this deviation. And so being able to detect with an out of control just the case in which there's a huge defect. I just want to emphasize that companies really hate false alarms. So if I'm even very, very good in detecting something that is deviating from the nominal, but this is due to the uncertainty of my measurement system, this is going to be at the end skipped by the process engineer because they don't want to see a lot of false alarms. So the path with them, it's just give me an alarm, even if the defect is huge, but you need to trust that this is a real alarm. We've been doing exactly the same type of approach for this type of shape that are called metamaterial or lattice structure. It's something that is really useful in many different applications. It's are shapes that you cannot do with any other process but additive manufacturing. And so you can see that since it's a cell full of void, this is going to be lighter. This is going to have a very important impact in terms of the reduction of vibration and can be of interest in many different sectors. I'm just mentioning aerospace, biomedical implants, and also competition in racing car. Again, what we've been doing here is just doing exactly the same stuff. So taking image at each layer and being able to compare layer by layer the deviation of what we have been printed with respect to what was the nominal shape. And we have been showing that just managing and somehow being able to deal with the over variability that you can see from one layer to the other, we have been using some sort of weighted linear model. You can be, at least in principle, able to have an in situ reconstruction that is really close to what you can do ex situ. X-ray CT, it's the black line. This is showing just for one specific cell in the lattice, the deviation from the nominal shape. This number is just the deviation in terms of pixel. As a function of Z, as a function of the layers that you have been producing. So you can create this shape that is representing the deviation of the nominal with respect to the real. The black, it's X-ray CT. So I'm taking the best that I can at the end using tomography for detecting this deviation. While the blue interval is what you can do in situ and in line in real time. So it means long time before you see the final part, thanks to this image-based reconstruction with some attention to uncertainty and keeping under control the variability of the lighting condition. Since we were, let's say, struggling a lot with the variability of the lighting condition, we have been inventing, let's say, or patenting a new solution that is called ScanIt. So we have been moving also close to new sensor, and I think that this is quite interesting. The key idea of this new sensor, it's just to mount on the powder recoater. So as the layer should be starting with the powder recoating, we have been attaching to this powder recoater a scanner, like the one that you use for scanning your document. So it means that you are kind of scanning the powder, the powder sheet, let's say, and the powder bed. And so you can have a quite accurate reconstruction of the melted, just the melted image, thanks to the scanner that is going back and forth. And this is for free because the powder deposition, it's a necessary step. So it's just taking advantage of this going back and forth for taking a close image with the stable lighting condition. Just I will show how it works. It's called ScanIt, and we're going to have a startup out of this idea. This is the powder recoating. This is the lighting because this scanner is taking the image of what we have been printing, and then it's going back and taking an image of the position of the powder. And you can see what is amazing in terms of the change of resolution that you can gain if you are using an external camera. Is each of these pictures, it's showing on the left-hand side what you can see in the traditional machines in which you have an external camera. On the left-hand side, on the right-hand side, what you can do with our ScanIt, with our scanner mounted on the recoater. You can see that the resolution is really, really amazing. And you can have a clear picture also, not just of the border of what you have been printing, but also on the 3D surface. So it means that you can start even analyzing the roughness of the printed job. This is just to say that when you start dealing with data for vision, maybe you can combine your know-how and go closer to people that is building the sensor and saying, why can we work together in creating something that can improve the type of data quality I have for going ahead and doing my job. This is also, let's say, the last example in terms of image. In this case, we are dealing now with polymers, and polymers used to create this random texture, this random structure. So if you want to detect the deviation from the nominal shape that can be due to over extrusion, under extrusion that are shown on the bottom, you need, there's a pain related to this randomness of the texture because it's not so easy to make an edge detection algorithm. And in this case, taking, let's say, advantage of some work that was dealing with textile industry, we have been using random forest and then applying some clustering analysis to be able to detect the defect at the end. I will not spend much word, but I mean, it's a paper that it will be available soon on IISc transaction. Few comments on video. I mean, image, it's tough, but video, it's even worse. In this case, this is the video, thanks to a camera that is mounted outside our machine. And I'm showing here what is the defect we want to detect. It's this guy, which is called hotspot. If you go back, you see that the natural in control condition, it's that the laser is doing his job going back and forth. But at a given point in time, it can happen that one point remain hot for a long time. And this is a defect at the end. This is going to create some defect on the part geometry. So the key idea is to have this sequence of frame and being able to let the laser do his job, random job, let's say, and be able to detect something that remains with high intensity that is not the laser for a long time in the same location. We have been doing a lot of stuff. I mean, unfortunately, this is not at the right position. In any case, the work we have been doing is using some sort of specially weighted PCA, and it was plus clustering. And in this case, we were very, very good in detecting the hotspot as soon as it happens to appear. But there are a lot of different solutions. We have been also playing with some friends in Georgia Tech on some spatial temporal statistical monitoring, and also applying some neural network with some supervised learning. And more or less, they are going to be able to do the same type of, let's say, solution, which means, again, being able in real time to detect the defect that is going at the end to create a problem on the final shape. Last few words on sputtering. We've been thinking about not just focusing on what the laser is doing, but just focusing on what is coming out from the laser that are the sputters, because it's well known, at least for people that is working on this type of problem, that sometimes the density, which means the voids inside the final part, depends on the sputtering phenomena. The example I'm showing here on the left-hand side is the black represent where the laser is doing his job, and the laser is clearly moving, but we have been recentering the laser in the same position. And all the red, the dots are the sputters that we can see in a sequence of frames, so in a video. As you can see, there's a sputter signature that is showing, in this case, it is quite different in the sputter signature that you can see on the right-hand side. In the first case, this is a sputter signature that is related to an in-control solution. So there's nothing wrong going on. So these are normal sputtering phenomena. While on the right-hand side, the problem is that it's usually creating a lot of porosity at the end on the part. So it means that this is a, let's say, condition that can be considered as over melting, too much energy. And so if we are able in real time to detect that this is going to happen, we are going, at least in principle, able to avoid the pores at the end on the part. So again, how can we model these spatial problems, these spatial, let's say, phenomena? What we have been doing is, again, making some sort of reduction of synthetic representation of the sputtering. And this was done thanks to the replay K function. The K function is basically representing how many events you can see as you move far from one point. You are counting the number of sputters you can see, and then you are randomly changing the location in the space. And then you are creating this function that is kind of representing the spatial phenomena. So if the spatial the spatial point process is concentrated, is clustered, the type of distribution, if it's normal, uniform, it's reflected in the different shape, let's say, of this K function. This to us is just a way of reducing complexity. Instead of just counting the point process, we are representing the spatial shape of this point process. And we've been able to show that if we are playing with process parameters and phasing, as I was saying, different condition of undermelting or overmelting, all the level that you see have been obtained just by changing the process parameters. The best condition is level 3, it's the best, so mean porosity, and all the other conditions are wrong in terms of the spatial signature. We've been able, thanks to this K function, to see that we can detect the best condition quite well, thanks to K function fitting plus functional ANOVA. And if we compare, we know what is the best condition, which is condition number 3. Thanks to the contrast of this K function, you can see that all the other conditions, overmelting and undermelting, are represented with a different contrast. So the contrast is not a flat curve, it's showing some difference with respect to the flat curve. So it's basically saying that the sputter signature is different in overmelting and undermelting, and you can detect this, at least in principle, in situ and in line. So I'm arriving to my conclusions. My first conclusion is we used to say that the twin transition should happen, so combining digital and green. The bad news is that digital, it's usually not green. So it means a lot of, let's say, energy consumption for, let's say, data storage, data analysis. And so the first thing is that we need to build, this is just an example of how many data for 24-hour build, depending on the fact that you are just taking layer image, coaxial photodiode, moving to off-axis high speed, or even infrared, which means thermal camera. So the big data, it's not a goal, it's an opportunity. So you need to, I think, be some sort of dietary data. You need to select the data that you want. You can start monitoring a lot of stuff, but then you can decide what are the data that are really counting. And so data reduction, sensor, and varied selection, it's going to be the future if you don't want to spend a lot of energy in doing this job. Simpler the better. A lot of companies want to move computation close to the machine, so edge computing is what they are asking for. So it means that you need to just take the information you need and then get rid of all the other stuff. And this is why moving from video or spatters image to simple stuff like a function, a profile data, functional data is going to be the solution. Data fusion is also possibly going the right way for, let's say, combining information. And eventually, last comment, data is not information, and information is not knowledge. So you need to some sort of, let's say, robustness, knowledge of the process, a lot of attention to what the process engineers know about the process, being able to interpret what you are doing. And so again, sometimes AI are not so friendly from this viewpoint. And so I really go in the direction of interpretable AI. And then also physics-based data modeling. There's a lot of knowledge on the process, on the simulation that needs to be embedded in the way in which we are taking data and also analyzing our data. That's all from my side. Thank you.
Thank you, Professor Colosimo. Very interesting talk. Now moving on to our award announcement. Before we go to the...
No questions.
Okay, we can take one question if anyone has. Yeah, we have to.
So let's take the coffee break.
Or
to do a presentation.
Okay, okay.
yeah.
And we will award the best paper at 10.
At 10. Okay, sounds great. Yeah.
And the professor, she went to gather with the professor.
Yeah. Yeah. So
A very general question. I'm Marco Pisani from University of Verona. Maybe it's too general, but at some point, yeah. So thanks for the talk. So at some point you said that you are using a random forest for detecting overeating or something like that, and then you use a PCA for visualization, etc. So my question is, why didn't you use some deep learning technology instead of more old-fashioned machine learning?
Yeah. Now the random forest was done for the texture, so that was kind of able to get rid of all the noise, let's say, it was so observed over there. And then the PCA was, and then after the random forest, we were just playing with the residuals, and it was quite straightforward. So I was doing his job of detecting what is wrong. The PCA was used for the spatial video image. In that case, we were interested in some steady state because the hotspot is something that remains hot for a long time. So it's some sort of autocorrelation in terms of time instead of, and it was quite effective. But as I was saying, the same problem was also faced with neural network and deep learning, and it was quite effective. The only issue is that in that case, we need someone that was supervising the labeling at the beginning, saying this is okay, this is not. And while in the other case for the PCA, it was unsupervised. So clearly there's some trade-off. I mean, you need to train something to detect what you want. In the other case, you are just, at least in the way in which we have been developing the PCA, it's just that you know what is the hint control and that's it. But all of them are competing, let's say. I have no recipe at the end of what is the best. And I have no, let's say, general comment. I mean, all the approaches are okay at the end. It seems that they were all working well.
Okay. I was thinking about interpretability, but yeah.
Yeah, interpretability can be an issue, and the PCA is really going to help us in this direction. Sure.
Thank you so much for the interesting talk. I had a question. You said that to detect the anomalies or the defects during the production, you compare the real products with the nominal products. So for the real products, we acquire the information by camera, so it's image. But on the other hand, if we define the nominal, the information for the, for example, machine, it could be a 3D CAD files. So how do you compare these different two types of information, especially when it comes also to the video? The nominal products at each time step is different. So are you defining images for the nominal data at all time steps? Would you just clarify this?
Okay. So the first thing is that when you are dealing with layers, layer-wise, the problem it's no more 3D, it's going to be two-dimensional, thanks to the fact that you are kind of observing a slice. And so the nominal, it's your CAD file. At the same slice, you know exactly what should be. Also because you are asking the laser to do exactly that path. So you know everything about the nominal, and you are observing the real thanks to the image. Clearly, if you want to move to the 3D, you need to change a little bit the way. We have been trying to do, there's also always a registration step so that you need to realign. But again, this is an easy job since you are controlling the machine, so you know everything that you are doing at that specific point. So combining the nominal, overlapping the nominal to what you have been observing, it's an easy job if you are good enough, let's say, in this defining some landmarks. We've been also spending some time in working 3D. In this case, it's the X-ray CT because in situ you don't have a 3D image. You have always the slicing because you are layer-wise producing the part. But we've been doing exactly for freeform 3D X-ray CT with the nominal. And in that case, we have been using outdoor distance or some other, let's say, way of, after realigning, measuring the distances between what you have been printed and what it's in your, let's say, idea, the nominal shape, with some voxel-wise condition. I think that there's a lot of research also to be done in that direction, especially if we're moving to complex shape. But the outdoor distance, it's a technometrics paper. It's been doing a quite good job.
Thanks to your talk. I have another AM question. So in my experience, there's a lot of pushback against using in-process monitoring with machine learning for qualification of AM parts, especially for laser powder bed fusion. And I'm wondering if you can talk about like what your experience has been and what you see as a path forward for making it so like a operator doesn't have to flip through like the CT scans at the end in order to qualify a part, especially for like let's say like aerospace applications where like a critical failure or too much porosity could cause like a aircraft to
Okay, thank you for this question. I don't know how to go back because I'd like to show that one of the projects, it's this IM space with the European Space Agency that is exactly going the direction of having someone that can let them trust what you see in situ and in line. And there's a recent standard from the ASTM and NASA that is exactly showing all the capabilities of in situ monitoring. Just to say that this is the direction and we are not ready. And especially when you are dealing with the indirect measurement of the quality, like mel pool, there's a lot of, let's say, trust that you need to bring to companies saying, okay, when the mel pool is strange, the mel pool is strange, it means a defect, you need to really prove this. While some other direction, like observing the shape and comparing with the nominal, are more mature for going, let's say, in the market at this point in time. And as a matter of fact, a lot of companies producing machines, they want to embed this knowledge in their machine. So there's different TRL, technology readiness level, but I'm quite sure that the direction is the one of, let's say, trusting and being able to analyze those data in some, let's say, robust way. So they want just to see when the problem is there, and you can say that the problem is there. They don't want to see some guess of problem or probabilistic idea of problem. As soon as we are good in showing that this is an effective way to go at the end, I think it's going to be the direction for the aerospace sector. We are now working with a lot of companies in the aerospace sector. They are bringing this knowledge inside the machines that they are using, turbine blade, for instance, and with some nice result.
I think we can take one last question.
Okay, so my question is, from what you show us, the manufacturing you guys do, or the kind of thing, the applications you do, you have very high requirement on error you can make from the prediction results, right? You're working in millimeter kind of range. Do you find that the current machine learning or statistical machine learning type of approach, the kind of limited, what kind of limitation are there for you to use in your application to achieve that kind of accuracy or robustness you need?
The first question, it's usually depends on the sensor. So each sensor has its own resolution, the capability of detecting some size of defect. So for instance, the pixel, what is the dimension of the pixel? So the first thing is that you should be aware that you cannot detect defects that are smaller than a given amount. And the second, and this is just mainly focusing on sensor. The second step is how I can, let's say, use those data, these pixels, for saying something more on the defects. So the way in which I'm managing and use machine learning for doing the job. Again, if you are able to show with a lot of different examples that your algorithm is doing the job of detecting defect over a given size, I think that this is the way to go. I'm always saying we cannot be very, very precise as X-ray CT, but at least in principle, for any defect that is larger than, you can trust what we are saying. So it's just a matter of being sure of what you can assure to the companies, and then they are going with you, let's say, in saying, okay, I will keep the machine learning plus in situ data just for this type of defects, and I will leave all the other one for the X-ray CT.
Thank you. Yeah. Thank you, Professor Kolosim and Professor Shi. So I think what we are going to do right now is to announce the award for the best paper, best research paper. And would like to invite Professor Shi on stage to deliver that paper award to yeah. So the best paper award goes to Wei Ji from University of Alberta. Do we have Wei here? Or anyone from the team? Yeah. Professor Shi, can you come over here? Like, do we have projector? Thank you. So we have like 4 minutes of break. So maybe we can just take like 3 or 4 minutes and then we'll resume our session for the research presentations. Thank you. So which paper? And we can see the screen. Okay. Okay, so now we will have research presentations for 9 papers with 10 minutes of presentation and 2 minutes of Q&A. So the first paper is from Yang Yu, Michaelis, Ying, and Tanya from Imperial College London, and the topic is towards automated polyp segmentation using weakly and semi-supervised learning and deformable transformers. Yeah. The notes, it's just not coming. The notes is not coming. Can you bring your laptop here?
Hello everyone, my name is Michalis and I will be presenting our work named Towards Automated Polyp Segmentation using weakly and semi-supervised learning and deformable transformers. First of all, I would like to thank the workshop organizers for giving us the opportunity to present our work. This was a collaborative work between researchers from Imperial College London, and my fellow co-authors are Guangyu Ren, Jing Yuan, and Tanya Stathaki. Polyp segmentation is a crucial step for computer-aided diagnosis of colorectal cancer, which is one of the most common types of cancer in the world. Most of the polyp segmentation models must be trained on pixel-wise annotated datasets that are tedious and time-consuming to produce. Furthermore, annotating images for polyp segmentation must be done from specialist physicians who would in turn need to sacrifice their time dedicated to the patients for annotating images. To this end, we are presenting our research that addresses the aforementioned problems. In this work, we are investigating the problem of automated polyp segmentation using limited supervision. Therefore, we propose a framework for training a polyp segmentation model using only weakly annotated images and unlabeled images. In our work, we make the following contributions. We provide the first publicly available weakly annotated polyp dataset named WPolyp, and the link can be found in our paper. We present the first weakly and semi-supervised polyp segmentation framework named WS-DefSegnet. We propose a novel weakly supervised loss function named sparse foreground loss that alleviates the false positives associated with weakly supervised learning. Lastly, we propose a novel progressive multi-scale architecture with self-attention mechanism for feature enhancements that significantly improves the performance of our model. Regarding our weakly annotated dataset, WPolyp is created by weakly annotating an existing polyp dataset, which contains 1,450 images in total. We randomly select and annotated 750 images with simple sketches, including lines, scribbles, and circles. Additionally, unlike other weakly annotated datasets, the rest 700 images are left unlabeled, maximizing the labeling efficiency and dataset sparsity. Further details can be found in our paper. Moving on, we will discuss our framework in 3 parts. Firstly, we will discuss about the weakly supervised training phase, then the semi-supervised training phase, and then the architectural design choices that we made. In the weakly supervised training phase, we train our model using only the weakly annotated data. We use a weighted average loss of 2 loss terms, LP, which denotes the partial cross entropy loss, and LF, which denotes the sparse foreground loss. It can be seen from the figure that the partial loss uses both foreground and background information, while the sparse foreground loss uses only foreground information. In the semi-supervised training phase, we adopt a teacher-student training paradigm and use the model trained from the weakly supervised training phase to act as a teacher. The teacher model assigns pseudo-labels for all unlabeled images of the dataset, and we train the student model using a consistency loss between the predicted pseudo-labels and the student's predictions. The loss function used to train the student model is the weighted sum of two terms. The loss function used in the weekly supervised training and the consistency loss between the teacher's pseudo labels and the student's predictions. Moving on the architectural designs. Our network uses REST2net as the backbone and utilizes the proposed deformable transformer encoder NEC to enhance raw features produced by the backbone. The enhanced features are passed to a vanilla segmentation head. The additional branch in the DAS box only exists in the training phase. We propose the DTN module based on a single encoder of the deformable vision transformer and 3 feature add blocks. The overall structure of the DTN is shown on the left. The reason we use the deformable transformer is that its attention mechanism is suitable for adaptive feature extraction. Our model fuses features adaptively across multiple levels at learned locations so that the classification of each pixel considers the surrounding features with learned weight. Therefore, the attention to features inside the polyp can help the classification of pixels at ambiguous locations, such as edges. Here, we draw the detailed structure of the encoder of the deformable vision transformer in the yellow box in the middle. It mainly contains a deformable attention block and a typical feed-forward network. We show the details of the former in the green box. The deformable vision transformer, it was first proposed in 2021. It introduced the idea of deformability into traditional vision transformers like DTR in order to reduce the memory cost. Our model takes advantage of this deformable encoder so that we can afford the training and achieve improvements at the same time. Besides the deformable vision transformer, another highlight of our DTN module is the feature add block. This block is designed to compensate the input feature map with enhanced features. As you can find on the left, we stack 3 blocks after the deformable encoder, and they serve as the last steps of the DTN module. The detailed structure of a single feature add block is shown in the middle. The original feature map is embedded via convolutional layer and a prelude function. The enhanced map is upsampled to the same resolution as the original feature map via bilinear interpolation. Finally, the results of these 2 branches are added element-wise to form a compensated feature map. With multiple blocks, the input features are complemented progressively to output a more expressive feature map. Moving on to our results, and more specifically the ablation study, we conduct experiments on 5 widely used polyp datasets, namely CVC colon DB, ETIS, K-Vasair, CVCT, and CVC clinic DB. We follow previous works and use 2 metrics to calculate the performance of our polyp segmentation method, namely mid-dice and mid-intersection over union. Here we ablate every component of our work. We start by having the baseline of using only the partial cross entropy loss in the first row. Performance improvements can be seen when sparse foreground loss is used in the row 2. The semi-supervised learning is utilized in row 3, and the use of DTN in rows 4 and 5. Furthermore, DTN can also improve the performance when trained in a fully supervised way, as shown in the last 2 rows. Finally, from the visualizations of the segmentation maps, the merits of our method can be clearly seen. The improvement from training only with the partial loss in column C to the complete version of our framework in column F is very significant. Lastly, we compare our method with the state of the art in polyp segmentation. It can be seen that our method outperforms most of the state of the art polyp segmentation methods and is only slightly inferior when compared to 2 of them. However, our method uses around 7 times less annotated pixels than the supervised methods and around 2.5 less annotated pixels than the semi-supervised methods, which makes our method a lot more efficient. Lastly, I would like to thank you for listening to the presentation. I hope you enjoyed it. And in case you have any questions or are interested in this research direction, please do not hesitate to contact us either now or through the links here. Thank you very much.
Yeah, we can take 1 or 2 questions if anyone has any question here or virtually from the audience. Thank you.
Thank you very much.
Okay, so our next presenter is Lasita from Industrial AI Lab. And the topic is XDNet, a few shot meta learning approach for cross-domain visual inspection.
So hi everyone. I'm not Lasita. I'm Joy from Hitachi America. So today Lasita and I in R&D lab focused on industry AI, and we are based in Santa Clara, California. So today I'm helping my colleague Lasita to present their work on the XDNet, a few shot meta learning approach for cross-domain visual inspection. So as we all know, like data labeling is an expensive and work. So nowadays there's a lot of well-trained models on large specific tasks. So on large and also on very large public data set like Coco, Pascal, or like ImageNet, which designed for specific task. So our goal is to utilize the knowledge which they trained on from the previous task and apply for the new domain specific task, which only require a very few domain specific label data. And within that, we can train the model more efficiently. So our domain here is the industrial visual inspection. Like we want to automatically detect a crack on our surface or a disconnection on a welding or a scratch on a car or a hole on a camera lens. So we already did some like customer project before. So we want to apply the same kind of techniques on any new project to to train the model more efficiently. So for example, we want to utilize deep learning method based to automatically detect or do the anomaly detection process. So since the defect is is very tiny and very domain specific, so the current models requires a large amount of data and highly computational cost to train a new model. So for moreover, like I said before, like for every new applications, we might requires a new data set and a new model. So to address the problem that can we train a model within which can be generalized across many domains. So we leverage on the method of few shot meta learning. We want to learn a variety of tasks and generalize to a new task with only a few examples. So for instance, we have the figures is different in the slides, but so if we have a well-developed classification model trained on thousands of flower images, so it is not applicable to directly influence on bird classifications within only like 5 or 10 bird images. So we hope the cross-domain meta-learning can solve the few shot problem. So here is our architecture used for the XDNet. So it's basically two phases, the meta training and the meta testing phase. In the meta training phase, we select the SE ResNet as the pre-trained backbone with the squeezing and excitation modules can ensure the model, the channel-wise attention, and the anti-aliasing low-pass filter can help the generalizations. And then we freeze all the other layers, only train the last 2 layers for the training. And we also use the supervised classification loss and the triple margin contractive loss to ensure more generalizability. And during the meta training, we took a snapshot of ensembles of the backbone we select the best 3 snapshot based on the validation data set. And in the meta testing set test, the support and the query images go through the ensembles of backbones to get the feature representations, and then they are concatenated into like a 1D scalar. And then in the n-way k-shot settings, n represent like how many data set, how many domain we have, k represent like how many examples in each data set. That's the upper bound. So in the k-way, n-way k-shot settings, one prototype represent one class by averaging k examples. So there will be n prototypes in total. So the n prototypes and the query features gonna go through the SOT feature transform to map the features based on their cosine similarity. And then they all will go to soft k-means classifier iteratively to get the query set prediction. So we also try out other like gradient-based method and the example method, but we found out like the soft k-means will be the best. And then we utilize the MV tech as a benchmark dataset to evaluate our result. So for example, it has classes like cable, carpet, and leather. So it has 14 classes in total. For each of the class, they have different defect tab, defects from 1 to 4. So to ensure our n-way k-shot setting. So since we want to measure the performance based on the n-way k-shot task, we utilize the normalized accuracy as a evaluation criteria. So the ACCRC is a random classifier accuracy. So 5 class means like 20% accuracy. And then our normalized accuracy is based on those. So it's gonna range from 0 to 1, like larger number means better performance. And also other than the XDNet, we also compare our performance with other baseline models. So like first we train from the scratch, we use one single backbone feature extractor, just the normal, and initialize the weight based on the ImageNet, adding a task specific MLP. So, and then train them directly on the task sampled at meta testing set, no meta learning here, no meta training here, sorry. So we also compare the transfer learning, same architecture as from scratch. The model is trained only also on the meta training phase. And third one is the ProtoNet, is a meta learning algorithm, and we train them in an episodic manner in the meta training phase, which like one class after another. We train the cable first and then the carpet. And in the meta testing phase, instead of using the soft k-means, it obtained the class prediction based on distance-based mirror between the query and the support set. So here's our result. The MV tag dataset have 14 classes. Out of the 14, only 8 of them have like 5 ways 10 shot. So we design a 14-fold cross-validation to ensure at least 2 dataset overlap between each fold. So the blue bar is the performance of the XDNet. And so across all the 14 fold and also on the average, the performance, I think we can conclude that the XDNet perform better than all the other 3, at least 1 standard deviation, even for the average. We also average the normalized accuracy based on different classes, because we have 14 classes in total. And we observed like only for the capsule, okay, the protonet gonna perform better. And we also found out we have higher performance on the domain like carpet, leather, and tile, which kind of have a uniform background without the object like pop up. And we have some ablation studies, which we cut out some modules we used, and like the architecture and the feature transform, the ensemble and the constructive loss. So, so from the result, we just can see like the backbone architecture had the biggest impact on the performance, and the feature transformer had the least compact. So in conclusion, we found out the meta-learning is promising for industry application. We designed a cross-domain meta-learning architecture called XNet, which is promising on few shot classification problem. And we evaluate the performance based on the MV tech. And also we have ablation studies shows the change of the backbone architecture had the most significant effect on the performance. So the next step, instead of doing the classification, we want to investigate the few shot setting in the segmentation problem. That's it. If you guys have any questions.
Any question for Joy? Okay, so next presenter is Yizhu Jin from Beijing University, and the topic is glass wool defect detection using an improved YOLO V5. He is going to present virtually. Yizhu, can you share your screen and start the presentation?
Yes, can you hear me?
Yeah, we can hear you.
Could you please stop sharing the screen because I want to share my PowerPoint? Oh, okay. That's return menu. Oh, is the PowerPoint okay? No? Okay.
Yeah, we can see your screen now. You can start. Yeah.
Okay, thank you. Hello, everyone. Today I will introduce you the related paper, glass wool defect detection using any oops. Wait. Sorry, there's some problem with my Zoom.
You're breaking a lot. Sorry, we cannot hear you. So can you reshare again?
Now can you see this? Oh no, sorry, wait a minute. Wait a minute, let me check. It's okay for this for the PowerPoint.
Yeah, I can see your screen.
But there is a
Yeah, your voice is still breaking. Can you speak a bit more?
Yes. Can you hear me?
Yeah, I can hear you, but can you go ahead and oops. I think what we can do is, Jinjin, I think what I can do is I can start your recorded video, and then
yes.
for and for Q&A, you can respond to the questions here.
Okay, please.
Yeah, sounds good.
Sorry for myself.
No problem.
Hello everyone, today I will introduce you. Related works of my paper, class rule defect detection using a utility UOV5. Let me first briefly introduce myself. My name is Ji Zhou. I spent 5 years studying in France and graduated from InspectiON in 2019 with a master's degree. After graduation, I joined the Hangzhou Innovation Institute of Beihang University, where I work as a research and assistant in the field of computer vision. In order to further my academic development, I was admitted to Beihang University as a PhD student in 2021, specializing in industrial vision. In this research, we focus on defect detection in glass wool, a versatile material with extensive applications in various industries. Its unique properties makes it integral in sectors like construction and aerospace, and its role as a catalyst career in chemical reactions. However, effects that occur during production can impact its quality and pose healthy risks, emphasizing the need for accurate detection. Traditional methods reliant on manual inspection suffer from low efficiency and poor accuracy. To address this, we propose an improved UOV5S model for defect detection, validated using a new dataset called GWD. This model enhances detection accuracy and efficiency, outperforming other methods on the GWD dataset and other public datasets. In summary, our contributions include the creation of the first dataset on glass wool defects, investigation of the performance of various models on this dataset, and the proposal of an improved UOV5S model, demonstrating superior performance in glass wool defect detection. Given the similarity between glass wool and textiles in images, let's focus on textile defect detection, which can be divided into single-stage and two-stage networks. Single-stage object detection models directly classify and regress only process. For instance, Zhang improved the UOV2 network for colored textile defect detection. GAO used the UOV3 and combined fabric defect size with the K-means algorithm for target frame size clustering. Preliminary AO fine-tuned the portrayed UOV4 model for localizing textile defects. GAO proposed SE UOV5, which added SE module to the UOV5 network and replaced some activation functions. Two-stage object detection methods process images in 2 stages. GAO improved clustering by incorporating techniques like FPM, DC, and distance IOU loss. ChenAO enhanced clustering by embedding the double kernel and using a 2-stage training method. MoAO enhanced clustering feature extraction capability with a dilated convolutional module. The glass wool defect dataset used in this experiment is called GWD, which contains 962 glass wool images. These images were collected from the production environment of a glass wool factory using a 2D camera. Firstly, the images were annotated by a senior industrial expert using the label image annotation software, and then tested and reviewed by 2 experienced industrial experts. The dataset contains 2 types of defects: gaps caused by excessive attention and runners caused by lack of glue. These 2 types of defects are the most common in the production process of glass wool. Gaps are usually smaller in size, while runners defects vary in size. Figure shows some sample images from the collected images and the annotated dataset. The main features of the GWD dataset weak texture and extensive variation in effect size. To enhance the detection performance of UV5, we utilize two modules, GS-code and CPM. GS-code reduce model parameters while maintaining accuracy, and CPM focus on important areas in the image through an attention mechanism. Inspired by the simple texture features of glass-full images in the GWD dataset, to emphasize the lower level features. CVPR is applied at the beginning of the backbone network to extract features from the initial sampling layers. It enables adaptive adjustment of spatial position and channel importance, by improving attention to target information in the feature map while suppressing irrelevant details. In industrial defect detection, where speed and accuracy are equally crucial, we introduce the slim map using GS code to reduce model complexity while preserving performance. With the integration of GS code and CPM modules, we successfully enhanced the performance of the improved UV5S model in detection of glass-wool defects. Here are some of our experimental results. We conducted ablation experiments on UV5N, UV5S, and UV5M. As shown in Table 1, the addition of GS code and CPM modules can improve the original performance. In addition, we also conducted statistical analysis on the model parameters. It can be seen that adding the two modules together reduces the number of parameters. The test results show that improved the UV5S model can process GWD dataset images at a speed of 97 fps with a GPU. The table 2 shows in details the performance of the model on gap and blueness defects using the GS code and the CPM modules on UV5S. Overall, the improved model performs better on gap and blueness defects after addition of the two models. We also compared our model with some other models, including one-stage methods such as FSD, FSD-Lite, UV7, UVXS, and two-stage methods like Cascade, RCAN, and Fast RCAN. And as shown in Table 3, our improved UV5S model performs better than other models in terms of MAQ15 and recall. Here are some visualization results of our methods on the GWD datasets. To further validate the effectiveness of our method, we also conducted comparisons from two other publicly available datasets. One is the Tianchi minimum surface defect dataset, which includes 10 defect categories and a total of 3,004 defective images. It can be seen that our method performs better than the original UV5S and other models. The second publicly available dataset is the Tianchi textile defect detection dataset, which includes 16 types of defects and a total of 3,101 images. The results show that our method is also effective. To conclude, in this work, we propose a glass-wool defect detection dataset named GWD, which is, to our knowledge, the first glass-wool defect dataset, and achieve precise localization and classification of glass-wool defects by improving the UV5 algorithm. UV5S model is selected as the baseline model for experiments, and the GS code and the CDM modules are applied for ablation study. Comparison results with other algorithms shows that the improved UV5S algorithm achieves the best result on the proposed GWD dataset, verifying the effectiveness of the proposed method. The GWD dataset has similar characteristics to other tactile defect dataset, meaning that research on the GWD dataset can also contribute to breakthrough in research on other similar datasets. And that's all, thank you.
Okay. Do we have questions for Yeju? Any questions from here? Okay, our next presenter is Liang Xu from Tohoku University, and the topic is how do label errors affect thin crack detection by DNNs. This is also a recorded presentation, and we do have Liang Xu on the call and happy to answer any of the questions you have.
Hello, everyone. In the upcoming 12 minutes, we will give a presentation to introduce our paper titled How Do Label Errors Affect Thin Crack Detection by DNNs. Numerous studies have been conducted on detecting errors in images of roads, surface of concrete, and other materials. Accurate annotation of cracks is crucial for supervised learning, but identifying cracks in images, particularly thin cracks, can be challenging, making accurate annotation difficult. However, little is known about how annotation errors of trained data affect the accuracy of detectors trained on them. This study attempts to address this gap by synthesizing annotation errors and analyzing their effects. This is made possible by employing an annotation method that labels cracks as curves with a single pixel width alongside appropriate training and evaluation method. We synthesized various types of annotation errors, including under and over annotation errors caused by crack-like image structures and polyline approximation of crack curves to reduce annotation cost. The experimental results reveal several important findings, such as under annotation is more harmful than over annotation, and the polyline approximation has a modest impact on detection accuracy. Previous studies formulate the problem of crack detection as binary image segmentation. To train the model, a pixel-wise binary map with the same resolution as the input image is provided. Most existing datasets of crack detection provide such pixel-wise annotation. However, real-world applications barely require predicting crack regions in a pixel-level accuracy. Rather than a region, the first priority is being able to predict the existence of cracks as curves, which may have at most a few pixel widths. Thus, the conventional region-based annotation does not match the practical demands. Meanwhile, pixel-wise annotation leads to an increase in cost and errors. Hence, there is some gap between the critical requirement and the standard problem formulation of crack detection. In order to address the gap, we choose to annotate cracks as independent curves. With respect to this decision, analyzing the impact of erroneous annotation becomes critical. Similar to existing studies, we treat crack detection as a segmentation task. Although it may appear to conflict with problem formulation, curve-based annotation can provide excellent segmentation supervision when appropriate training method are employed. For instance, we could use branches crack labels to occupy specific area of the image rather than a single pixel width. Thus, the branches map represents crack as one pixel width curves, representing their center. In contrast, DNN output a two-dimensional map of crack likelihoods, which yields a binary map reflecting predicted crack regions by threshold. This conflict leads to the inappropriateness of standard pixel-wise IOU matrix, which is used in previous studies to evaluate predicted crack regions. To tackle this conflict, we use morphological operation when identifying true positives and false positives in evaluation. In detail, we delete the ground truth crack labels using a small disk. Predicted crack pixels inside the deleted region are counted as true positives, while pixels outside are counted as false positives. To investigate how inaccurate annotation impacts on detection accuracy, we classify possible annotation errors into three types: feature independent, feature dependent, and polyline annotation errors. we experimentally synthesize these types of errors and train DNA models on the training data with the synthetic errors, and then test the trained models on error-free test data. In detail, feature-independent annotation errors emerge purely randomly. To simulate this type of errors, we eliminate some part of labeled cracks or add crack labels in a purely random fashion. Feature-dependent annotation error usually results from some image structures. They will occur either when annotators fail to identify a crack, or they erroneously label a non-crack image structures as crack. Such errors will represent most real-world errors more accurately. Polya annotation error occurs when annotator do not provide a precise trace of a crack in images. For instance, they annotate cracks only roughly. We simulate such errors by approximate the track of a crack with a polyline. Independent from the above categorization of errors, there is another property of annotation errors. One is over-annotation if non-crack pixels are labeled as crack, and the other is under-annotation if crack pixels are labeled as non-crack. Errors of the first two types include feature-independent and dependent, each contain over and under annotation. In practical usage, instances of over and under annotation often occur. For example, a misplaced annotation can be seen as an over annotation at the indicated position of a crack, coupled with an under annotation at the actual position of the crack. In this part, we are going to introduce the method of synthesizing errors. We specifically focus on errors that arise from crack with width too narrow to be discernible to the human eye. To synthesize feature-dependent errors, we intentionally blur the images using a combination of downsampling and upsampling with identical factors. We choose this method as it offers a simple yet effective simulation of image acquisition from a greater distance than that of the original input image. A polyline is defined as a collection of straight lines that connect a series ordered points. Using polyline to annotate cracks can reduce the cost of annotation compared to the precisely tracing their centers. Assuming that accurate labels are provided, we generate polyline annotations by approximating the original labels with polylines. To achieve this, we use Douglas' Perker algorithm, which has a threshold that allows us to adjust the level of approximation. This threshold controls the degree of roughness of the polyline annotation. Examples of the approximate polylines are shown in figure in the right side. The compression rate are the ratio of polyline points to the number of pixels in the original crack labels. In this section, we describe our experiment in detail. Some simple but noteworthy experimental configurations are introduced firstly. We split original images into 512 square pixel patches, getting positive patches containing at least a single pixel annotated as crack, and negative patches without crack pixel annotation. Then we have 3,341 and 479 positive patches for training and testing respectively. For each type of annotation errors, we synthesize errors with different error rates arise from 10% to 50% in a patch-wise fashion. To examine if different DNNs are affected differently by annotation errors, we tested 4 classical models, including UNet, DeepCrack, DeepFormer, and HRNet. In order to spatially smooth the labels, we apply Gaussian blur whose coefficient sigma equal to 3 pixels to the map. We adopted the mean square error loss as a loss function. All experiments are implemented using PyTorch. More training and testing details can be found in the paper. We first evaluate how feature-dependent annotation errors affect the detection accuracy. After training the UNet model on the training data with synthetic errors, we evaluate its performance on error-free images for the test set. From figure 4, we find the detection performance deteriorates with the increasing levels of errors, but the impact is modest and tolerable with the low error levels. Additionally, comparing under and over annotation errors, the impact is smaller for over annotation. Specifically, the impact of 30% error for over annotation is mostly the same as that of 20% error of under annotation. We also report the F1 score of compared models in Table 1. We observed HRNet achieve relative better performance than other models. Furthermore, better models seem more robust to annotation errors. Finally, the error mentioned tendency that over annotation has smaller impact on detection accuracy than under annotation covered for these models as well. Similar to the above, we then examine how feature-dependent annotation errors affect the detection accuracy. It is observed that under-annotation has a greater negative impact than over-annotation. Also, the difference in the impact of under and over-annotation is more pronounced than the case of the feature-independent. Table 2 shows the result of 4 compared models. Our observation is when compared with error-free cases, 40% under-annotation errors lead to a considerable reduction in F1 score for all compared models. In addition, 40% of annotation errors may only result in a minor decrease within 10%. We also discussed the situation of mixed errors. Table 3 and 4 present the result of feature-dependent and feature-independent errors respectively at total error levels of 30% and 40%. We found in the case of feature-dependent errors, the ratio of under and over annotation has no significant impact on detection accuracy, while the total error level is a main factor. In contrast, in the case of the feature-dependent errors, the ratio of under and over annotation has a significant impact. Combining both types of errors leads to better performance than using only one type. Additionally, a combination of under and over annotation errors is likely to improve accuracy, which is good news as it is more common to encounter a mixture of 2 types of errors rather than just one type. Finally, it is crucial for annotators to ensure that under annotation errors occurs less frequently than over annotation errors, which aligns with the aforementioned observation. We then synthesize the polygon annotations using the aforementioned method and subsequently train 4 DNA models using the synthesized training data. Figure 6 shows F1 scores of the UNet model trained on the polygon data with different compression rates and then test on noise-free tested data. It is found that the accuracy of the models decreases proportionally to the compression rate. The ranking remains unchanged regardless of the compression rate. Also, it should be noted that even a compression rate of 25%, all the models shows only a modest decrease in accuracy. In the end, our work can be summarized as we defined and accesses 3 types of errors that affect crack detection accuracy. Hence, we experimentally find that under annotation has a more significant negative impact than over annotation. This implies that when annotating cracks, it is crucial for annotators to ensure that there are fewer under annotation errors than over annotation errors. We also found that the combination of under and over annotation errors tends to improve accuracy. Specifically, for the same amount of error, the accuracy of the result is better when both types of errors are present rather than just one. In addition, we conducted experiments on multiple models and demonstrated higher accuracy are also more robust to annotation errors. We finally found the polygon annotation is an effective way to reduce annotation costs while maintaining model detection accuracy. That's all for our presentation, and thanks for your kind attention.
Yeah, so questions for Liang Xu. He is on the call. Any questions? Yeah, if you can come on the mic.
Hi. First of all, thanks for the interesting presentation. I just was wondering if you could say a bit more about the annotation error rates that you actually encounter when humans do the annotation, because you said that you synthesize between error rates between 10 and 40%, and I was wondering how these numbers relate to what actual human annotators would provide and how much they would agree with each other. Is there any insights on this that you can share with us?
Liang. Do you see Liang on the call or? He's not. Yeah, he was on the call before, but I think something happened.
Okay, thank you.
Yeah, take it up. Thank you for your question. And sorry about that. So next presenter is Juraj Fuller from Fraunhofer, and the topic is synthetic data for defect segmentation on complex metal surfaces. So hi everyone, my name is Juraj, and today I will present to you a new synthetic data set for inspection. So as we know, the manufacturing industry tries to keep the defects as low as possible, and this creates a problem with our inspection quality design because we don't have enough data. In addition, when we work with complex geometry, which is quite often and is used in a lot of applications, we have to construct very complex inspection setups. And additionally, another problem is that often these products have different surface finishes, which are highly textured and can create problems in detecting defects. So the existing research in this topic mostly focuses on planar geometry with very large data sets. On the other hand, we have some curved geometry, such as railroads or steel pipes, such as we saw in the Tianqi dataset. And we have complex geometry, but usually the surface is kept, the surface texture is kept simple, and the defects are much easier to differentiate from the surface. There is also an approach to generate some data using GANs. However, the problem is we need a lot of data with a lot of variety for this, which is sometimes not available. And it's difficult to guarantee image quality and to extend support to new defect types and new product surfaces without the data. So our contributions in this work is a new data set for defect recognition that involves a more complex geometry and texture applied to it. In addition, we also present a corresponding dual data set, which is a synthetic equivalent, which is building upon recent developments in the body of work of Laura Bosner. We perform a comparative study by using our custom synthetic data, which was produced by using a computer graphics pipeline to similar data sets in the field. And we present some methods to improve performance in this domain. So the real clutch data sets consists of 6 objects, 3 of which were manually defected because defected data is usually not available, and because it's proprietary, and it also has different surface textures applied to it, 4 of them. The acquisition was performed in a dark environment, so we have a controlled environment. So we focus only on the object, and we end up with just over 500 images, which were manually annotated using focusing only on significant defects, because there are also insignificant defects which can be safely skipped. So we work with really large images, and we have to rely on random cropping. However, we observe that most of the random crops end up in the background regions of the acquisition, which is not the regions of interest. So we try to increase efficiency of our training by biasing the random cropping towards threshold at higher intensity regions of the image. This way, we guarantee that each crop will contain significant parts of the object which are visible, and it will also contain certain amount of background so that we don't have overfitting. We show that by using this intensity bias, we can increase performance across 3 architectures in our models, and more importantly, also the stability of training, because the sensitivity to hyperparameters was lowered. So we perform a comparative study with existing data sets which are similar to ours. We introduce several similarity points, which I will go through quickly now. So we start with the DAGM dataset, which is a synthetic dataset which focuses on generic textures, and it actually doesn't satisfy any of our similarities to our domain, but it's still interesting because it is a generic dataset, so we can see how the performance is here. We also have the collector surface dataset. So here we have similar defects shapes. However, the surface material is diffuse with certain coating, which is quite different from our application. We also have the Seversal steel, which is the largest large-scale data set. However, it focuses on planar geometry, but it still has the surface material and the reflective properties of our materials. We also have the magnetic tile defects dataset, which has slight curvature added to the objects. However, it is still not considered complex geometry because, but it contains some shadowing effects that are similar to our dataset. And also we have the CSEM MIST dataset, which has 3 objects, which have different types of geometry and different types of textures. And more importantly, it also has defect visibility changes. because the camera was actually fixed and the illumination points were dynamically triggered across the object. Finally, the only way we can get similar geometry to our product and similar acquisition setup is to create a synthetic data set, which we did. So the synthetic data set consists of 40 objects, which are procedurally defected and textured, starting from the original CAD model. The defect, material, and texture parameters were sampled from specified ranges so that we get plausible results in all images. And we end up with just over 3,000 images rendered together with segmentation annotations automatically. And we build up on recent work by Lovro Bosnar here. So in all of our experiments in the comparison study, we will train on the train and validation set of the source data set, and we will test our models on the test set of the real clutch data set, where we split our train and test sets into two groups, so that we have more samples in the test set because we want to ensure generalization. So we start with the baseline, and we report in this presentation the F1 score across 3 different popular architectures for defect segmentation. And compared to the baseline, the relevant data sets are actually quite underperforming. So we decided to also introduce fine-tuning to help with the domain gap alleviation. And here we see that even with the best data sets, we get at best comparable results with the baseline. It is only when we introduce the custom synthetic data set that we get much better performance compared to the baseline. In general, we notice a rough trend that the closer we get to our domain, the closer we bridge the gap of the domain, we get better results in our models. However, there is still a domain gap present, and we will try to handle it. So one of the ways that the images that the annotators could see differ from our models is that annotators could artificially change the exposure values of their images. As you can see on the image on the right, the lower defect suddenly becomes visible. Our models don't have that capability, so we artificially increase the exposure as well and stack it as RGB channels to provide it as inputs for models, hoping that the model would benefit from such technique. However, we got similar results to our synthetic data set, which means that this was actually not the main source of the domain gap. So just to quickly conclude what we presented so far, so we have a new dual data set for the inspection planning community. We also provided the comparison of using custom synthetic data sets to similar data sets in the field. However, we still rely on small amounts of real data to bridge the domain gap. We showed that intensity biased cropping actually benefits the training process, both in stability and performance. And we showed that stacking multiple exposures did not help with increase in model performance. So what are the problems here? Well, one other problem in synthetic data is that the rendered masks are too perfect. So they actually render the defects based on geometric visibility, not the actual defect visibility. And the problem of defect visibility is actually a complex problem, and it is a bit ambiguous. So this is something that should be left as a further research in the field. Another problem is that a lot of these models are actually created to create a decision based on a single image. This is not what a human annotator would do, because if we see a certain glint on a surface, we are not sure if this glint is actually a significant defect or just a small deviation that can be safely ignored. So we would just have to adjust our viewpoint so we can have a closer look. This is something that is missing in the field and is something we are also researching. And finally, we are exploring the further possibilities in different product types and different acquisition setups to see what are the limitations of such approaches and how we can increase the performance of our models in industry. Thank you for listening, and I hope for some questions. Questions for Raj?
How exactly did you make your synthetic data? Was it with like Unity game engine or some like rendering from CAD or something else?
So I'm actually not the expert on this. So we have the expert here. Lovro is with us. So if you want to have a detailed discussion, he will be available. But I can tell you that we relied on realistic rendering pipelines. So more specifically, path tracing because it gives us the most realistic results. And the problem of reflection is quite problematic, even for real-time ray tracing. So this is what we rely on. The procedural methods just mean that the textures themselves are not represented as images. They're represented as functions in a field. But however, Lovro is here, maybe he can go more into details about that.
We can take one more question if anyone else has a question. Can you come to the sorry.
How many real data do you use for fine-tuning?
Yes, so we only, for fine tuning, yes, sorry. So for fine tuning, we only use the train set of the real clutch data set. So it only has two objects, one of which is correct, one of which is defected. And because we also need the validation set. So what we basically did is we randomly sampled the viewpoints of these models because there was no other way to construct it. It's a data shortage issue, yes.
So since we have very limited physical parts, did you do some kind of k-fold evaluation over the real parts to address like the variation that you have and the noise that you incur? Or
yeah, so we didn't use k-fold in this research. The problem is that we only have three samples which have one texture variation, three samples with another texture variation, which was actually an update in the production process. So it was difficult to construct a meaningful k-fold from this, but the data set is available, and yeah, we can update the results if it's more interest. Mm-hmm.
There is an online question. Basically want to confirm if adding more channel information actually decrease the model performance.
No, so yeah, it doesn't consistently decrease or increase. That is the issue. So we basically get similar performance. The difference is basically due to stochastic nature of the training itself, even though we did our best to try and initialize the models the same, but yeah, the convolutions are stochastic. So that's the issue.
Okay, thanks, Yura.
Thank you very
Thanks
much.
again.
Okay, so our next presenter is Ying Wei from Chinese Academy of Sciences, and it's a virtual presentation. And the topic is diversified and multi-class controllable industrial defect synthesis for data augmentation and transfer.
Hello everyone, I'm Wei Jing. Next, I will introduce this work, diversified and multi-class controllable industrial defect synthesis for data augmentation and transfer for you. This presentation includes the following 5 aspects. Firstly, data issues such as the small number of defect samples, the broad diversity of datasets, and the huge time cost of creating datasets limit the application of inspection methods. Image data augmentation is a key way to solve these issues and improve the performance of deep learning methods. It involves methods based on traditional image manipulations and deep learning. The former can't edit the defects. According to generated results, defect synthesis methods based on deep learning mainly include those with image level annotations, which cannot improve the performance of segmentation models. And those with pixel level annotations have higher application value in industrial defect locations. However, there are some challenges in current defect synthesis methods. Firstly, these methods may be disturbed by the non-defect information. In the generation of the whole defect image, the non-defect information is probably generated as defects. Secondly, these methods cannot totally preserve real normal backgrounds and provide pixel level annotations for defects with complex textures. Besides, most of the existing methods heavily rely on circlegram to avoid paired training inputs. They can only get one defective image from a normal image by a well-trained model. Aiming at these challenges, our methods generate defect contents with pure backgrounds by DCDGA, proposing improved Poisson blending to totally return real normal contents and generate diversified defects by style modulating. The flowchart of our work is shown in this picture. Firstly, only the defect contents are used to train DCDGA. Raw binary masks can be easily obtained. Then the improved Poisson blending fuses the defects to the normal backgrounds. Finally, the synthetic datasets are utilized to train the segmentation models. Our defect transfer extends the generated wood defects to the tail background to create a synthetic training set and reach zero-shot inspection. DCDGA is shown in the figure. The generator generates a defect content image of the category specified by the input class constant map. Sampled Z and one-hot class C are connected and modulated into the generator by ODSPADE to get diversified defects. The encoder encodes image into latent space. An image and C are inputted into the discriminator to distinguish whether the input image is real or not under the given class C. Next are the training details. Firstly, in order to control multiple defect categories of the same product, for each class, we repeatedly pass the class label to obtain a corresponding class constant map as the source input of the generator. ODSPADE modulates the connection of one-hot class code and random noise into the normalized middle feature maps. Different noises correspond to different styles. Besides, we constrain encoded outputs of the encoder to follow Gaussian distribution to further enhance diversity. The losses are shown in the figure, and the pseudocode of the training process of the algorithm is shown on the right. Defect contents generated by DCDGA need to be blended into normal backgrounds to acquire whole defect samples. To avoid foreground content loss in Poisson blending, we get the binary mask M by watershed segmentation, then process it by distance transformation. Next, alpha compositing is adopted to get the background input alpha n. Then Poisson blending formula is used to calculate the whole defect image IPV. The fusion comparison results are shown in the figure. We perform experiments on defect images of 6 classes in the carpet and 5 classes in the wood from MVTech 80 separately. In this figure, all defects in the same item derive from the same 1Z, and the continuous change of class labels causes the category of the generated result gradually transits from the original to the target. It indicates that DCDGA models the class space continuously by our constructed class constant maps. This figure shows the comparison between all real defect contents and the potentially generated contents of carpet color and wood color. DCDGA generates a large number of defects with different shapes and contents from datasets with only 19 images. Yellow boxes indicate mixed defects which didn't appear in training sets. DCDGA achieves a rich expansion for few sample datasets. Here are some compositing results. It can be seen that the defects generated by DCDGA and the real normal backgrounds are well preserved, and the refined binary masks accurately indicate the defect locations. To test the practical application effectiveness of this work in real industrial scenes, the above experiments are conducted on the metal foam band. It can be seen that our method has also achieved a good synthesizer effect for weak metal defects. Synthetic samples of our method and augmented samples of traditional methods are added to the real dataset raw to get enlarged and augmented training sets, respectively. They are used to train segmentation models based on the backbones of UNITE and RESNITE, respectively. The AUC and epsilon coefficient calculated from the same test sets are shown in the table, where Enlarge has achieved the best test performance. That is because defect contents generated by DCD-GAN provide more different textures and shapes of defects into the inspection models. Segmentation results of the format are shown in this table. This shows that our work has practical application value in intelligent manufacturing. Since our defect synthesis is carried out in 2 stages, defects can be fused to different backgrounds to construct the transferred defect samples. As shown in these figures, the hole and the scratch defects in wood are fused to the normal background of enemy tag tail as the transferred defect samples of the crack and the rife in tail, respectively. Then only the transferred defect images are used to train segmentation models, and all the real tail defects are used as a test set. As shown in this table, models trained only by transferred samples achieve excellent test performance in real tail defects. This figure shows some segmented results which are similar to the ground truth. We achieve wonderful zero-shot inspection performance by transferring generated defects of other datasets into new target backgrounds. In summary, different from other image synthesis tasks, industrial defect generation must serve the detection performance. That is, controllability, diversity, and usability are the key considerations in the generation process. Synthesized methods can obtain infinite defect samples, so we need to efficiently explore the optimal synthetic samples for the detection network. Besides, introducing knowledge of other existing similar defects by defect transferring is an important breakthrough in solving industrial data issues. In our opinion, defect synthesis will have a place in future industrial foundation model training. If you are interested in our work, please feel free to communicate with us. That's all. Thank you.
We do not have the author on the call, so let's move on to the next presenter. The next presenter is Wei Ji, and the topic is segment anything is not always perfect. An investigation of SAM on different real-world applications. This is the paper that also won the Best Paper Award in this workshop. Number 7.
Hello, everyone. I'm honored to be here, and since Wei is not in Canada at this time, so I will help Wei to present his work in the first region workshop. Yeah, I'm Shihao. I'm the colleague with Wei and Jingjing, and we are also in the same lab led by Professor Li Chen. Yeah, so today we will talk about Wei's work, segment anything is not always perfect, an investigation of SAM on different real-world applications. Okay, earlier this year, like Meta AI proposed or introduced the segment anything model, which is actually a foundation model for the vision segmentation tasks. Actually, this kind of model is trained on a large scale data set, and it can generalize to, it can achieve zero-shot generalization to many like downstream segmentation tasks. Yeah, so based on this like segmentation anything model, it can work in 3 modes, which we showed in this video. So the first mode is click mode, where users can click an image with 1 or more clicks, and then this model can segment the corresponding objects correspondingly. Yeah. And the second mode is the box mode, where the users can draw a rough bounding box on the image And this model can automatically segment the objects within this bounding box as the results. And the third one is the everything mode, where the model can segment all the objects in this image automatically. Yeah, so this is 3 modes works in the segment anything model. Okay, so basically speaking, SAM model performs well in common natural image things, as is shown in the paper. Yeah, so in this work, we want to ask this question, like how does SAM model perform in various real-world applications, for example, the industry or the healthcare applications. Here we give some, this figure gives like 6 examples that we will show later. So, so the left side is the ground truth of the segmentation in the industrial and also the healthcare applications. And the right one is the results given by the segment anything model. We can see that, yeah, we can see that actually like SM model actually does not give acceptable performance on this like industrial and also like the healthcare applications, and we'll discuss this later. So, so in this work, we will have 3 points. The first point that we conduct a series of intriguing investigations into the performance of SM model across various applications, particularly in the field of industrial defect segmentation, and some like 3 closely related segmentation tasks in the natural images, and also the healthcare like applications. The concealed and fine-grained and non-salient characteristics of these tasks offer the valuable insights for the development and refinement of industrial segmentation. So the same point that we further analyzed and discussed the advantages and the limitations of SM model in these applications. So the final point that we will, based on these studies, we made some observations and insights towards the prompting the development of segmentation models in the industrial inspection. So for the applications on the industrial scenarios, the first example is the anomaly detection. We can see that here we show 3 examples: SM1, SM2, SM3. So these 3, 1, 2, 3 means using the click, box, and everything modes respectively to do the segmentation for the images from the industrial. So we can see that SM1 and SM2 works perfectly because it has the prior knowledge given by the humans with the click or the bounding box area. But for the SM3, which is works in the everything mode, we can see that it gives reasonable results, but this is not correct for the anomaly detection. Yeah. And the other example, we can see the similar pattern, which is surface defect detection. We can see that SM1 and SM2 works like reasonably, but actually it's not perfect. Yeah, but for the SM3, which is working in the everything mode, it actually does not provide any meaningful results because actually, visually speaking, like we can see that this texture overall does not have like very obvious like textures provided for the segmentation. Yeah, so in this case, we can see, so from these 2 examples, we have this observation that SAM performs imperfect in the industrial scenarios. So in particular, when examining the surface defect detection task, it becomes evident that for practical deployments, a significant amount of expert prior knowledge is indispensable. Yeah. So this is the applications on the industrial scenarios. And next, we will talk about the applications of SM model on the natural image things. So the first example is the dichotomous image segmentation. So dichotomous image means that the objects within this image has very fine details. For example, like showing the shape or the car here. Yeah, so we can see that both all the three modes, like SAM2, 1, 2, and 3, does not provide effective, does not capture effectively the fine details of the objects in the image. Yeah, so this is the dichotomous image segmentation examples. Another example is the camouflage object segmentation. Yeah, so camouflage object means that the object in the image can seamlessly embed it in the surroundings. So we can see these two examples. Yeah, and in this example, we can see that SAM1, 2, and 3 all fails in this case because it is hard to discriminate like what objects in this case within these surroundings. Even if that for the SAM1, where we have an extensive number of clicks, it still provides many like false positives because of the ambiguity given by the images. Okay, the last example in this applications is the shadow detection. We can see that SAM1, we provide many clicks on this image to let him segment the shadow of this building. Yeah, we can see that the results is still like not good. Yeah. So for these three examples, we can have this kind of like a conclusion that SAM has powerful ability at finding the location of foreground objects, which is particularly impressive for like everyday applications, such as the object detection or the online meeting background subtraction. However, in the situations involving noisy backgrounds or the similar foreground and background, or scenes require more detailed segmentation, SM model leaves a significant opportunity for further exploration and improvements. This is the second part of the applications of SM model on the natural image things. So the last applications is on the healthcare images. So we give an example in this case, which is the optic disc and cup segmentation. We can see that the SM1 gives like impressive results given the clicks given by the human priors. Yeah, but for the SM2 and 3, actually they does not like provide like reasonable or acceptable results for this case. Similar patterns can also seen in the like polyp segmentation where the lesion areas, yeah, SM2 and 3 cannot identify the correct lesion areas. And also for the skin lesion segmentation, yeah, it can be observed for the similar pattern. So in this case, like SM delivers the apparent result when substantial human prior knowledge is given. So on the other hand, like in the box and automatic modes, SM's performance fell short. This emphasized that ongoing demand for the dedicated SM explicitly tailored for the tackling medical scenarios. Yeah, we also show some numerical results. We can see that SM model in all these 4 data sets, they are still like a large gap between the SM model with the top performing models or methods in these 4 data sets. So in summary, like SM model has excellent generalization ability on common things, but it requires a strong prior knowledge and a less effective. It is less effective in low contrast applications. And on the other hand, it requires. It appears to have limited understanding of professional data. And for the smaller and fine-grained objects, SM may fail in this kind of applications. So finally, we will discuss 4 like potential directions for the future research. So the first one is the industrial focused SM model. So in this part, maybe we need a dedicated large scale data sets which can follow what the SM model do to train a foundation model for like for the applications or prompt learning in this part. Yeah, and the second one is a pre-training strategy tailored for the industrial segmentation. This is what we mentioned in the first point, that we have if we have dedicated large data set, we can train or pre-train such a kind of foundation model for tailored applications. Yeah, the third one is the multimodal SAM, multimodal SAM, which means that we can introduce, like, for example, the depth or the thermal modalities for the complementary information besides the RGB images. Yeah, the fourth one is the semi-supervised application, because like we can use the segment anything model to generate pseudo labels with suitable human clicks, or the bounding box, or the weak scribbles. So within using this kind of data, we can we can fine tune the segment anything model to using the like semi-supervised way, and then we can possible to achieve the industrial focused SAM model. Yeah, and thanks for listening. Yeah, this is the waste email, and also the code is provided here. If you're interested, feel free to contact with Wei. And also, if you guys have questions, I'm happy to answer if I can. Yeah, thank you.
Okay. So yeah, thanks for your presentation, but unfortunately, I don't understand the significance of the work. So the conclusion I got from your presentation is nothing is perfect, right? So you don't have one size fit all solution from one algorithm. Let's say for different applications, you need to further tailored, customize your solution for that. That's all the conclusion I can get from your work. Any comments?
Yes, basically you are right. Actually, like in this case, like we want to provide some insights on segment anything model to industrial based applications, or how can we like improve like those kind of general model to some like focused applications. So this is actually our like efforts here. Yeah.
Yeah, but I think it still not give me an in-depth insight about the problems, because for any specific problem at healthcare for industry inspection, they have different challenges from the specific problem. So all you show us is this does not work well and no quantitative validation or evidence to support your claim, right? So that does not convince me, even though you have you show another table, say, okay, in comparison with some other top model, this is not that good. But if I pick up another model you show in table, I can have the similar study and give the same conclusion out of it.
Yes, basically you are right. Like because actually I'm not expert in this area. Yeah. Maybe I can like let Wei to reply to your questions, and maybe I can communicate with you later and from Wei. Yeah.
Okay, thank you. I just have a question about the research methodologies here. Okay, thank you.
Any other questions from the chat? Or... Yeah.
Hi. So it's kind of like more common to the previous question. So yeah, I understand and I totally agree with you. But the thing is, for example, I'm working with industrial objects with quality detection, and you just hear this SAM, amazing, and there's like tons of presentation. You can see LinkedIn in the video. It's like yes, SAM, but nobody actually talks about where it doesn't work. So yes, I agree with you. It's not. Yeah, and it's not tailored for it, but it's maybe nice that there is a work that actually shows, yeah, probably don't use it here. Probably you need to do something more. So maybe like for businesses like us, so if not somebody comes in like, yeah, let's integrate SAM before we actually analyze it. So I think it's nice to see that work, even so I agree with you, but yeah, I think it's nice to see also your work that you actually show the downside of this popular, because it is popular and you see it and it's like this big, great thing. So yeah. That's my comment.
Yeah, thank you.
Yeah, I agree, but I would say, given a specific example, you cannot claim SAM doesn't work here, because you need to modify that, right? You need to, based on your specific application need or challenge, you need to customize, tailor that. You cannot just get the off-the-shelf product and work on that. That works. No, nothing work like this way. That's luckily, but that's not research anymore, right? So let's say if you give me the funding, I can make the sample work for one of these applications. Okay, thank you.
Thank you. Thank you very much. Yeah. I think we'll have a good discussion during the lunch break.
Yeah,
maybe.
I want to make one comment. I think
Yeah.
I really enjoyed this great discussion. We carefully think about the wording of this award, and we give it as a most inspective award. And I think there's so many exciting things going on for machine learning and AI industries. And we also need to be carefully think about what is gap and identify the gap first, and then we can move forward collaboratively from industry and academia. Yeah, thank you.
All right, so moving on, our next presenter is Bohao Peng from the Chinese University of Hong Kong. And the topic is hierarchical dense correlation distillation for few shot segmentation. So this is virtually recorded as well.
Hello everyone, my name is Bohao Peng. It is a great honor for us to have this chance to introduce our work. First, let's give a brief overview of our work. In this project, we have made three main contributions. Firstly, we propose a novel decoupled downsampling and matching paradigm to alleviate the problem of information interference. Secondly, we improve the existing matching module based on correlation matching and distillation. Finally, we employ hierarchical correlation map distillation to enhance the overall performance of the model. We achieve a 50 points in IOU on the Coco 20i dataset in a one-shot setting with unseen categories. Extensive ablation experiments and visualization results demonstrate the effectiveness of our approach. Now, let's dive into the details of work, step by step. Before moving into the details of our model, let's briefly discuss related works in the field of the feature segmentation. Feature segmentation is an approach aimed at reducing the dependence of models on large-scale training data. The goal is to improve the effectiveness of model learning, enabling the training of segmentation models with judgment.
It's like a lion roaring. I hope he's doing fine. Let me just restart.
Hello, everyone.
I think the entire.
Really was curious.
Yeah, there is some challenge with the audio here. I think we will skip this presentation then. I don't know if Bohao is on the call. Shanchung, do you know if he's on the call? Okay, I think we will move to our next or our last presentation. Yeah.
So I think this paper is also accepted by the CVPR main conference. So if you are interested in, just attend the poster sessions. Yeah.
So our last presentation, research presentation for today is from Neve Cohen from the Hebrew University of Jerusalem. And the topic is set features for fine-grained anomaly detection. Okay, here you go.
So thank you. I'm not actually Niv, I'm Edith Rocha. Niv is my PhD student who unfortunately could not present this work, so I'm presenting it for him. And another collaborator is Isatho. Okay, so anomaly detection is really the task of discovering rare but interesting phenomena. And both of these objectives are important. We cannot have one, but not the other. Now, in the past, we introduced or proposed a simple but reasonably powerful anomaly detection paradigm called deep nearest neighbors. This work is by Bergman and Cohen. And the idea was to detect anomalies by basically using some foundation model, which was pre-trained on something else like the ImageNet dataset or something even more powerful, to extract representations for the entire dataset, both training and test. Now, for each test image, we compare its distances in representation space to each training image. Then we pick the K images which have the shortest distance to this image. K is usually 1 or 2. And these distances represent the anomaly score. Test images that have large KNN distances are taken to be anomalous because there's nothing that's similar to them. So they're different from everything else. Now, often we cannot really use this idea as is. And the problem is that the anomalies are quite fine-grained. So if you represent the whole image using one representation, you'll actually miss the anomalies. And so this leads us to segmentation, to anomaly detection by segmentation, which means that we break the image into smaller elements like patches or some image regions. We extract some representation for each element. And then we do the same thing as we described before, right? We do this kind of deep K-nearest neighbors approach. And we try to detect elements that are anomalous. And if an image has one or more elements that are anomalous, we deem the entire image to be anomalous. So we had an approach called SPADE that did that. And this was significantly improved by PatchCore, which is very popular right now. So this is only one type of setting for anomaly detection. A more recent setting introduced by the ENVITEC team, by Bergman et al., is logical anomaly detection. So the type of anomalies we described before are now called structural anomalies. And the reason is that if we look at one specific element, we can understand whether it's normal or anomalous. Like, for example, this nut. If we see a scratch, then the scratch is anomalous. We don't need to look at the rest of the image because the scratch by itself already tells us that there's an anomaly. Now, on the other hand, logical anomaly detection is different. In logical anomaly detection, each one of the elements is actually normal by itself. And the anomaly comes by the novel configuration of elements. So let's show an example. It's easier to understand by example. So for this data set, so the data set ENVITEC introduced is called ENVITEC Local. It's a great data set. If you're interested, please check this out. I'll just describe one of the classes in this data set. And in this data set, in every image, we have one long screw, one short screw, 2 nuts and 2 bolts. 2 nuts and 2 washers. Don't worry too much what each one of them is. One of them is the round one, the other one is the squiggly one. Now, an example of a logical anomaly is, for example, is shown on the right-hand side, right? So we have one long screw, one short screw, but then we have, I hope I'm getting the terminology right, but I think three nuts and 1 washer, right? So each one of the elements by itself is actually completely normal, right? We expect long screws, we expect short screws, we expect nuts, and we expect washers. And the only thing that is anomalous is the configuration across the image. So by looking at any given element, we do not know whether it's normal or anomalous. We have to look at the entire image, the distribution of elements in the image to understand whether it's normal or anomalous. So we believe a good way of tackling this task is by set anomaly detection. Basically, we represent each sample as a set of local elements. And then we represent this item by the distribution of elements, and we completely ignore the order. We just look at the distribution of elements. And we detect anomalies using density estimation of these set descriptors that I will describe. Now, just to be more concrete, for example, each patch could be an element. Okay, so what's a naive solution? I see that there's some formatting issues, but don't worry. So one preliminary idea would be that we extract a deep representation for each element, and then we summarize the whole set using the average. This isn't such a silly approach as it sounds, because that's also what they do in PointNet, and this is a state-of-the-art approach, or at least was state-of-the-art approach for many years. The problem, so it's good if averages of the element representations are different between normal and anomalous images. But for fine-grained anomaly detection, it's pretty unlikely that the differences between the averages would be very significant because we only have few anomalous elements. So this really wouldn't be discriminative enough. And you can see an example here, right? Where we have two distributions, but the averages are not different. So the first moment isn't always sufficient to differentiate between two distributions. So specifically, we use another approach, which is inspired by the slice-Wasserstein distance between distributions. And the idea is like this. So we take all the features of the elements and we project them along some random direction, which we sample this direction is basically just a vector with the same number of elements as the number of features. And we sample the elements from a random Gaussian distribution. Then projection is basically just taking the dot product. So it's just a fancy name, just dot product. Okay, so this gives us a scalar for every element. Now we summarize the distribution of projected features for each image using a histogram, right? And histograms are orderless. They don't care about the order, they just care about the distribution. And they're one-dimensional, as we can see here, right? We can see a histogram for this projection, histogram for this projection, for each one of these distributions. Okay, now because these projection angles, these projection directions are quite arbitrary, we randomly sample many projection directions, and for each one of them, we compute a histogram. Then we represent the entire image, the image using the concatenation of all these histograms of these various directions. And that's what we do for every image. Okay, so now we have these concatenated histogram descriptors for all the images. And now we can do density estimation as we've always done using k-nearest neighbors or some approach like that. I should mention that we have a whitening stage before k-nearest neighbors, which does matter. It does improve results. Okay, so the only thing I left out is how do we actually, what are the elements and how do we create the distributions? So I'm going to show both image anomaly detection and time series anomaly detection. The only thing that changes is what are elements and how do we compute the descriptors. So for elements, we basically just take the image, pass it through some foundation models, some ResNet pre-trained and ImageNet or something even bigger. This lets us create a dense representation, the deep representation for the image. Then for each image region, we basically concatenate the results of the activations of multiple blocks as they do in PatchCore and Spade and various other approaches. So each element is an image region and the representations just come from some deep neural network, which was pre-trained. And this is sufficient for achieving state-of-the-art performance, even though this is a reasonably simple approach. So on the MVTech local dataset, this does outperform existing approaches, but to be fair, I should say that this has complementary strengths to existing approaches. So it's not as if it's better at everything. GCAD, which is the approach proposed by the MVTech team, is actually better at sort of anomalies that are linked to some spatial properties of the image, whereas our approach is a bit more, it's not exactly spatially invariant, but it's nearly spatially invariant. So there are complementary strengths, and I assume that combining the two approaches in some way would achieve even better results. So just to show the generality of the approach, we can show that it's also very useful for time series anomaly detection. Now, I should say that this is different from your usual time series anomaly detection, because here we look at an entire time series, some, for example, gyroscope recordings of an activity, and we want to characterize this whole time series as normal or anomalous. So here things are even simpler. Each time point is an element. We describe each time point using just basically a simple histogram, a simple pyramid of the elements. As illustrated here, it's as simple as it looks, no deep learning involved. And then we do exactly the same thing as we did before with the set features and k nearest neighbors. And this outperformed the previous approaches that tackled this task, which used deep learning and was significantly more complex than this approach. So to summarize, we've argued that set representations are key for logical anomaly detection. They do have complementary strengths with some existing approaches, so there are avenues for improving the results. And we've shown strong results for both image and time series logical anomaly detection, so this approach has some generality as well. So thank you very much.
Questions for Eddie? Yeah, any comment?
I just wonder for this user case, why not just use the object detection? So you can detect for nuts or washers.
Yeah, so that's a great idea. And to be fair, we also tried that. The problem is that these are very general objects, right? One of them is push pins, the other one. So I don't know if using SAM might be effective here because it's a very general object detector, but at least the object detectors that we had available at the time were not able to detect these objects reliably enough. And also in advance, you don't know what object you care about and what not. Like, is the background an object? Is the background not an object? This is an interesting avenue for further research, but I should say that it's not trivial to use object detection for this setting because objects are not actually that well defined. They can come in hierarchies.
Then what if in your case these nuts or washer overlap to each other?
Sure. So in that specific use case, object detection seems fairly natural, but there are other classes in which object detection, I haven't showed them, but in which object detection is not so natural. So it really depends on your use case. I think in some cases, object detection would be a great fit. And we also believe that's a great direction to go, but I should say that it's not applicable everywhere.
Right, for the time series detection, does it really only apply to specific types of time series? Are there some characteristics of the time series that this method works better for?
Probably, but we haven't analyzed it carefully enough. We just took a previous benchmark and we've applied it on that benchmark and we got good results, but I assume that it doesn't apply everywhere. And this approach is actually quite interpretable, right? We understand what's going on. It's just a set descriptor. So you could probably tailor some time series for which this wouldn't necessarily apply, like if it had very strong locality. So I could probably speculate on where this wouldn't work, but we haven't tried it extensively enough. So this is left for future work. But a great question.
Yeah.
Hi. So I've noticed that you're talking about objects that are typically high volume production. So you would find this on a production line that goes rather fast. And typically in such stages, it is not very easy to ensure that all the objects are like nicely spread. How does your approach work with that? So what happens if there's some kind of curtaining, shadowing and situation where you cannot actually distinguish between objects?
So our approach isn't actually object-based. That was the first question, right? And our approach is actually patch-based because we couldn't necessarily always properly define the objects. So this might make it maybe a little bit less susceptible to the kind of problems that you're mentioning. But we just use the MVTech local data set as is. We haven't tried stress testing it further. I don't even know exactly how we could do it. So perhaps if someone were to create maybe a more challenging data set, even though MVTech local isn't that easy, right? But if someone were to create an even more challenging data set, that this could actually stress test these approaches, and I could give you a better answer to your question.
I think first I'll take the question from Peter, and then we'll come to you.
So if I understand it correctly, the invariance to the patch location comes from the fact that you basically apply the same random projections to all of them. Have you tried concatenating the patch locations or the patches with some kind of positional encoding? Because that would reintegrate this locality information if it's indeed helpful.
Yeah, so I have skipped some technical details, which I did not have time to go into in a 10-minute presentation. But we have encoded locality in a few ways, and this has improved results by about 1% absolute, which is nice, but it's not critical. It has a lot to do with this specific data set, right? Because you could definitely design a data set where locality would be critical, and then we would fail. Yeah. So we've actually added the locality by basically taking a few crops and basically just comparing between the precise same crop. So taking the image, breaking it into various crops of fixed locations, and then comparing just these locations. So this is a way of taking exactly the same approach and just applying it on specific localities, and this is a way of encoding. Now, in terms of what you're saying of actually using positional encoding, I think Niv has tried that. It's a shame he's not here to answer that. We've definitely discussed it, but I don't know how serious the experiment was in the end. I think this did not outperform the final approach, but presumably, if we worked harder at it, maybe we could have done even better. I don't know.
Thank you.
But it's a great idea. Thank you.
We'll take one last question.
Yeah, thank you so much for the nice presentation. I love the way you look at the problem, which is the definition of the anomaly is completely contextual. So for this specific application, have you tried, for example, we have the non-defective materials with the exact numbers of each element, but what if the color of these elements change? For example, instead of a silver screw, we have a golden screw. So is the method robust to this change? And also one general question, have you investigated any solutions to just have a somehow general model, but to find a way to define the context of anomalies, to just conditioning the training to that context?
So I think your first question is easier than the second one. The first one is, are we robust to color changes? This really depends on the features, right? And we specifically take features from a pre-trained ResNet. It is somewhat robust to color changes, but you don't want it to be too robust to color changes because the same benchmark also evaluates structural anomalies, and they care a lot about these color changes because that's how it's defined in the data set. So it would not necessarily be beneficial for us in terms of like the benchmarks at the moment to be too invariant to color changes. I don't know whether that is something very deep or just, trying to look good in terms of benchmark. This is obviously very, very dependent on your actual application. And when you're in academia, you don't necessarily have any specific application. So you just try to do well on the benchmarks, and we've done, so that's the answer to that. It's not a very satisfactory answer because at the end of the day, if you're in industry and you actually know your application, then you make sure your features are actually, they actually satisfy the properties that you want. But when you're in academia, basically you just have the benchmarks and you try to do the best. So that's the easier answer. The second answer is, can we define can we define the context? How do we tell the model what's interesting? And that's a great question. So there've been methods trying to do it using natural language processing. There've been methods trying to do it using few shots. There've been in another workshop yesterday, we discussed how we can use priors to do it. There's a lot of different ways of doing it, but it seems like we haven't, as a community, we haven't really converged on how do we specify this is an interesting anomaly. So it's a good question. I think it's something for us to do in the next couple of years.
Thank you so much.
Thanks.
Okay, thank you. Thank you. Okay, so that was our last presentation of the session. So it's time to give ourselves a well-deserved lunch, and let's reconvene here at 2 p.m. sharp. So we will have 2 more keynote speeches after the lunch, and then also panel discussion followed by the data competition presentations. And also we do have like poster session in the exhibit hall west building, which is the same building where we are. Okay, thank you. Thank you, everyone. We'll see you at 2.
Thank you for this very gracious introduction. And before I start on the main topic, just a little bit of prelude. So I want to thank Meng for organizing this and inviting me to be part of this workshop. And when he first talked to me about this, I thought this was great. Like, this was a wonderful idea, and mainly because of a huge potential impact, a real world impact that this may have in terms of bridging together the vision researchers such as myself, the industrial partners, and perhaps even more importantly, formalizing some of the challenges that might exist in this with data sets and benchmarks. However, when I started preparing this talk a few days ago, I had a major imposter syndrome. And that's because I don't actually work on industrial inspection. And so after getting over that, I decided that I should disclose that in the very beginning and just say that I don't generally work on these topics, but I do work on computer vision in general. And I think some of the algorithms that we're developing in the broader sort of set of applications might be quite applicable to inspection. And that's what I'm going to cover today, essentially talk about those applications and hopefully give some ideas for how they can be used in inspection. And if anybody wants to collaborate on these topics, I'm happy to explore that as well. All right, so now back to my title. So I'm going to talk about efficient and less biased learning. So clearly there's sort of, I think we all understand what visual learning is, but the two keywords that I wanted to focus on today is efficiency and bias in data and in our models. So in terms of efficiency, there's at least two types of efficiency that we can talk about. One is the data efficiency, right? How much data does a model need in order to train? And then also the computational efficiency, and this is more about inference, right? How fast can we actually perform inference? So I'll talk a little bit about both of those. So in terms of telling you why these things are important, just a little bit of my own perspective on this. So data efficiency, I think, is important for three different reasons. First one is just pure scientific curiosity, right? So the models that we have to date tend to be very good. They're getting better with GPT-3, 4, soon probably GPT-5. They're getting better and better, but they're also using enormous amounts of data. Clearly much more than an average human has access to during their lifetime. So for example, GPT-3 was trained with 400 billion words. GPT-4 probably was trained with more, I just don't have the data. But if 4 billion words is about how much a human can read in 400 years of continuous reading, right? So multiple lifetimes of human experience in order to get sort of close to potentially human performance on particular things. So getting more efficient agents would be, and learning would be, good for that. Some problems may not have a lot of data to start from, right? Like medical imaging, certain diseases are not common, for example, certain cancers and so on. And if we have to wait until, a million people get imaged with this disease, then obviously, we're waiting for 1 million people to effectively die before we can actually start building models that actually diagnose these diseases. So from that perspective, also having efficient data models is important. Now, the last thing, which I also is quite central to my own research, is the fact that as we scale things up, and as we look at detecting and recognizing more things in the world, and as we're trying to do more granular tasks, like look at individual objects and how those objects interact and so on, more and more individual aspects of problems, then the data is becoming, we both need more expensive data because it's more granular to collect, and we also need more of it. And so that also is sort of a scaling issue as we move from classification to detection and segmentation to maybe something like scene graphs, which I'm going to talk about a little bit today, where you have objects and interactions between those objects. You can imagine that labeling all of this data as you go from left to right becomes more expensive, just in terms of human effort. And in terms of the recognition problems, they're also becoming more difficult. And so we're going to need more data. So we're going to need more expensive data. And so having efficiency is good in that way. All right, now switching gears a little bit and talking about computational efficiency. So computational efficiency, there's a number of reasons why we want that as well. So one is we want to be able to run our models on low compute devices such as smartphones, right? So we don't want everything necessarily to be deployed in the cloud. So we do want efficiency for that. We also want to have models that have low latency, so we can pass through many and detect many things sort of in real time or faster in real time. And the last one, which is largely being overlooked right now, I think, in general, is adaptability of a model, right? So we don't want our models to be in general static. We don't want to train it once and just deploy it. We want to have this model which is deployed, and then we're going to collect some more data, retrain it, have better model, collect more data, retrain it, and so on. And so we want to have this live model, and the sort of livability of this model, how often we can retrain it, is directly proportional to how fast we can do inference and train it, right? So those two in the bottom in particular, I think, are very relevant to inspection applications, because in those scenarios, we do want high throughput, right? We have machines that would producing things. We want those are doing this quickly, and we want these models probably to adapt as they see more examples of particular manufacturing process and so on and so forth. Okay, the last thing I wanted to talk about is bias. So I'm not going to dwell on this too much, but this has been in the news a lot, right? Machine learning models can be biased. And the reason why they're biased is because they're really good at picking up and modeling in some cases, and even amplifying in certain cases human biases that they get from a training data, right? And so just not to go into too much details, there are canonical examples with, for example, gender bias in language, where if you train a language model to complete analogies, and you give to that model an analogy man to a doctor as woman to something, and let it fill in the something, it would return a nurse, right? So there's clearly a bias there. And if you think only language models are capable of this, that's not true. So these are results from DALL-E. So DALL-E, if you give it a prompt, a photo of a doctor, sort of more times than not, it'll generate a male. And if you give it a prompt of a photo of a nurse, more times than not, it'll generate a female. In fact, if you look at the statistics, and this was calculated by this post, which I don't know how much I should trust, but at least that's out there in the world. It's basically calculated that for every female doctor that's being generated, the DALL-E 1 model would generate 2.35 males, which is an exuberation of the actual statistics in terms of who's a doctor. Now, things are not that bad, right? There's a lot of people, really smart people and entire communities that are working on alleviating these biases. And so DALL-E 2 is actually much less biased than the original DALL-E model. So just want to put that out there. All right, so hopefully now I convinced you that these are more important, these are important topics in general, but why are they important for inspection, defect, and anomaly detection? Well, because when you have systems like this, then often these similar types of issues do come into play. For example, a large number of defect-free images may not be available, particularly when you have a new product line that is being manufactured, right? And so if we need to wait for 1 million devices to be manufactured just to get the data, that means that the first 1 million devices have to be expected by humans or in some other way, right? So having ability to basically deploy models with relatively few examples has been started to take place. And these are some of the references that I actually found in terms of inspection with few shot learning that are relatively least recent that I happen to come across. And in terms of the bias, there's also going to be a significant bias in the data, right? So the defect images are relatively rare. So there's going to be very few, if any, defect images, and there's going to be a large amount of sort of regular defect-free images. And so we're going to have to deal with that in that way as well. So essentially, all of those things that I talked about and motivated in sort of these other domains are also relevant here. So hopefully, if you buy that, what I'm going to do now is talk to you about some of the strategies that we use to actually mitigate some of these problems. In some of them, I will go into the detail. Others, I'll just skim over. So the very sort of first or some of the earliest work on kind of data efficient learning was an idea that we can learn a model using a large data set for a source task, and then essentially fine tune that model to a target task that has very little or limited data, right? And in this particular example that I have here, both the source and the target tasks are classification of certain form. But that doesn't need to be the case. For example, the source task might be something like classification. The target task might be a detection or segmentation on a different data set that have different classes and so on. And we actually had a paper on this 2 years ago at this conference at CVPR that exactly looked at that particular scenario. I'm not going to talk about it in detail here because I want to focus on other things. but I do, if this is of interest, I do welcome you to check it out. I think it's a pretty interesting work. One of the nice things I like about it is it's fairly intuitive, and it's a unified framework that basically works across a variety of supervision and levels of supervision that you might have. Okay, so moving on from that, the next kind of thing you can do is, instead of having a single source task, you can have many source tasks. Right? You can have k source tasks. It could be different. And then you are essentially using multitask learning to learn this source model, or in this case, it's mostly going to be a feature extractor, and then fine tune that feature extractor to essentially with small amounts of labeled data. So the right-hand side doesn't change at all here. And we do have some work on this as well, but it's under review. And so I self-censored myself for not talking about it and promoting it earlier than it's going to be available. So stay tuned for that. So now that I've talked to you about everything I'm not going to tell you about, I'm actually going to tell you about something we are doing. And this is about foundational models. So that's another way of doing this, right, is to learn a model using a self-supervised task or a proxy task in order to form this, this foundational model, and then fine-tune that model with limited data. And the benefit from previous approaches that I talked about just now is the fact that you don't actually need a source data of any source, no labeling at all. You're just using sort of self-supervised learning mechanism in order to learn that foundational model. So let me talk about how we did that. And of course, the canonical example of this is ChatGPT, right? Everybody's talking about ChatGPT. So let me talk about how we did this for images and some of our latest work on this. And in order to do that, I need to talk a little bit about self-supervised learning, right? Because that's a mechanism for learning these foundational models. So essentially, there's two categories of models in self-supervised learning. The first one is what is sort of broadly called contrastive or discriminative learning, where you take and essentially introduce transformations to images, and then you learn the feature representations that are invariant to those transformations that you introduced. Right, so there are different variants of this, whether you use negative samples or not, in terms of the training objectives, and there are many different algorithms for this. I'm not going to go into a lot of details. What I do want to focus on is actually the second class of models, which is predictive or generative in nature. And there we essentially have two types of models. One are what is called BERT style, and the other one is GPT style. So in BERT style models, what we have are inputs. So here is, let's say, pixels or patches that go into this model. You mask out some of the pixels or patches, and you essentially try to predict the ones that are missing. And so the task is essentially to predict missing pixels or patches in this case, and that's a proxy task that you use to learn a foundation model. And you can see that this could be done in parallel, right? Like you can predict all of these missing patches at the same time in parallel. Now, the alternative to this is GPT-style pre-training, where essentially what you're doing is sequentially predicting what the next patch or pixel is going to look like. So you start from a single pixel, and then sequentially, iteratively, you predict the next one, condition on the next one, you predict the third, the fourth, the sixth, and so on. So the important distinction here is that on the left, where you have a BERT style, it's not essentially sequence-driven, whereas on the right, it is sequential in nature. Now, in language, both of these strategies have been explored, and actually the GPT style training is preferred, and this is what GPT-3 and GPT-4 is based on. For a lot of tasks, it works better in language. In vision, we've done a lot of BERT style pre-training, but not as much on off the GPT style. And part of that is because if we serialize images, we're just going to get incredibly long sequences, right? And so that's a challenge. So one of the things we wanted to do with this work is kind of both combine these two types of pre-training strategies to get something better, but also explore what can we do with sequential predictions more similar to what GPT does. All right, so we're going to effectively build a visual language model, and Patrick on the right corner is the student who is most responsible for this. So all credit goes to him. So we're going to build a visual language model, and essentially if we are doing this visual language model, a number of questions arise very quickly. One is, how do we partition images into what is equivalent to words, right? That's not obvious. Like words are well delineated in language. In vision, that's not particularly as well recognized. How do we serialize images into sequences, right? Words are naturally sequential in sentences. Images are don't have a natural sequential order. And how do we formalize a prediction for the next likely word? So in order to kind of do this, what we did is took a little bit of motivation for human vision And very sort of high level way human vision works is if we're trying to make predictions or things like this, look at the scene. Essentially what we do is we have a series of foveal fixations, right? We look at the scene at various points and then we shift our attention. And in fact, what happens is that you have sort of these shifts, what are called saccades, and you have sort of small shifts, which is micro, and then large shifts, which is macro. And so you have this hierarchical way of essentially traversing the image. And so what we're going to do is essentially have this type of hierarchical traversal in order to actually build a language model. Okay, so what are we going to do? So we had this algorithm or approach called random segments with autoregressive coding. And what it's doing is essentially it's grouping pixels into patches. So these patches is what are going to be our visual words. Then these patches we can group into hierarchically arranged segments, and you can think of those as phrases or sentences in language. Within each segments, we can do all the predictions in parallel, so similar to BERT. And across segments, we're going to have predictions that are sequential in nature, right? And how do we actually get the order for those predictions? Well, we couldn't figure out a good way, so we just randomize the order, right? So we have the predictions are still sequential, but the order is random. Right, so we basically essentially go over all potential orders of traversal of the image. And what you can see on the right is actually illustration of this. So the different shades are essentially different patches of words. The different sort of color illustrates the segments, and the arrows illustrate sort of the random traversal that we would have, where the black is sort of local traversal order, and then red is more macro moves in terms of the image. So if we actually trying to predict an image, this is an actual result from our model. We start from this set of pixels, and we just keep predicting it until we get the full image. And what we want to do is to predict sort of real images. Right? That's the objective. Okay, the architecture for this is pretty simple. I'm not going to go through the details, but effectively it's a transformer. So we have an encoder that takes a set of patches. Those patches could be individual pixels or bigger sort of patches of an image. And then it encodes that into a representation, and then conditioned on a particular position which we want to decode, it predicts a patch at that position. Right, so the input to the decoder is basically positions of patches, and the output is the actual content of them. And through various masking mechanisms, we can make sure that the predictions are actually sequential. For example, a particular patch, when it's being predicted, is only looking at the patches that's been predicted so far, not at any future patches that will be predicted. So the model doesn't really matter so much here. What I wanted to go through is an actual design choices that we made, and sort of what's important for actually making those predictions rather than sort of architecture, which is fairly standard. So let's look at what we do if we actually apply this model and try to learn representation. So what we can do is the simplest model we can think of, make each word essentially a pixel and make an order sequential, just raster order of images, right? And then we can use that in order to learn a representation. And then once we learn that representation, we can do something linear, like linear probing, take a representation from an encoder, just a single classifier on top of that, and then predict the classes of objects in this particular case. Or we can do fine tuning where we is going to fine tune the entire encoder and get a better, hopefully, results in that case as well. So if we actually do this for this scenario on CFAR10, which is a fairly small data set, these are the results we get in terms of classification. Right, so 41% in terms of linear probing, 59% in terms of fine tuning. That makes sense. With fine tuning, we should do better. Now, what if we don't know, remember that we don't know how big our words have to be, right? We don't know sort of the scale of these words. So what happens if we make them bigger? We make them into patches, right? We're still going to raster serialize it. We're just going to make our words bigger and make the model predict these patches instead of individual pixels. Well, performance goes up. Right, so essentially the scale is important, and in particular, if you go even higher, things start to deteriorate. But doing things at the pixel level is too redundant, so we do need to do this at a patch level. Now, the next design choice is how do we serialize it, right? So before I do raster order, well, we can also do the randomized order that I talked about initially, and if we do that, then the performance goes up by a lot, right? And so this is important. So basically, by introducing an order, even though our order is random, our sequences are not orderless, right? Each sequence has a particular order, it's just that order has been assigned at random. So that was an important observation that we thought was quite good. That also holds across different data sets, larger data sets like ImageNet. We can further now take this model and say, well, what if we actually put these patches together into the segments where within each segment, we're going to have these parallel predictions. And again, the performance does go up quite significantly. So I'm sort of giving you quantitative evidence for why we built a model in a particular way. And then finally, we can have sort of hierarchical way of doing this where we group these segments in a particular order, then we traverse them, we have a sort of hierarchical grouping, and that adds a little bit of performance, but not quite as much as the other design choices. So these are actual reconstructions. So the top is the ground truth, the bottom two rows is our model. So this is what our model is learning to do, is basically learning to generate images, and in doing so, learning an intermediate representation that then we can use for a variety of other tasks. So the difference between the blob and square is not too important. That's basically is the shape of our words. In one case, the square is just a group of pixels, which is a square. In our case, it's sort of more elongated, kind of blobby in shape. More or less, it works the same way in both. Now, the interesting part about this is that if we do this sort of pre-training with essentially quite limited amount of data, we do fairly well. We beat other state-of-the-art self-supervised learning approaches, which is Dino and mask auto-encoding. And interestingly, we actually beat the supervised performance by some margin. And part of that, I think, is attributed to the fact that we are doing this randomized order. And so that, in a sense, is a data augmentation technique that allows us to more effectively use individual samples, as opposed to just when you do classification, where each sample comes with one label. It's basically a unit. Now, we can also do this for large data sets like ImageNet. And again, here we compare to a number of different self-supervised models. And we do roughly 0.5% better, which, whether it's significant or not, I'll let you be a judge, but it is sort of an interesting type of a model. We can also fine tune it to different tasks like detection, object detection here, which again, sort of better than some of the state-of-the-art models that's been around at the time, and on segmentation. So all of these things kind of benefit once you have a better representation. Okay, how are we doing on time? All right, so that was the first part. And now what I want to do is talk a little bit about computational efficiency through iterative refinement. And then ultimately that's going to get us to also talk about bias. Okay, so we're going to switch gears a little bit now and talk about a different problem, which is the one of scene graph prediction. So here, the problem is that we want to predict a scene graph from an image. The scene graph is basically a collection of nodes and edges. The nodes would correspond to objects that are detected in this image. For example, a hat, umbrella, lamppost, and person. So those are going to be our nodes. And the edges are going to correspond to actually relationships or predicates between these different objects. So, person wearing hat. So there's a directed edge along which wearing is done and so on, right? So on the left, you basically see the input, which is an image. And on the right is the desired output, which is a graph that corresponds to individual objects grounded in an image and also the relationships between them. And Sadesh should be credited for this work. All right, so when you essentially make an estimate of a scene graph, so most models, what they do is effectively first they predict a subject, right? So what is the actor in this particular image, for example, a person, and then condition on this actor or a subject, they would predict objects that that person may be interacting with, right? Like a head, and then condition on a subject and an object, they would predict a predicate or relationship that would tell you sort of what the interaction is. And once you have all these objects, subjects, and predicates, you can actually form a graph out of this. Now, the observation that we had is that we can formulate this as an iterative process, right? So given an initial graph that's contracted in this way, we can actually use this as a conditioning for the next step and the next step and so on, basically improving the results. One step at a time, building better and better graph. Formulate this is again using a series of transformers. So we have an encoder similar to DETR, if anybody is familiar. So it's basically just takes an image and encodes it into a high dimensional feature representation. And then we have three different decoders: one for subject, one for object, one for predicate. I'm been given a warning of 5 minutes, so I'm not going to go into the details of these, but basically each one of us predicting its respective sort of element condition on the others, right? So for example, when we're predicting a predicate, there's an intention here that's going to condition on the subject and object, and also will condition on the prediction of the entire graph from a previous kind of iterative step. Now, once we formulate this model, we can learn it based on the data that we have. And we had some interesting things about joint loss, which I'm also not going to go into. But the thing that's going to happen if we learn this type of a model and we actually test it, what you're going to see is behavior something like this, where for the most frequent relations or predicates, we're going to have really good performance because there's many examples of them in the data set. And for the rare relations, we're going to have a very poor performance because there are very few of them, right? And this is a rudimentary sort of this idea of data bias. So what can we do to actually improve the performance? The very simple thing that other people have done is basically resample the data set. So that if you resample the data set, then the model could be more uniform. And then you're going to get performance like this. Now, the issue is that when you're doing this type of resampling, you're basically creating additional sort of samples of the data, which is redundant, right? So now you have a much larger data set to train on. It takes longer. So the alternative strategy that we've done is essentially to do loss rescaling instead. So we're just using the original data, but we're going to rescale the loss based on the amount of data available for every class. And so we do that by introducing a weight factor, which is in a functional form, inversely depends on the class frequency and the two parameters alpha and beta, which we can tune in order to essentially trade off performance of the rare classes for very common classes. So this is the results, and the things to call out here is this is, these rows are different variants of our model where we tune these parameters, and you can see that we can either sort of get the best performance on most frequent things, or if we turn alpha and beta, we can get sort of better performance on rare classes at small expense to the most frequent ones. So it's a way of mitigating the bias. And it also gives us state-of-the-art performance overall in terms of sort of other models that's available. Now, one last thing to mention about this model is this is qualitative results. So you can see how the graphs actually improve over iterations of this refinement. And so one of the nice properties of this model is that that means that we can also sort of cut off computation at any point, right? We can just do one step and then get worse a result. We can do 2, 3, 4, 5, however many steps the computation allows us to do, and then we got sort of best result at that particular stage. So we can trade off computation for performance. In the very last 2 minutes, I'm going to tell you about the last thing, which is essentially the last strategy is adding prior knowledge. So you don't necessarily need to learn everything, right? If you learn everything, it requires a lot of data. But if you have prior knowledge, for example, about processes or other things, it could be a lot more efficient. So in this particular case, we had a vision question answering system. And what we do is we have an image, we have a question, and it produces an answer. Basically, it's an agent that would produce an answer for us. In this particular case, where it's asked about this animal known for acute senses, including what, it should answer like hearing and smell. And this requires both visual knowledge to figure out that there's a cat in the image, but also common sense semantic knowledge to figure out what cats are like and what their sort of properties are. And so if we train sort of a standard language model type of an architecture for this, which has been done, that actually does pretty well on the task, but it does require a lot of data. But if we just add a simple component, which is essentially a common sense component that's going to say, like, what is this object like, what properties it has, and what other things, which is actually a neural component in itself, then that could serve as context for making better predictions. And so the point I wanted to draw here is that we don't necessarily get the best performance out of all the models, but if we compare to the performance of Pika base, for example, we get pretty much comparable performance, but we're using 118 million parameters instead of a GPT-3, which is 175 billion. So orders of magnitude smaller model and orders of magnitude smaller data, right? So basically getting the same performance at much lower cost in terms of the data and the model size. All right, some qualitative things. We can also visualize sort of common sense that's being used. And I just want to conclude. So what I've done is hopefully I convinced you that data efficiency and bias are important things. There's many mitigating techniques for this. I talked about a couple of them, like large models and foundational models and using prior knowledge. About the computational efficiency, I talked about this iterative inference, which is in a lot of cases is also called cascades, that you can cut off at certain levels and trade off performance for speed. And there's many other techniques that I'm not talking about, right? So do check it out, not just my work, but others in the field. Hopefully it's useful for the inspection. So thank you, and thanks to my entire group.
We can take 1 to 2 short questions. Anyone has? Yeah, go ahead.
A bit of a technical question. When you measure the error on the patch completion.
Sorry, can you come to the?
Yeah.
When you measure the error on the patch completion algorithm, do you take into account pixel values or just the class?
Pixel values. It's literally trying to predict normalize RGB values. Yeah.
Thank you. Sure. Okay, thank you. Thank you.
Thanks.
Okay, so building on our exploration of cutting edge topics, we now transition to our next keynote speaker. It is my pleasure to introduce Dr. Cheng, founder and president of OG Technologies, a leading provider of inline machine vision inspection systems. With his expertise in system design and integration, Dr. Cheng will enlighten us on imaging under challenging conditions and application case in steel mills. Let's welcome Dr. Cheng.
Physics.
Thank you very much for the opportunity to be here. I'm not going to talk about math or models or anything of methods. It's more like a case report of imaging applications in manufacturing. So vision-based inspection in manufacturing have different categories. It ranges from like a component or feature check or surveillance monitoring. So things has to go in the right place, for instance, or dimensional measurement, or one step further, shape conformity. And what I'm going to focus today would be surface imperfection detection. Okay, that's actually what I'm going to focus on. So let's talk about the object. The object is actually quite simple. It's a cylinder we're going to talk about. It's a bit more complicated than flat surface. It's round anyway. But we can see that there are defects along on this bar, different shapes. It can be like this. It can be like this, very obvious, but it's visible by naked eyes. So it's in the millimeter level. However, if we look at another piece here, there's nothing really immediately visible by naked eyes. And if we zoom in and look closer, there is a crack there. Okay, so it's actually in the micron level. Not a really big deal in today's technology because it's still in the visible light range. Okay, we're not talking about nano yet. But even for that, it can be complicated by the working conditions it gets into. So in this case, we're dealing with temperatures that are actually 1,000 degrees Celsius. That's about 2020 degree Fahrenheit. And the speed today, the steels, you probably won't believe how fast they move this hot piece of metal. Can go up to 112 meters per second. That's about 400 kilometers per hour, or 250 miles per hour. That's how fast it's moving. And again, going back, we're talking about micron level defects for inspection. And worse yet, okay, it's non-clean room. And I actually have videos here. It's not, unfortunately, not working here, not converting properly. So we're dealing with water, high-speed vibration, and you can see some smoke, or you actually would see spark right here. And we got flames here to show. So not quite a friendly environment to be with. So the problem really is, I would conclude it as one word: variability. Traditionally, or typically in image processing, we will try to identify the invariant in the images and then detect anything other than staying the invariant. That's for the defect detection, traditionally, or any kind of anomaly detection. However, we may be in a situation that the definition of surface defect may not be well defined, as well as the surrounding conditions may be changing as well. So that makes the issue interesting. So let's first ask a question: what really is a surface defect? I don't really have a good answer for you, unfortunately, really. Because take a vehicle as an example. Whatever you visually can see, the manufacturer, Ford, General Motors, those automakers care about, they call it a Class A surface. They call it Class A surface. Any smallest, lightest scratch in any shape, any form, any orientation, they care about it. It's considered a defect. Does that affect the function of the vehicle? No, but it's a defect. But if you look at a car, there are many parts in the car that you probably would not see during your entire ownership. And if we go back to the piece of steel that has defect on it, you probably would not like this piece of steel being made into parts that go under your engine hood. You don't want it to be your coil spring for your suspension. You don't want it to be the gears in your transmission, and you certainly don't want it to be the fastener to tie your wheels to your hub. Risky, right? There's a safety issue there. So in conclusion, even for the bottom line, the definition of surface defect itself can vary from one application to another. And even in our case, we've seen the definition even varying in a single application for different products, different markets, different users, and sometimes even for one defect to another, it can vary. Unfortunately, that's about surface defects. And the surrounding conditions doesn't make it any easier, particularly in our case for the steel mill applications. Temperature is nothing really specific. We've seen the laser manufacturing earlier in this morning's presentation. However, oxygen is not a friend at high temperature. We will be dealing with something like this. It's really arbitrary on the surface over time. And speed does complicate the issue at 112 meters per second. However, today's imaging processing capability or optics, particularly in the visible light range, is not that much of a big deal. The problem really is when temperature and speed combine together, it generates something unique. Then we are dealing with now an object that is hot, that moves fast, and it is soft. Now, steel is soft. Okay, steel at that temperature is not much harder than the spaghetti on your dinner table, trust me. And that created a problem because in terms of handling, we don't like to touch it. And as a result, there's no precise motion. And you can imagine when the object is not steady, it's not well controlled, and you're imaging at the micron pixel level. You're not going to get picture perfect photos every single time. As a result, you're dealing with a lot of variability. And furthermore, because you don't have, because it's soft, the motion will create defects on its own over the manufacturing process or even the transportation process. So that introduced a lot of variability as well. We showed some photos before in terms of a spark, smoke, dust, etc. And I did mention spaghetti. Okay, that's about 2 tons of spaghetti piling up right there. That's catastrophic. So the imaging system has to survive that. one thing on this slide I really want to emphasize would be the surface defect. Really, surface defect, what are they? They are actually noises to the normal surface. So a typical schemes or approach to do noise reduction in image processing would not be adequate. I'm not saying it doesn't work. It's not quite adequate. So in terms of noises, other than the real defects, we either have to prevent it or to live with it, meaning to find a way to differentiate the real defect from noises. So here are some examples of different type of defects we can see. Now, these three are actually all the same defects, but they come in different forms. And these are only examples. They can vary by shape, vary by length, vary by orientation. Scratches does look like a scratch, and they also come in from a different orientation, different shape as well. On the right-hand side, I want to show you, as I mentioned earlier, there's same defects when viewed from a different angle. They may be sometimes difficult to differentiate or detect, because like in this case, it's big enough so that even though they look different, they can still be detected. But for this particular defect, we can detect it from this view, but it's kind of difficult from another angle to see it. The background noises. So we're dealing with water, smoke, spark, pool mark, scale, rubbing mark, different kind of reflectivity because of material, and vibrations. And the extreme of that can go as high as 1,000 hertz. Now, keep in mind, these by no means exclusive. So one noise does not exclude the other from happening. So they cannot be combined. Aside from the variation in terms of the noise or the defect itself, for an imaging system to work in industrial environment, there are other constraints. So for a particular application, we need to think about component availability, which is not much of a big deal today because of the technology advancement. Clock ticks, the throughputs required. For instance, when the steel is moving at 100 meters per second, you have to sustain, in our case, more than 180 seconds at least. And then you got to break about 5 seconds. Then another piece will come. So you have to finish all the inspection within that time frame, basically 150, almost real time, almost real time. Space is another issue, particularly to fit into existing equipment or existing lines. It might be easier for discrete parts. We saw a lot of things that are made, like this part is a discrete part. You can easier to take it offline, inspect it, put it back in line. But there are applications like we are talking about the steel that keep coming. It's more like a web or semi-web manufacturing. Space really would be an issue. There are obvious space, you can go walk in and see, and there are some latent space restrictions. I once in a steel mill looking at big space in the plant. I said, well, you guys got a lot of space to install my equipment. There's no problem. The foreman just tell me, stay here for the next 24 hours and you'll know. No, they don't have any space. Because when the mill has some startup phases that will take up all the space that they need. The critical thing I would say here in our experience, working with different customers, this is really an issue we all have to think about it when we take the technology to the market or to the actual industrial application. Every single plant has their own style of operation, their own style of maintenance, and their own style of management. It's limited by their resources, how many people they have, limited by their working habit or managers, preferred indexes. So it's completely different. And that does affect the performance of a piece of equipment like an inspection system. Once we address all that, the technical feasibility does not automatically lead to an application or a successful application, because dollar cents will kick in. It depends how much the users are willing to pay for. So we've seen different categories of customers. There are customers that are quality inspection is a must. Quality is a must because that's a threshold into the market, or by regulation they have to do it. And there are customers that quality is the base for their business to grow, so they will have put it a very high priority. And there are customers that we call it quality sensitive. It's only higher quality will give them higher profit, but slightly less quality will still give them profit, but not as much. But they may be overcome it by quantity. So there's always a balance. And circumstances do change. For instance, Toyota used to be very picky. However, in 2021, because of the supply chain issue, they actually changed their rules in terms of surface defect acceptance. So in my opinion, if we define the defect as, or the target we want to detect as the foreground, and the rest of the image is the background, I would say that if we plot into a chart with the variability, when the background and the foreground variability are both low, I would call it a good application. That means you probably can get something off the shelf today, and it's easier to deploy into the actual production line. And when one of the variability goes higher, I would say it's still accomplishable, achievable, but it will require a good set of skills to do it. And when both are having high degrees of variability, that will be challenging. It needs a lot of skills, and sometimes it's fun, and sometimes it's frustrating. On this chart, we can actually draw a line. And if you are limited by budget, these funds are not supposed to be that big, sorry. That I would call it trade-off, and we'll always deal with trade-offs. And that is limiting as to whether your application would be feasible or would be accepted by the market or by the user. Now, these things are dynamic. It's not fixed because we always deal with innovation or development or R&Ds, a lot of experts here to help us. We can shift these limits so that it becomes more and more popular and be adopted by the industry. To cope with the variability, here's again our experience of FuSoft, going from physically prevent the variability happening. Like this, my top priority and my preferred one to go to. My dream is to build a vacuum clean room in the steel mill. That's my dream, but so far, unfortunately, I have not found a customer that will allow me to do that, unfortunately. So we have to do something else. First, I would say, personally, I would apply deterministic, like engineering knowledge first to help me. And then if that really still haven't solved the problem, that goes back to the experts of image processing, go to the high dimension discernibility operations. So here are some examples of physical noise reduction. In the steel mill, there's only two ways, either water or air. Water, we're dealing with that high pressure, 250 PSI descaling. So you can see the difference here. And air stripping to get rid of water, dust, etc. And on the left-hand side, we can see some examples. This one is really, I show you the scales. Those are covered by the scales. In the middle is somewhat clean. On the right-hand side is truly clean. Okay. Cleaning is good. Again, that's my preferred way. However, it comes with a price tag. It depends on whether the user is willing to pay for it. And do we really need it to be this clean, or can we live with this? In reality, I would have to say most of the time, more than 90% of the time, we're dealing with somewhere in between the two. between no cleaning and this degrees of cleaning. In terms of applying engineering knowledge, here I would like to give you a few examples here. Now, first one is a repeating mark detection. If you know how the steel rolls, it's more like a spaghetti machine. You take a wheel and keep rolling it. So if you have a dent on the roll, it will continue to repeat. For instance, we got a mark here, we got another mark here, another mark here. So this one is real easy. So if you know it's repeating and you know its pitch has a range like from 75 millimeter to 20,000 millimeter over a length of 14,000 meter, pretty long again. It moves fast. So this one is easy to detect. The next one isn't too bad either, so it's quite visible. This one is a little more difficult. We can easily see this dent here, and there's dent here. So they're supposed to be the third one. It's right here. Kind of a little different shape. Why? Again, going back, we do not have precise motion control for an object that hot and moving that fast. So as a result, even a print, it may not be printed exactly the same way. So it's harder to detect, but we can detect it. Now, if we look at this set of defects from a different perspective, that will be this image. They are actually identical. These two are the same. It's just a different camera taking the pictures. And it will result in these three small white dots. So those has to be detected there. It does come from come into a different form too. I don't know whether you can see it. There's a light longitudinal curves here. So it can come in a different shape as well. And find cracks. So detecting these cracks is no big deal. That's day and night because the background and the foreground differs quite so much. What we are looking for really is there's a crack inside here among these scale marks, and to detect this line. The same thing is, it's not, the pronounced black line here is not a defect, but a defect right here, right next to it, there's a crack line. That's a real defect. So how to differentiate them? How to identify the true one? Needs some, and actually we did that without, it's not based on image model or learning model, it's based on engineering knowledge. Same thing for a transverse one. So now, if all those things wouldn't work, we have to really come to some kind of learning models that a lot of experts has been discussing today so far. To us, I know, I heard you. Okay, we're talking about using fewest samples for precisest models. I heard you. But in reality, so far, our experience is the number of samples does matter. The higher the sample number and the more complete the different sample sets or sample types do matter. Now the key again, but the key really when you deal with a large sample, consistent labeling becomes an issue and that needs to be addressed. But if you can address all these three, the decision boundaries can be better defined in our experience. And to address the consistent labeling, so one thing we do today is to do unsupervised labeling or unsupervised cluster that helps our engineers to do the consistent, or our customers to achieve consistent labeling. Okay, we do have some examples, like we send in 50,000 image samples for this kind of results. We can get, to us, is satisfactory. We can greatly reduce human interventions into the samples. So with that, the summary is, for the application of imaging into in the manufacturing, in real manufacturing, we really need to think beyond imaging or beyond image processing. We have to engineer not only the image or image processing, but also engineer for the image or image processing to work in that environment. And the next thing that's important, or to, at least to me personally, I will use the word alignment. Early on, we stick to, when we engage with the users, we stick to the word like tuning, fine tuning, or adjust the settings. At the end of the day, or today, our thought would be more about alignment, because we are having a technology of detecting, again, the surface, as a surface defect is not well defined. So there's a lot of alignment work. Now, let's forget about the good and the bad. There's always white, and we know it's all white. It's universally white, and there's always black is universally black. But the gray area, where you make the cut, that needs alignment. You have to learn from the user and learn from the market. Another key notion we have in terms of industrial application really would be prevented from failing. And that's a lot different than making it work. Making it work is essential. But for industrial use, is to prevent it from failing. You have to be adaptive to new batch. So I make a batch of new phones now. The next batch comes in, your algorithm doesn't work. That ain't going to work in the industry. Or if the production equipment changed, or if it works in the United States, doesn't work in China or Europe, that's not going to fly. And I would be cautious on extrapolation in conclusion. Okay, I would be cautious on extrapolation. Our experience is interpolation typically is fine if you build up the foundation well. So that would be our experience in terms of that. So in addition to that, I'd like to show a few other applications. For instance, we're dealing with really different reflectivity. It can go really shiny, like mirror-like surfaces, to black surfaces. And dealing with complicated shapes, we talk about solid cylinder. So different rails, and even in the case of rebars, reinforcing bars in the construction. You may think this is low grade, but the newer standards, particularly for the tunnels or bridges, do require the inspection of them. And our newest challenge, and it's still in the trial mode, is to do inspection for hot on the internal surfaces. That would be a really challenging. We look forward to that challenge. And the other thing we do really is 3D inspection. 3D, in our view, it has a higher dimension. It actually helps and provides more features to overcome noise. So the application we choose is to apply it to continuous testing, where on the surface it has a lot of irregularity. For instance, there's nothing smooth here. And to detect defects like these small holes, I mean, 3D is a little interesting. 3D rendering is a little interesting. You give it a different angle, you see it, you won't see it from a different angle. So to detect these are the actual surface, these pinholes, to detect them and present them. With that, I thank you very much for your attention and welcome any question. Thank you.
For one question, if anyone has a question here. Yeah, can you come to the mic?
Hi. I don't know if you can share, but what kind of techniques do you use to do the clustering of the data points? What kind of features? Is it just standard, straight off the mill, something like, what clustering algorithms?
Actually, exactly, I don't know. Actually, there are experts who probably here probably can answer that question. Jen, you want to answer that? It's not that I don't want to tell you a lot of things. It's because we are in industry, so there could be a combination of how to make it work.
Yeah.
You know, instead of sticking to a certain method and then and stay with that method. So it sometimes can be a little more complicated than that.
Thank you.
Okay, thank you. Thank you.
Thank you.
So now we have a panel discussion with the panelists from very diverse background. I would like to invite Gogberg here for moderating this panel discussion. So please, all the panelists, please join us in the table here. Dr. Angel, Joseph Rubin, Rahul Kapoor, Daniel, Dr. Colosimo, Dr. Eagle.
And actually, we have one more guest, Professor InduStrial. Welcome to our workshop, and welcome to the last minute invitation. And thanks for joining us. Yeah.
I showed up here intending to sit in the back and just listen quietly. I wasn't expecting to be invited to join the panel. I hope you don't mind.
Pleasure.
Hello, everyone. It's a pleasure to be here today with such a great group of panelists. I'm Gökberk Cimbiş. I'm from Middle East Technical University in Ankara, in Turkey. I'll try my best to moderate today's discussion. So based on a detailed study we prepared together with organizing committee members, we prepared a list of questions. The panel discussion will be based on these questions and topics that we have prepared. On behalf of the organizing committee, I would like to thank all panel members for agreeing to be here. I think we are all very excited for the discussion that we are going to have. I would, yeah. Yeah, very good. We don't want to spend too much time on introductions, but I think it's better I do it. So I would like to briefly mention bios. They are all very long, but I'll try my best to summarize them. In the order of last names, Dr. Danny Bixson is here. Thank you very much. Dr. Bixson is a graduate of Hebrew University of Jerusalem, and he is known as one of the co-authors of the famous distributed ML framework Graph Lab, founded at Carnegie Mellon University. Dr. Bixson was also a co-founder of the ML startup Turi, which was later acquired by Apple in 2016. Most recently, he is working on his startup Visual Layer, backed by prominent VCs, where he is currently the CEO. Thank you very much. Dr. Cheng is here. Thank you very much. Dr. Cheng obtained his PhD degree from University of Michigan in 1995 on system design and integration. He's a co-founder of the established company OG Technologies, where Dr. Cheng has been the Chief Technical Officer leading R&D projects focused on surface defect problems. And since 2011, Dr. Cheng is the president of the company. Professor Bianca Maria Colosimo is a full professor at, thank you very much. I'm sorry. Professor Colosimo is a full professor at the established University Politecnico di Milano, where she is the deputy head of the Department of Mechanical Engineering and a member of the board designing the strategic agenda of the university for the next decade. She is a member of the implementation support group of the Manufacture European Union, member of the steering committee of EU Vanguard Initiative on 3D printing, member of the board of directors EIT Manufacturing, and she is currently the department editor of IISE Transactions, senior editor of Informs, Journal of Data Science, and editor of Progress in Additive Manufacturing. Thank you very much for being here. Professor Andrew Ng, I think he doesn't need any introduction at CVPR, but I still will go over his short bio, short bio from his webpage. Thank you very much for accepting our impromptu invitation. Andrew Ng is a globally recognized leader in AI. He is founder of DeepLearning.ai, founder of and CEO of Landing AI, general partner at AI Fund, chairman and co-founder of Coursera, and an adjunct professor at Stanford University's Computer Science Department. He's a well-known pioneer in machine learning and online education, and he has changed countless lives through his work in AI and co-authored over 200 research papers in machine learning, robotics, and related fields. In 2013, he was named to the Time 100 list of most influential persons in the world. Thank you very much again. Rahul Kapoor is also here with us today. Mr. Kapoor received his MSc degree from Carnegie Mellon University in 2004, and in the following 19 years, he worked at Bosch at various positions, including Director of Data Science and AI, Senior Director of Bosch Center of AI, and Vice President of Global Head of AI Services and Engineering. Since March 2022, he's the Director of Machine Learning at Apple. Thank you very much for being here. Next, Joseph Rubin. Mr. Rubin is a graduate of Stanford University, Wilfrid Laurier University, and the University of Waterloo. He has acted in a variety of positions, including reliability engineer, project manager, mechanical designer, and senior applications engineer at General Motors, Canadian Nuclear Safety Commission, DSR Systems, and ATS. Since 2010, Mr. Rubin is with Apple and currently the senior manager in manufacturing, design, metrology, and inspection automation. Thank you very much for being here. And Professor Jane Shi, for those who are new here, I'll also go over his bio. Professor Jane Shi received his PhD in mechanical engineering from the University of Michigan in 1992, and he is currently the professor in industrial and systems engineer and mechanical engineering at Georgia Institute of Technology. Prior to joining Georgia Tech, he was a professor of engineering at University of Michigan. He's the editor of flagship journals and a fellow of American Society of Mechanical Engineering and fellow of a variety of prestigious institutions and organizations and a member of National Academy of Engineering. Thank you very much for being here. Yes, sorry, I couldn't see you. And Professor Leonid Segal. I'll speed up the bios. Sorry, I'm not fast enough, but Professor Segal, thank you very much for being here. He received his PhD from Brown University, and he's currently a faculty member in the Department of Computer Science at University of British Columbia. He's a NSERC Canada Research Chair and CVPR AI Chair at the Vector Institute. He has been a recipient of multiple Best Paper Awards, and he has been part of the editorial board and organizing committee of leading journals and conferences. Thank you very much for being here. And Dr. Angel Tuzel is also here with us. He received his PhD from Rutgers University in 2008. And following his PhD, he worked at Mitsubishi Electric Research Laboratories until 2016. And he is currently with Apple AI Research Group, where he is a principal researcher and a research manager. He has co-authored over 50 peer-reviewed papers and holds over 35 patents. He is a recipient of Best Paper Award, Best at CVPR, Best Runner-Up Award in 2007 CVPR, the Best Paper in 2017, and an Honorable Mention Award in Robotics Science and Systems Conference 2015, and the 2014 R&D 100 Award, awarded to top 100 most innovative technologies. Thank you very much for being here. So it's been a bit longer than I planned, but I would like to thank again for all panelists for being here. Sorry. So I would like to start discussion with the predetermined topics. Maybe we can start, since this is a visual inspection workshop, maybe we can start with the discussion or more from the manufacturing side. We have a question on the evolution of measurement technologies for quality control, where it was and where it is today. What are the major trends and future directions? Perhaps Professor Shi, you may initiate the discussion. Thank you very much.
Okay, I'll be quick. I'm doing the manufacturing process control for 30 years, and over the years, I see how these sensors evolve for the manufacturing system. Instead of talking about the specific sensors, I think the types of data generated from sensor is something could be interesting. In the very beginning, I would say 30, 35 years ago, lots of sensors are go, no go gauge in automotive industry, basically good, not good. And later on, they have measurements on the critical dimensions, the temperature, basically different numbers, individual numbers. Even they have generated curves, use some simple image in some time. They still translate into dimension, into the temperature, the average. So that kind of time about 30 years ago. Later on, there are functional curves. They measure the force, they measure the temperature over time. So the functional curve becoming more important. And later on, they have a multi-channel functional curves. They analyze that kind of multi-channels simultaneously. And then image coming in. So people use image to do different measurements. It's not translated into individual numbers from the image, but the image itself. And of course, the video signals coming in and monitor the product quality and the process variables. And right now, like in this conference, there are much more high dimensional, high resolution, high speed sensing video signals coming in additional high resolution wave signals, the text data. And more importantly, in the last 5 years also, I would say, all this sensing data become centralized, either centralized or distributed sensing, but still data are available. So how to analyze those heterogeneous data for quality improvements become more and more important. I just mentioned the sensing aspects, but all together come with computation capabilities, communication capabilities, and more important, the data science go with it. Start from basic SPC to multivariate SPC, functional data analysis, wavelets, and Bayesian probability network, and tensor-based monitoring, tensor analysis, anomaly detection. And right now, I think the talk of the future or talking about what's going to be. So that will be heterogeneous data modeling analysis, and more important, the different types of data, different types of sensings work together to get holistic model from the product quality as a response, and all types of sensing data, process variables, material property as a text data, they all work together and how to improve the quality. Basically try to do monitoring, diagnosis, prognostics, control for defect prevention.
Thank you very much. Are there any panelists that want to comment on this?
So, just add extra perspective, agree with what you said. There's one problem that I think is pervasive across manufacturing inspection, which is the heterogeneity of the applications. And even if we just look at image data, which has been where I focus, but I agree also about heterogeneity of data. Every manufacturer makes their own unique object. And so every manufacturer has their own images. And so every single manufacturer, every single product that's needed needs a custom machine learning model. I remember when Rahul was leading AI at Bosch, right? His team had tons of demands from tons of different groups, all of which had different images, and everyone needed a custom machine learning model built. And what I'm seeing is that it's not scalable for anyone's team to hire enough machine learning engineers to solve all of the custom image, all of the custom problems, computer vision for me, maybe others, that our users and customers need. So I feel quite strongly that in computer vision, our fields figured out how to build the single piece of software that makes $100 million, like face recognition or driver assistance or something. So we know how to do that. But in manufacturing, with the long tail, where instead of one $100 million project, we have tens of thousands of $1 or $5 million projects. And the challenge is, how do you solve 10,000 unique computer vision problems? And so I feel the approach that I've been taking, landing AI, is to build tools that make it easy for non-AI specialists to build and deploy custom computer vision applications. I think that's critical for us as a field to get all the tens of thousands of custom vision systems built that in turn will create even more value than I think like the giant face recognition system or the giant driver assistance system that people tend to talk about at CVPR.
If I can add something that I think it's changing, that I think it's changing the landscape. It's this Internet of Things, and the cloud computing. So what is happening is that we are really enjoying a lot of data across many different machines that are spread in many different settings. And I think this is going to change the way in which we are used to create the software and algorithms that are just staying on the machine, but then enjoying also that data can come from many different domains and many different applications. And so the challenge, I think, is try to find some hierarchical way of sharing the knowledge coming from many different plants, so that the machine start becoming a little bit more intelligent, not just using the data in very simple mode, but also learning while the machine is running. I think that this is the future that the machine tool builders are asking us to solve together with them.
Thank you very much for all the views and comments. I would like to continue to the second topic, more to the deep learning and CVPR side of things, let's say. We are aware that there have been very impressive developments in statistical generative models, and one interesting avenue is their use in synthesizing training data. But there are a number of questions, problems, including data reliability, data set balance, the balance of samples generated from deep generative models, and covering edge cases, properly training conditional models, effectively ensuring that the samples generated are compatible with the conditions provided. And of course, the question of realism, how much realism do we need? Do they really need to be photorealistic? or are there other bottlenecks that we should pay attention to? Perhaps, Dr. Önder Tüzel, we may initiate the discussion.
Okay, I'm going to talk in general about using synthetic data for machine learning in a broader sense, both vision problems and other domains. So in my experience, I find it extremely useful to use both simulations, physical simulations like computer graphics, and then simulating data using computer graphics in vision domain to be extremely helpful. Similarly, using generative models. And actually there's synergy between these, and they are pretty much complementary. Let's start with the simulation side of the things. We have a very good understanding of the world and how it works, objects, their relations with each other. And we have, over the years, we have built really good techniques, very good simulators, for example, Carla, or even more realistic simulations that's shown to be very promising in terms of training recognition models. In the manufacturing domain, this is particularly critical because like when there's a process that's been started, probably we have very little data. We have new objects that are coming and we would like to inspect, and there's not much data. Simulation in this case is extremely useful. We can easily create edge cases that we have not seen in the past. So this is really promising. On the other hand, there are some drawbacks of this. So we can collect some data, or we can replace it with simulated data through a graphic simulation. The problem is that now we are delegating the task of collecting and annotating data from the data collection process to artists. So they need to really go and create these assets. Maybe depending on the domain, animate these assets or put them in realistic scenes, control the lighting, and generate a lot of variation in the scene. So it's a little bit of a chicken and egg problem, so that we are moving from the data collection process to the simulation process. And since artists are creating this, capturing all the variation will be pretty difficult. So we will have a little bit less variation in terms of what we could see, and the realism of these assets that are created, or the training data that's created, will be a little bit less. On the other hand, we have the generative modeling aspect of it. Over the years, for example, we have similar inspection problems, and we have a lot of data that has been collected. Maybe the new object that we have, we are interested in recognizing the defects, that's not the same object, but we can learn really good generative models from the past data that we have observed, and we can use it to synthesize data for the upcoming objects that we are interested in. Though, in my experience, it's really important to be careful how we use the simulated data, particularly from the generative model. This is also a little bit of an interesting paradigm because we have all this data. We can directly train recognition models. Alternative is we can learn a generative model and synthesize more data. Where's this additional information coming from, right? So in here, what we observe is that when we train generative models, it's really important to think about the space, and particularly the latent factors that generates the scene. For example, if you're interested in different objects and different defects, can we create different defect types? Can we control the illumination of the scene? Can we capture it from arbitrary views that we would like to place our sensors? If we can really control these different factors of generation, then we can targetfully generate what we are missing in our training set. So this seems to be actually extremely important in targetfully improving the downstream processes. The other thing that, in addition to being able to control the variation in the scene, is synthetic data or rendered scenes will never be as realistic as the real data. So if you are not careful, then rather than improving what we would like to improve as a downstream task, this might actually start hurting us. And we have seen this across many different domains: vision, speech, language. And to do that, but the data doesn't have to be perfect. What we could do is that as a post-process, we can, during training our downstream models, we can be careful and we can address the domain gap between real and synthetic data. Over the years, there has been, again, like multitude of methods that have been developed to address the domain gap, and many of them actually seems to be pretty powerful.
Thank you very much. Anyone else that want to continue the discussion? Yes, please.
Yeah.
Hi, so I worked at Google for 5 years along with Onsel here and Meng and Joseph, and we worked on glass inspection, which is very tricky problem. And one factor that we didn't discuss yet is the human in the loop. So what really slowed us down is that when we did the collection of data set, it's huge amount of information. You don't need to generate because you have so many, just you have to find them and label them, but the annotators are so bad at the factories and they are so often mistaken that you deal with such a large amounts of bad data. And as Andrew here says, the data-centric approach is really the thing. If you don't have high quality enough data, you are really doomed. The same with all the generative AI models. They are amazing. It's a huge trend. It's for us, it's fun to see the development, but if you rely on bad data set for training those models, you may have unexpected results, which may be super weird. So the approach we are taking now with Visual Layer is taking a step back and looking first at the data quality issues. Before that, you cannot progress for the more advanced and fun and generative models before you really check what's going on with your data set.
I'm just going to add one quick thing, and that is for a certain domain, if you do have good simulators, one alternative to generating lots of data from those simulators is to build those simulators as priors essentially into the recognition models themselves. And that actually alleviates the need to generate and effectively learn those factors from the data, whereas they can just be built into the model, and then you're essentially inferring the latent factors that you need in those cases. Now that doesn't always works, right? Like one of the good things about generative models is that we can just have examples. We don't necessarily need to understand the process which leads to them, and then it'll generate other sort of interpolations of that data. But I think for other processes where there do exist good models, that could be a very effective approach for actually building good recognition systems.
Thank you very much. All very interesting points, important points. I think this is a very interesting topic, but we need to move on to other topics for the sake of time. I would like to continue with a topic that that requires understanding on what's going on in research and what companies need. So what are some of the open problems in automated visual inspection that requires midterm, long-term research, perhaps more academic attention in research? So perhaps Mr. Kapoor can initiate the discussion.
So I would like to answer the academic question from a business standpoint. So if I look at it from a business standpoint, one thing that we really care about is time to market for any product. So if we have a new product that we're launching, or a variation of a new product, or a product that belongs in a certain product family or product line, we would not want to start from scratch every time. And even if we don't today, then we would like to accelerate that process as much as possible. And then when you think about that, then the question is, what are the big bottlenecks in that? And then, of course, data collection, data annotation, rare defects that appear probably after a certain time. These are the questions that come up. And hence, I would like to reemphasize the need for something like a synthetic defect generation system that works very well. So that is one thing. Second, along the same lines, explainability is something we didn't touch on so far, but very often what we see is that once we hit a certain threshold of performance very fast, then especially for complex AI tasks, start turning the wheels. So we are not moving forward anymore, right? At that point, it is really important for the machine learning engineers, or even if we are going for more self-serve approaches, to really understand where the problems are, like why is the model not doing well, and where can you do something actionable to improve that performance. So something along the lines of what I call as model debugging toolset would be really great. Third, from a model performance, especially for inspection of cosmetic systems, like what was shown about the scratches on the car and so on, what we see very often is it becomes difficult to distinguish or differentiate between real defects sometimes and what look like defects on images, but they can be cleaned away, right? And Now the question is, where should we solve that problem? Should it be solved on the hardware layer, where we work with imaging system and lighting systems and make them better to see one thing and actually not see the other? Or should it be on the annotation side, or with the data, more data-centric approach, right, to improve that? Or with on the modeling side, where we let the model do the heavy lifting. So that would be one question I would put as an open question to the research community there. And how many can I say, by the way? But I would like to emphasize maybe one last, what Andrew had highlighted. If we are dealing with systems at scale, at very large scale, then machine learning teams should not become the bottleneck of scaling and deployment. And then the question becomes, if you want to give the power in the hands of non-experts, non-MLEs, then do we have systems that can allow us to do that end to end, right? Do we have the right tools, or can we put together all of these tools that we spoke about in a manner where you can have generalization, but also end user customization as well? And that would be another big topic that would make a big difference, I would say, in the industry. So yeah.
Thank you very much. Perhaps Mr. Rubin is working closely with manufacturing teams. You may also continue the discussion.
That's fine. I have a launch list just as long as it is, but I'll try not to take that the whole time. I think maybe just one thing to add on what Roel was talking about is like actually tools. In a lot of the discussions today has been on like once we add the actual imaging, but how do we actually know we've optimized the actual imaging? I've seen very little tools to say like, hey, there's an escape, or we're not seeing something in the image of like, we've talked about a lot of like pixel resolution, but how do we know is we've gone down low enough? Hey, we can go down to like whatever, 1 micron. Is 1 micron good enough? Is it 0.5? Or can we live with 100? The actual optimization of that entire setup on the hardware stack, there's really no tools to kind of set up and say like, put something into a box, do an evaluation and say, hey, we can go through our standard suite of vision setup, go through the standard set of lights and say, this will work using, say, like a 5 megapixel camera, or it will usually using on that side. So actually understanding of an optimization cycle for the hardware side is a tool that honestly doesn't exist, and in the long term can go a long way to like advancing, because a lot of the premise is like we can actually see in the image, but there's a point that we get to where like, oh, we made a mistake, the imaging's wrong, so then if they like throw all the model we made, go back to the start and kind of reiterate on it. So that's an interesting part of it that is like, I've seen a lot of done like trial and error. We get I've seen multiple industries where like, hey, we have a bunch of defect parts, we put them on the table, some vision engineers look at them and we think it's good enough. But then when we actually deploy it at scale, that's where some of the challenges, the things that kind of fall through the cracks actually happen. So it's just a whole bunch of tools and ability to say like, yes, this solution is good enough, or no, it's not, even if it's on like an FA basis afterwards, beyond, let's call it what was previously mentioned. And yeah, those were all, let's go this way. We experienced all those same challenges across the board.
Thank you very much. Very important points. Unless there are other.
Can I add something?
Yes, sure, please.
So I'll keep it short. Just to have an experience that may resonate with many of you. We're working on a landing AI. We'll work on inspecting these plastic injection molded parts. And I found a part that was partly melted. I couldn't tell was the defect or not. So I walked to one inspector in the plant. I was traveling at the time. And I said, hey, is this defective? And one inspector said, no, of course not. This is fine. Don't throw this out. You're wasting my money if you think this is defect. Showed to a different inspector. Second said, what? This is obviously a defect. Anyone that disagrees with me is an idiot. And so I find that one of the challenges is the human factors HCI aspect of, if even the top manufacturers in the world have inspectors that don't agree with each other, what's the software or system designed to get a consistent definition of what is the defect? Fun fact, second inspector, unknown to him, I showed him the same part later that afternoon. And guess what? He said, what? Of course, it's a defect. Anyone that thinks, and so he actually called himself an idiot, not knowing it. So I think there's that human factors of, it's really data-centric AI. If even our best inspectors and best factories don't agree, how do we extract a good data set and a consistent definition? And there's just one more challenge for research that I want to mention, which is over the last few years, I've seen building a computer vision system used to take me like 12 months, collect data, tune the model, deploy it. It was a very long process. I think that we and others have been shortening the process to, this morning I was talking about visual prompting, where with a very large pre-trained transformer model, we could use visual prompting like text prompting of ChatGPT and prompt it with 2, 3, 5 images and get something that works pretty well. One of the challenges is as the process for practical deployment becomes so fast, it's incompatible with the way we tend to publish papers in CVPR. Namely, to publish papers here, we like to collect large test sets and do a systematic evaluation of a large test set to benchmark how well different algorithms do. But we are seeing that more and more of our users are now trying to push things to deployment with 10 images. And that's not a test set, that's just a training set. So how do we think about documenting the degree to which these algorithms work or don't work when the practical machine learning process, really the best practice for many applications where there isn't risk of harm or risk of damage, just get a prototype working with a few image, deploy it, monitor in production, use that to fix and improve. But I think that there's that fundamental incompatibility with how we tend to publish papers in data-centric AI as well. If I don't like the test set, I would change the test set, right? But you can't do that in computer vision benchmarking. So how do we fix that to do research on this is something I think about a lot.
Thank you very much.
Maybe just one more thing. One other thing I always found interesting is also like just almost the standards, right? So like in let's call it just normal things like sending like Excel's kind of sent out the default standard. A lot of those challenges still exist within the community, right? Is like how do you like get all the annotation, the standard data, getting it formatted, making sure that like their interoperability going all the way around from like the life cycle, so that you can use like those 10 images and kind of easily combine or sparse out databases is also just one thing of like. In the long term, I think is also good just for the industry because right now it's always, you're almost potentially starting from scratch if you're moving different vendors. That interoperability of like the imaging and learning is challenging on that side because otherwise you just have to reformat data, which can be challenging at times.
Thank you very much. Yeah, I would like to continue to the next topic before we run out of time. We would like to cover 3 more topics. So we've seen great developments in large language models and vision and language models, and also foundational models. We've seen also a lot of interest in zero-shot learning, few-shot learning, continual learning. So the question is basically what are the implications and potential applications of these developments in language models, vision language models, in visual inspection, and a related question, the few-shot learning, continual learning approaches built on top of these foundational models, are they ready for prime time? Do they have reached a maturity level that can be used in practice? Perhaps Professor Leonid Segal can initiate the discussion, and I would also love to hear Professor Ng's point of view.
No, I got 2. I have 2. Sure, I can start. I think in terms of the foundation models and these large scale models, so going back to what Andrew said earlier, where there is sort of this long tail and you need to bootstrap these models quickly. I think that's a very promising direction in terms of doing that. I think there should be a foundational inspection model that we can leverage for basically bootstrapping and doing something very quickly with limited amounts of data. Because I can assume that at least within a certain industry there'd be transferability across different problems. So I think that's a very promising direction. There's a question of how do you actually get there, particularly if you want to pull data from different vendors and different places. Maybe you need sort of ways to obfuscate some of this data. Once you're training, you get into some of these new techniques and federated learning and other things that may be required in order to do that. But I think as a direction, it sounds very promising to me, and I do believe that we'll get there at some point. In terms of the second part of the question, with continual learning, I think that is very important, both for inspection systems and I think more broadly in vision, actually, because I feel like that's a very important thing where we are approaching where just having a single test training set and single test set isn't really a realistic scenario in most applications for real, right? We're going to get some more data at some point. We're We're going to want to improve our model, and we want the improved model to basically generalize better than the previous one. And we want to continue this cycle and basically make that cycle fairly quick so that we can get these models that are getting better, but also don't deteriorate, because one of the issues is that when you're continually learning, you can also diverge in building a model that's actually is not performing well. And continual learning has been around for quite some time. This is something I'm actually getting into in terms of the research direction. There's quite a bit of sort of things on if you want to do maybe classification or simple scenarios, but I think there's still a lot to be done in the space, particularly for detection and other type of problems. So I don't think that's quite ready for deployment, but I think it's a very promising direction in terms of building tools forward for us researchers, but also collaborating with industry, because this is where these data pipelines are actually very realistic incarnations of this type of process, which, you know, in academia, we have to sort of synthesize or so on. But in reality, you know, if you have a factory floor, that's what happens. You get data every day, and there's more data coming in over time. You get some of the labels, perhaps you discover new artifacts that you need to detect, right? So your actual set of labels is also changing over time. So that's a very realistic scenario that I'm personally very interested in pushing tools forward for.
Thank you very much. Yes, it would be great if you can.
Well, it feels like I'm talking too much. Certainly, yeah, I agree with everything Professor Segal said, and I think that you know, I think vision transformers are kind of getting there. I remember a couple of years ago, before ChatGPT broke onto the text processing scene, when we go to the NLP conferences, everyone knew there was something in the air about transformers. And when I walk around CVPR now, I feel like, yeah, we all feel there's something in the air about vision transformers. And I think going forward, the recipe of a large vision transformer, followed by a very relatively small amount of data for fine-tuning or prompting or some other ways to adapt it, I think that would be very promising. So I actually feel like the ChatGPT revolution that's already happened in text is on its way to computer vision, and all of us feel that excitement. It's not yet there, but it's getting there. So Landing AI, my team, we built a visual prompting system that lets you can actually try this yourself if you go to landing.ai afterward, but have an image, just draw, you know, label a few pixels, that's the visual prompt, and then in seconds, used to take me like 4 hours to train a model, right? But now if you specify a visual prompt, just like ChatGPT responds to you in seconds, you can actually get a response from a visual prompt in maybe 10 seconds or so, and build a computer vision system in just minutes. So, and I think it is actually getting there. It's a very exciting time to be. And I think, and this is actually ready for deployment. With Landing AI, with a bunch of users in manufacturing, in life sciences that are actually using this successfully already today. So I think this is actually ready for prime time.
Thank you very much. Any other additional comments?
Maybe one comment of why this is important as well from an industry standpoint. So you know, if you think about a small factory with one machine or two machines that cannot generate enough data. Today, if we go with the rules-based system to deploy something, we can do that very easily because the rules are not changing, right? But they should also have the ability of, without being able to generate so much data, having that kind of model, right? Likewise, if you think about products that have scratches, let's say electronic, there are different electronic products. As a human being, I can look at a scratch on one and the other and the third, and I can recognize it as a scratch, even if I haven't seen one on this particular variation, right? So these abilities need to be built into the systems going forward in order for us to scale and do meaningful things with it.
Thank you very much.
I would like to second on the Dr. Ying's point that actually learning large foundation models using a lot of data, even from different domains, are extremely helpful for many different downstream tasks. Now we have available to very large data sets, for example, segmenting from Facebook, and many using internet like clips scale data sets. Once we learn really good representation using these methods, we can reduce the data need for the downstream task by an order of magnitude, even more than that. So we have observed that like very few, maybe only hundreds of images are sufficient for a downstream task that we in the past needed closer to 100,000 images. So yeah, particularly with continual learning and over the years collecting data from the target domain, these methods will be more and more powerful.
Thank you very much. I would like to continue to the next topic, the role of unsupervised anomaly detection and its effectiveness compared to supervised detection models for visual inspection problems. Perhaps Professor Colosimo, you can comment on this.
Yes, I mean, I can provide my experience in manufacturing, helping some companies that are building machine tools, and I'm referring to companies that are building additive manufacturing processes. So most of the times they are complex processes. Usually they want to have machines that are intelligent, so they want to have some sort of algorithm that is using the data that they can gain in situ and in line for detecting anomaly in real time. And they come to us and say, please define the algorithm, define the solution. But when you start trying to create defects on purpose, usually they are unrealistic. And so this is why usually we are going with some unsupervised solutions. So it means that we train the model in what is supposed to be an in control state. And so it should react to everything that is out of control in many different directions, because defects can be provided by many different causes, but usually they appear with a, let's say, low frequency in time. So it means that you need to spend a long time in order to define or find some defect. I think that the scenario is changing because of the gap between people that is building the machine and the end user is getting closer, thanks, as I was saying, to the Internet of Things solution. So it means that I can have data of my machine working in any different place in the world. And so I think that we are going in a new direction of some sort of continuous learning. So to take advantage of also the type of defects that I can see in all the plants where my machine is working. And so little by little also improving my algorithm, because usually they tend to create some algorithms that are fixed and stable and close, let's say, with some threshold to be tuned. But I think that the new generation and the new solution are algorithms that are learning, let's say, thanks to the fact that they can take advantage of all the data that they can be taken everywhere in the world.
Thank you very much. Any additional comments? Yes, please. Yes.
Yeah, so I strongly believe in the unsupervised approach. At Apple, we had a project that we finished in 2-3 weeks for just finding unsupervised anomalous parts, and it was done. And we worked for years with Joseph on the glass, and it was very difficult. And the reason the supervised is way more powerful, but you need the humans to annotate. And then also when you deploy it, after 2-3 weeks, someone steps on the cable or the vendor changes a little the light or water is spilled on the machine, and suddenly the algorithm stops working and you have no clue why, because they're really memorizing the examples and they are completely not robust to changes. And that's a major pain. And the other thing is have supervised, you have to annotate one by one, which is really slow. So what we're trying to do with Visual Layer is to group things and cluster things together. So imagine you give the annotator 100 effects that are super similar, and in one click, they say, this is a scratch, and suddenly you don't have to work one by one. So at Apple, maybe we were able to annotate maybe 50 to 100 pieces a day, where you manufacture 2 million a day. So you never can catch up with the amount of data that you need to annotate, and that's a major pain.
Thank you very much. So any additional comments? We can actually extend the session a little bit because this is such a great discussion. So we can maybe take extra time.
I guess maybe just building on that last comment, one other interesting thing beyond of like just grouping them together. So say if you have a scratch or a dent, is actually trying to build up sensitivity in there. So like, hey, if something's really bad, right? How bad is it, right? Because like there's an element of severity of like, hey, yeah, these are grouped correctly, but there's also this element of like, hey, this is really, this is horrible versus this is more of like marginal in the gray zone, and where the overlap is. Because there's also times when, especially when you're in early development of cycles, you don't know where the actual, what is the truth. I see a lot of elements of like, oh, this is my accuracy rate, but that accuracy rate assumes there's a ground truth. a lot of the times in manufacturing, there is no ground truth. And effectively, we're setting the specifications in simultaneously while we're designing the process, while designing the quality systems. And then there's some element of like combination to them. So having that ability to adjust the sliders of like having a sense of right or wrong while you're developing your quality system, improving the quality system while you're improving your process part, they kind of all go together in manufacturing. So that's another element that's also brings this a challenge, especially as like some people brought the Internet of Things. Well, this is like as these are quickly deployed, these are more and more challenges you're probably going to see as you go there.
Thank you very much.
Maybe I'll just
yes,
add one
please.
point to that, and I'll take a slightly different take on it. So even though I would love to have a completely unsupervised system, where I find it challenging in the inspection is that what is a defect is actually a opinion or a specification set by a set of individuals. They define this as a defect, and someone like who is not in that role would look at this and say, yes, I can see this is a defect, but maybe that is acceptable. It is in specification, right? So when we think about anomaly detection approach to that, I feel that it is going to be very difficult to have it completely unsupervised. Maybe a more semi-supervised where you have a human in the loop who is looking at that and is even teaching the algorithm along the way based on the specification of the person who's or the team that is responsible for deciding what is and what is not a defect. So.
Thank you very much. Unless there are additional comments, we can move on to the last topic. So the topic is the commercialization of research, going from research to startups, entrepreneurship, especially in the domain of visual inspection, which requires knowing both the technology and the production environments. We would love to hear suggestions, comments on experiences, and points on avoiding common pitfalls. Perhaps Dr. Cheng can initiate the discussion. Possible.
By no means I'm the person to talk about this. I'm sure there are other people on the panel, other experts or leaders on the panel that can answer this better. But from me personally, I think there are a few basic things to know if you want to commercialize your technology. The first thing, you need to have a business case. Not only your business case, but also you better know your customer's business case as well. But a lot of times they don't want you to know for many reasons. You have to know your technology, how it fits into the production flow, particularly for the object you're dealing with, where the object coming from, and where the object is going into. Knowing that, and then knowing how your technology will make an impact, whether you're making it better. It's hard for machine vision because imaging, I always said, you don't touch the object. You're not changing its shape, you're not changing its mechanical property. So that's a little difficult, but you may be able to help the process, help the other machines. And either by reducing the cost or improve the profitability or anything you can do. Find out, discover the value position and make your business case. The next thing to remember would be you need to convert your technology into a product. What are you selling? Are you selling a service or are you selling something else, or tangible goods, for instance? And are you going to have a business that's project oriented or product oriented? Most research projects are project oriented by definition. It has a life term. You're deeply involved in that, but for product oriented businesses, like Professor Young was saying, he wishes AI can help a lot of the small companies, those small manufacturers to do that. And that will become a product. You are talking about AI product for small businesses, and I'm looking forward to that day because that can help us a lot. So that's a different scenario. You have a different business model to run. And with all that, you would have to have another thing is to have a roadmap to carry this out and make it happen. And that includes pull all the resources together and have a team, and then going forward with that. And the last thing I would like to mention is to be ready to expect the unexpected on the course. Thank you.
Thank you very much. Yes, yes, please.
Yeah, I just add to Professor Chen's last comment, expect the unexpected. So there's one pattern I've seen in different industries in eras of technological disruption. It turns out when the technology is mature, then different teams will deliver maybe similar results. When the technology is mature, kind of the most elite team versus a merely good but not the most elite team, they may deliver similar results. But in eras of technological disruption, I saw this very clearly about 10 years ago when deep learning was advancing rapidly. I see it now again when pre-trained vision transformers and prompting is very disruptive. In moments like these, the best AI team will deliver results that 10 times better than a team that is sort of good but not like fantastic. So I think in eras of technological disruption, sort of all the old rules are being thrown out the window. And then I think because it is now, it feels like we're in a deep tech business, which means that in addition to the business use case and the go-to-market monetization, all that is super important. I think in this era, I think having a really good technology team really helps. So this is why even now I try to read like one research paper a day myself on average to make sure I stay on top of it. And a lot of my team is coming to CVPR because I think vision is now a deep tech business in a way that frankly it wasn't even 3 or 4 years ago.
Thank you very much. Perhaps Dr. Bixon, as an entrepreneur, another not entrepreneur, can also comment on this.
Yeah, sure. So I have some beginner's advice. Yeah, so one thing to know that I learned the hard way, spending a lot of time in China, is that the business definition of what we call the metrics of the precision recall, that you measure your paper on CVPR, are really different. I see Joseph is joking, is laughing. So the thing is, in the factory, they may define the metrics completely unrelated to the machine learning metrics. And you cannot convince them that this is the right way to measure because this is how they measure. And it's often a business problem. So I'll give one example. So we were struggling with, we were fighting with the vendor competing equipment, but the annotators were getting bins that were one all good units and one all bad units. And since they're human, they understood very quickly, this is all bad, and then they say, okay, that's bad, bad, bad. So they had a confirmation bias to always prefer the same, they wouldn't check one by one, they check bin by bin, and suddenly the vendor equipment is amazing, and your algorithm is way less good, and it's more of the human in the loop, and the business, and all kinds of politics behind the scenes is not just the actual metric. Another, so that's one thing. Another thing is that when you look at manufacturing as a simplistic, it's way more complex than you believe. For example, when you have two factories that one manufacture to the other factory as an incoming supply, and they're supposed to be on the same specification, but one factory decides that the lot is super good and sends it to the other downstream factory, and then the downstream factory decides this is not quality enough and returns it to the first factory. So then is what we call supply chain friction. And you think there is no truth because they work by the same spec, but they say it's good and they say another factory say it's not good. And then what you do, so this is like real life problem that I'm sure Joseph struggled with it a lot, and returning shipments. And what do you do? Because there is no, it's everything is suddenly subjective.
Any additional comments? We have last few minutes.
Yeah, maybe just one comment on customization business for companies like the one that we were mentioning, but in other type of processes, we saw a lot of customization. So the user is defining his own product. And so defining what is quality and what is not, it's going to, you cannot learn just by doing because every time it's a new case. So you really need to find a way of redefining what is defective, what is not, and how you can learn what is defective and the right way to produce the part because each part is different from the previous one. So everything is going to be a little bit more complex.
Maybe just going back to the question of advice I would give kind of new entrepreneurs and stuff, really understand what makes you different, right? And so discussions of deep technology, but a lot of people say, hey, I have this great new ML model, it's completely optimized. Oh, and there's another person. Then you have 100 people all saying they're great. How do you understand and do those evaluations, making sure you know what space you're playing in, who those competitors are, and are you adding something unique beyond all those other things are another key aspect that I would just like before you even start trying to go to that next step beyond the idea, try to understand like how differentiated are you? Because like the more differentiated you are, I think the better you'll end up.
Thank you very much. I'm very happy about the discussion, and I would like to thank again on behalf of the organizing committee for taking your time here and contributing to the discussion. And I would like to invite Dr. Manksau for thanking the panelists.
Yeah, we prepared some appreciation certificate. And I do have a spare one for you. I don't have your name. I follow up with you. Yeah, Dr. Shi, Joseph, Professor. Yeah. Yeah, thank you. Still? Yeah, Joe. There's time. Thank you.
It's good.
Thank you.
Thank you all.
Thank you
Thank you for joining us.
Thank you. Thank you for doing
Probably your grandson. He worked with Mark. So well.
Yeah. Just to announce that we have our last session on the data competition presentations that will last around 1 hour 30 minutes. So it will be starting shortly, like in 5 minutes.
Nice to meet you. Did you know Saldar? Oh, Saldar Really? Because he was our customer in the previous factory that was acquired by He was? Yeah. No. When we was at Bosch, we had software fighting. You remember signing for that?
I'm wondering because I signed something.
We started the event together.
Oh yeah,
We
so
worked
I
together
was
until we left for Microsoft.
yeah, so I was in close touch with him. That's a small word.
No, he's a very close friend
So
of mine.
yeah,
Since 15 years.
he was our customer in Turin. We were acquired by us, and Carlos Kessler probably.
Okay, yeah.
Just use
Small world.
Yeah.
Small world.
So which team are you in now? In
Shanghai.
Oh, Shanghai. Wow.
Small.
Yeah. I work with Shanghai on the root cause analysis system that is deployed. Yeah, that's, that was our biggest success in manufacturing.
Okay, I joined just like 15 months ago. So I kind of took over the machine learning team, and maybe before that you were working together.
Yeah, it was.
You're basically like a couple months apart.
Almost over. Yeah, she knows really well how to push things into completion. It's really hard on manufacturing to close the loop and make sure everything's working. And I did see cases where she changed the cosmetic spec if the system was not working good enough. Some little tweaks and suddenly everything's okay. But that's how we should do it. Otherwise, you'll never finish.
I know. You need people like that to really close those things.
Right.
So she's really good at that.
Okay. Very cool. Yeah.
So you guys work together?
Yeah.
Yeah, we worked a lot.
That's why Danny left.
Yeah.
He worked for,
No,
he was working
actually,
with me. He was
no.
pulling out all
Actually,
his
I
hair.
tried to convince him to move my team to his team, but it was too complicated in Apple.
Oh, okay.
Yeah.
Okay. Wow. This is really amazing.
Thank you.
Thank you very much.
Thanks for organizing, for helping us.
Thanks for the invitation. I'm too low level.
So everyone, let's take a break for 10 minutes and start at 4:15. Short break for 10 minutes, coffee break.
Yeah. No, actually, we work together, and essentially it's amazing. Amazing work. Yeah. I'm surprised to be invited. I was kind of invited last week. It's really glad to be. We also worked together. And yes, it's going pretty well. We have I'll show you a 30-second demo of what we're doing. First cloud product. It's based on our open source product. We got so it's becoming very popular. Low-level tasks, gory tasks, we don't want to do like billion-level rates and duplicate from the power side. If you have 30 seconds, that's fine. The one that you have on the right, that one. Maybe you can show. Yeah, I can show you 30 seconds. Yeah, because okay, yes, sessions to go there. Have a lot of experience. I have the experience just the same thing during industrial applications. We have faced some situations, for example, a good large program is tested to be achieving like 80 accuracy in the math for doing work. But if we apply to industrial applications, the single time just a large gap. Given the situation that every industrial image is severely protected. Yes, but it is not easily accessible. So you're collaborating with Right.
Yeah, I think it's some. It's hard.
Yes. The whole system resolve issues. But I wonder, is it just so many people have so many servers? Yeah, sure. Yeah, I think very interesting data science okay, sure. Yeah, I sent the email. Okay, thank you. Yeah. See you next time. Maybe something about the contribution. Conference, like $500, my first person, and then you get lots of good algorithms. It has been much better than the enrollment here. Other than everyone. So all the manufacturing process is problem need to be addressed.
Yeah, with Samsung for 6 years, every year, so they send 1 year. Basically stays.
Okay, so I think we can, let's start the data competition presentation. So okay, so we now move into our last session of the workshop, which is the data competition presentations. And this competition comprises of 2 tracks, and each track has 4 presentations with 10 minutes each. Let me first invite Shanchung and Felix to talk about the data sets and competition, and who will also announce the awards, and then we'll ask the presenters to discuss their submissions. Yeah, Shanchung? We cannot hear you.
Hello?
Yeah, I can hear you now. Yeah, go ahead.
All right, hello everyone. I'm Felix, and here is Shensu. We're a part of the organizing team for the Vision Challenge. And throughout the course of this workshop, we have witnessed exciting paper presentations, inspiring keynote talks, also as well as the thought-provoking panel discussion from the industrial and academic experts, shedding light to the forefront of production and research in the field of vision-based introductions. So here I will, as Arsalan introduced, I will briefly introduce the vision datasets and challenges to lay out the stages for the challenge winners. So as one of the conclusion from our panel discussion has revealed, the heterogeneity of data and production needs in the manufacturing domain have proven to be one of the major challenges preventing the scaling of machine learning solutions. While previous data sets in the domain, such as MVTech and BINTech, has led to a great surge of research outcomes in unsupervised anomaly detection, the value of supervision and human guidance is still valuable in the reality of production. And our hope is to provide the dataset foundation to further push the performance and reliability of machine learning solutions, given such considerations. To achieve this goal, we built the largest vision-based industrial inspection datasets with high-quality instance-level defect segmentation annotation. The vision dataset is a collection of 14 industrial inspection datasets sourced from RoboFlow, designed to explore the unique and heterogeneous nature of vision-based industrial inspection problems. These datasets cover a wide range of manufacturing processes, materials, and industries. And the dataset have a total of 18K images to support. And to support the challenges, we leverage an annotation team with extensive prior experience in producing high quality annotations for manufacturing related datasets. The annotation effort spent a total of 30 to 100 working hours. And for the competitions, we provide 10K high quality instance level defect segmentation annotations and 4K images spanning 44 defect types. And to keep it short, I'll leave more details to our report, which will be available at the QR code on this slide. And based on the datasets, we host 2 challenge tracks. Each, as Arsalan mentioned, each track is designed to address the challenges in industrial inspection domain from a unique angle. Track 1 takes a model-centric approach, while track 2 adopts a data-centric perspective. So track 1 combines all 14 datasets to mainly assess the data efficiency of machine learning algorithms. And this came from the realization that real-world manufacturing processes often comes with many data and annotation constraints. So this track is specifically designed to review such challenges. And the reason why we incorporate so many different type of products is also to reveal another layer of challenge, which is, as we mentioned in the panel discussion, the heterogeneity in manufacturing domain. So the participants are encouraged to come up with solutions that can effectively tackle such heterogeneity. So in the end, Track 1 receives participation from 46 registered teams representing over 12 companies and 20 universities. And in the second challenge track, our focus shifts from data efficient defect detection to data generation for defect detection. So this stems from the consideration where real-world manufacturing can often face the restriction where there will be an extreme imbalance between normal and defective samples in the data because defects by their nature are anomalies and can often do not occur as frequently as normal instances in high-stake manufacturing. And furthermore, we can also encounter imbalance in the distribution of different defect types. And the long-tail defects can, although occurring infrequently, they can also be of great importance for downstream production. So following the data-centric AI approach pioneered by Dr. Andrew Ng, which was just there in our panel discussion, the Track 2 competition is provided with a fixed model and an initial data set. And the focus is on the data itself, and participants are encouraged to apply data cleaning and augmentation techniques to enhance the existing data. And at the same time, also free to generate synthetic data to further enrich the provided data. And next, without further delay, we'll be hearing a series of talks from the competition winners, sharing their solution to the respective challenge tracks. And I'm honored to introduce my fellow challenge organizer, Shansong from Georgia Tech, to the honor and announce the winners.
Thanks, Felix. Hello, everyone. I'm Shansong. It's my honor to introduce the winners for both tracks. So the winner for track 1 is, so the first prize goes to the Last Ink team, and the second prize goes to the AOI overfitting team, and the third prize goes to the MicroEye team, and the most innovative solution goes to iEvasion and SYSU team. So congratulations to those winning teams. And for track 2, the winners are, the first prize is the LeadTech Sichuan University team, and the second prize is the Dinner team. The third prize is the Focusite Tech team, and the most innovative solution is CAS team. So congratulations. And next we will have their presentations, but before that, I would like to express our thanks to all the organizers who helped a lot to make this data challenge, and thank you all. So thanks.
Okay, so we will have our first presentation from Luster Inc. team. Do we have anyone from Luster Inc. on the call? Felix or Shanchung, can you confirm if they are on the call? If not, then I'll start their video recorded.
So seems no. Please start the video.
Okay.
Hello, I am Pengcheng Gao from the Institute of Intellectual Rationality of Luster Light Technology Company. It's my honor to present our team's solution ensemble learning of multiple pre-trained models for data-efficient defect detection, which is proposed for the Track 1 Data-Efficient Defect Detection Challenge of the first workshop on Vision-Based Industrial Inspection Challenge in CVPR 2023. The goal of data-efficient defect detection is the accurate detection and segmentation of defects in industrial images by training the model with only a small amount of annotated data. We treat this as an instance segmentation problem with both defect localization and mass prediction, and the detection and segmentation tasks are mutually reinforcing. The main challenges of this competition include the limited amount of annotated data, with only a few dozen training images per dataset. And defects are small, shallow, and weak, which makes them difficult to detect. Next, I will describe the solution our team developed to meet this challenge. We analyzed the on a number of dimensions, including data and models. To address the difficulty of limited annotation data, we used a hybrid dataset training approach to enrich the distribution of training data and selected pre-trained model fine-tuning paradigm for prediction. To address the problem of small, weak, and shallow defects, we selected multiple heterogeneous model ensemble learning. We trained the CNN architecture model and the transformer architecture instance segmentation model in parallel to take advantage of the different architectural models and use tricks to fuse the results of the different models. Below is a detailed description of each technical point in turn. Hybrid dataset training means that all datasets are fed into the same model for training purposes. As the table illustrates, this competition provided 14 datasets containing dozens of defects. However, there were only a few dozen annotated images for each defect type. As shown in the figure on the right, we visualized and analyzed all the data and found significant differences between defects. And we also experimentally verified that there was no risk of category confusion when using hybrid dataset training. Meanwhile, hybrid dataset training can greatly enrich the training data, and other types of defects can be considered as background classes for the current defect, improving the accuracy of defect detection. The pre-training fine-tuning paradigm has been widely used in deep learning research. Pre-trained models obtained on large datasets have strong generalization capabilities, which help the models converge quickly on downstream task datasets, and also avoid overfitting when trained on small datasets. Pre-trained models commonly used for instance segmentation tasks are obtained on the COCO dataset. As shown in the figure on the left, the COCO dataset is a large multitask dataset that can be used for image recognition, semantic segmentation, and so on. It has over 330K images with 1.5 million targets and 80 target classes. We select the pre-trained models based on the public evaluation results on the COCO test dev dataset. We design and propose a heterogeneous model ensemble learning framework to address the challenge of shallow and weak defects. The current instance segmentation models with state-of-the-art performance can be divided into two categories. One is the model based on CNN architecture, which is an improvement of the classical mask RCNN model, such as Cascade Mask RCNN. The other is the model completely based on transformer architecture, and the representative methods are DETR and MaskDino. Due to the different architectures, these two models have different advantages in prediction results. Cascade Mask RCNN has a lower false detection rate, while the MaskDino has a higher segmentation accuracy. Therefore, we choose multiple models for ensemble learning to complement each other's strengths and thus improve the final prediction accuracy. Specifically, our model consists of two branches, a Cascade Mask RCNN model and a MaskDino model. For the classical Cascade Mask RCNN method, we choose the EVA model as its backbone. EVA is a large-scale visual backbone model obtained by self-supervised pre-training based on clipped features with a 1.3B parametric number and powerful bottom-level visual feature extraction capability. MaskDino is a transformer-based encoder-decoder model with features such as anchor-free and NMS-free. It has a larger feature perception field and higher segmentation accuracies. Both models provide pre-trained models on the COCO dataset and are highly ranked in the COCO Test Dev leaderboard. In addition, we use stacking ensemble learning, dataset-aware checkpoint, and improved loss functions for segmentation in heterogeneous model integration learning. Specifically, we train the models of both branches in parallel and finally fuse the results of both. In the meantime, the speed of convergence varies depending on defect difficulty, so the model with the highest accuracy for each dataset is stored. The evaluation metrics of the competition are only related to the prediction mask of the segmentation task, so we focus on the accuracy of the mask prediction. The standard segmentation loss function is the CE loss, which does not converge properly on unbalanced data. In industrial defect detection, there is an extreme imbalance in the distribution of defects and background. Where the vast majority of an image is the background and only small areas are the defects to be detected. To solve the phenomenon of category imbalance, we introduce another loss in image segmentation, dice loss. Dice loss is a kind of region-dependent loss, where the loss and gradient value of a pixel point are related not only to the label and predicted value of that point, but also to the label and predicted value of other pixels. The weighted dice loss is designed to compute the loss for the foreground category only. The final defect mask prediction loss function used in our submission is a joint loss function of CE and weighted dice loss. In the final result fusion part, we use some tricks to improve the prediction accuracy, mainly including two strategies of ROI filtering and score correction. We count the ROIs where each defect appeared based on the labeled images for each dataset. Only the predictions that appeared in the ROIs are reported. In addition, we statistically calculate the area and digital number for each type of defect. The prediction results are weighted according to the area and the digital number of the corresponding defect category. And the prediction score of the defect is corrected. The higher the digital number and the larger the area, the higher the corrected prediction scores would be. Finally, the 100 highest scoring predictions are reported for each image. With the combination of the above technical points, the final submission of our method ranked first on the leaderboard, achieving 50.2% average mean average precision and 68.7% average mean average recall over all 14 test datasets. The table on the left shows the final results of the competition and some intermediate results of our approach, while the image on the right shows two examples of the prediction results of our method. By ensembling MaskDino and EVA and using ROI filtering and score correction post-processing strategies, the accuracy of the prediction mask has been effectively improved to accurately detect many types of defects. Thanks for listening.
Okay, so next, your next presentation is from AOI overfitting team solution. Do we have someone from that team on the call?
Yes. Yes.
Okay,
Can
that's
you hear
great.
me? Okay.
Yeah, I can hear you. So I'll stop sharing the screen. Then you can share your screen and start
Okay.
the presentation. Yeah, I can see your screen. You can yeah, go ahead.
Okay. Okay. Hello, everyone. Good afternoon. I'm Tao Xian from the CASVision. It's a great pleasure for me to have the opportunity to participate in the track 1 of the CVPR 2023 Vision Data Challenge. I'm honored that our team has won the second place. Next, on the behalf of our team, I will give a detailed introduction to our solution. Our team have 9 members, many from the CASVision and the Institute of Automation Chinese Academy of Science. CASVision is a company specialized in the AOI defect detection, while the Institute of the Automation Chinese Academy of Science is a leading research institute in the field of the artificial intelligence. The outline is divided into 5 parts. So the first part is introduction. The defect detection or the defect inspection is an important link in ensure the product quality. With the defect of the vision and artificial intelligence, more and more manual inspectors are being replaced by the machine vision. When the deep learning is applied to the defect detection, it requires the sufficiency and balanced defect data set. But in the action situation on the production line, maybe we cannot provide enough defects, and the defects is also random. So it is very meaningful for our computation focus on the data efficiency defect detection. And first, a challenge of this computation is that there are too few training data sets. The left finger shows that the distribution of the training and validation and the text data set. And maybe some data sets of the text site have even more than 30 times larger than their training site, such as the console. And some data sets maybe have no more than 40 training samples, some such as the capacity. And another challenge is that the image in different data sets are not the same size. We list 5 data sets as an example. We can say that the size of the electronics data set can range from the 400 to the 2000. Maybe so we need to same network to take into account the defect, which propose a greater challenge to the network training. And the last is the computation include 40 different data sets. And the overall computation time is about 1 month. So it is not practical to set the different training pipeline or fine tune each data set. So it's difficult to design a unified pipeline to propose the 40 different data sets is a challenge. To address the problem, we can show our many solutions. The first is that we focus on the limited training sample. We're using the transfer learning based pre-training models. And the second is that we handle the different problem and the different size. So we're using the multi-scale training and the taxing. And the third is to tax the program of the poor segmentation performance of the single model. So we're using the model of the embedding multi-models. The second part is the pipeline of our solution. Okay, our 4 solution is divided into the 3 stages. For the first one, the tax is the instance segmentation. So we're using the hybrid text cascade structure as the base model. And in the second stage, we integrated the result of the semantic segmentation into the instant segmentation to further improve the processing. In the third stage, we're fusing the result of the multi-instant segmentation models to improve the recall. And the next, I will give the detail of all the each key points. So the first one, the key points is that we're using the hybrid text cascade structure. So it is a classical object detection model, which can achieve the high precision detection. So in our text, we're using it to perform the image segmentation and achieve the good result. And our backbone, we adopt the CB lights. So it's using the multi backbones for the feature extraction and fusing in a cascade method. So in our method, we can using the swim transformer as the backbone. And the second point is that we integrated the result of the semantic segmentation into the instant segmentation. And the semantic segmentation model will adopt the mask to formal. So we can use this method to improve our more accuracy segmentation result and increase the precision. The third key point is that we're fusing the result of the multiply instant segmentations to further improve the recall. So we have the three models. One is the first is HTC, and the second is the cascade masked RCN with the backbone of the ResNet 50s. And the third is the cascade masked ANS with the backbone of the Convex, which is also a big convolution neural network backbone. And in this way, we can increase the recall. So we also show some the training details, such as we're using the pre-trained swim transformer based models and multi-scale training strategies to improve the model against the different object size. So we also adopt some tricks like the soft NMS and the multi-scale texting, also known as the TTA, and to further improve the segmentation result. Okay, the next is the result, and we can got some conclusion. Is that the first is the compare of the different instant segmentation models. The large the backbone and the better the performance. And the second is HTC is superland the cascade RCN, and the third is the different data site has different in their performance. So we can get that the defect on the PCB1 and the PCB2 are relatively simpler because they have the uniform image size and uniform defect scale and types. So maybe we can choose the best performance on the data side. And the second is that the model ensemble result. The first is fusing the semantic segmentation result can increase the precision, and fusing the different instant segmentation result can increase the recall. Okay, we also we have also open source the main train code, and the whole framework is based on the MM detection platform. The next part is the protection improvement. So the first one is that we also in the semi sequence-wise the learning, and we also want to using the enable data site, and we also using the soft teacher, but found that maybe it's a single pipeline work on the one data site, but it's difficult to achieve the good result on other data site. But we also think it's a good direction. The second one is that the segmentation harnessing model with the population of the ChatGPT, the foundation model has arrived. So the SAM model released by the mentor company has give a change to the segmentation method. Although the model was released in the April, so we can also use in the computation according to the rules. But we try it on an image from the lens data site on the left. So you can see that the SAM has a strong zero-shot detection capability. So we think it is a good direction for the defect detection. And I think we can maybe in the future, a lot of the method based on the foundation model can use to dissolve or solve the defect inspection or the defect detection problems. Okay, thank you. This is my presentation. I'm Tao Xian. Yeah. Okay. Okay.
So we will have a Q&A session after all the presentations from track 1. So I think we can just hold our questions for now. Okay, so the third presentation is from Micro I team. Anyone from Micro I team on the call?
Hello, yes.
Okay, so can you please share the screen and
Sure, one moment.
okay, yeah, go ahead.
So, we'll try it, okay. Dear audience, ladies and gentlemen, my name is Huang Zhengling. On behalf of our team, I would like to thank the CVPR 2023 and the organizers to offer this opportunity to present our experimental work. So before I start this presentation, please allow me to introduce my team, Micro I. Micro is a team with 3 members. Mr. Zhe Wang is a senior AI engineer, and Dr. Jimmy Chen runs the entire department of AI algorithms. And I lead the research team on this department. Now let's go to the presentation. As the competition data set was released,
we cannot hear you. Can you?
Categories from 14 industry products with different kinds of material.
What's his name?
Manufacturing processes. As the organizer at the very beginning already produced.
Sorry, we cannot hear you. Can you come closer to the mic?
Another way.
Because
do you hear?
No, we cannot hear you. Can you get closer to the mic?
Just in this competition. Problem 1, future learning. Nearly 880 images. Approximately 5%
What was his
of the
name?
image data is divided for training. And problem 2, the distribution of the
You are the host. Can you maybe like maybe stop the presentation or
the distribution of the defect size shows that the circa 62% of the defects. Hello?
Yeah, we cannot hear you.
Okay.
So.
Okay, I will continue.
No.
Good. Okay.
So don't continue because we cannot hear you.
I was just mentioning the second problem. I said the distribution of data size shows that 62% of the defects have size smaller than 32 times 32. And the last problem is imbalance of defect categories. The statistic result on the right side of the slide.
That's the beauty of more 20% presentations.
Problems. And we propose the firstly the CB2 as a detector and the 3T. Well, I'm so I'm muted sometimes by the moderator.
Yeah. So can you hear me? Because we cannot hear you clearly.
Okay, it works.
So
weird.
Yeah, he's sharing the screen. So we cannot hear you clearly. So I think we need to
just one moment. What is content? Just 1 moment.
So yeah, I just want to. He's starting to share the screen again. So your presentation is fine, but your voice is not clear. Can you speak again?
Sure. Can you hear me now? I think it's much better.
No, I think it's still not better. So what I am going to do is I'm just play the recorded video you had.
It's okay. As long as we already prepare a video, so it's okay.
Yeah. So I think that would be better.
Okay.
Dear audience, ladies and gentlemen, my name is Fang Zhenlin. I'm an AI engineer from the company Microintelligence. On behalf of our team, I would like to thank CVPR 2023 for offering this opportunity to present our experimental work. So before I start this presentation, please allow me to introduce my team, MicroEye. MicroEye is a team with 3 members. Mr. Zhe Wang is a senior AI engineer. Dr. Jin Qian runs the entire department of AI algorithm development. And I lead the research team on this department. So now let's go to the presentation. As the competition data set was released, we analyzed the given data. The data contains 44 defect categories from 14 industrial products with different kinds of material and manufacturing processes. The dataset also states 3 problems we should address in this competition. Problem 1, viewer should learn. More than 880 images, approximately 5% of the given data is divided for training. Problem 2, the distribution of defect size shows that circa 62% of the defects have a pixel size smaller than 32 times 32. The last problem lays on imbalance of defect categories, as the statistical result on the right side of the slide indicate. Now, in order to solve these problems, we proposed firstly CVNet V2 as the detector and the swing transformer as the backbone. The CVNet architecture connects multiple identical backbone networks through composite connections. It integrates high-level and low-level features from these backbone networks and gradually expands the receptive field to perform objective detection more efficiently. This design allows for the extraction of richer detail features and exhibits strong generalization capabilities and accuracy performance. Swing transformers is an excellent universal backbone network for computer vision tasks. The model adopts a hierarchical architecture and incorporates shifted windows and cross-window connections. It's enabled swing transformer to model visual information at different scales and making linear computational complexity. Therefore, swing transformer is suitable for various visual tasks and performs outstanding across multiple tasks. By scaling the depth of the network proportionally, the model can be configured with small base and large structures of different sizes. As this slide denotes swing B, swing S, swing B, and swing L. They provide the flexibility to handle tasks of varying difficulty. The other proposed solution is Cascade as a detector and ResNet 50 and or swing S as a feature extractor respectively. Cascade is an extension of the popular object detection framework FastRCN. It aims to improve the accuracy of object detection by using a cascade of multiple stages of detectors. Each stage in the cascade gradually filters out false positives and focuses on detecting objects more accurately. As long as the model solutions are determined, we also utilize several strategies for data augmentation. The principle of random center crop path is a random location of limited center range. Then corrupt data area is determined and padded to the input corrupt image size. Mosaic data augmentation is a technique of combining 4 images by randomly erasing, co-grouping, and arranging them. Its advantage lies in enriching the diversity of backgrounds and the small objects in object detection. The random erasing method randomly selects a rectangular area in the original image and replaces the pixels in that area with random or fixed values. During this process, the images involved in chaining are partially altered to reduce the risk of overfitting and improve the robustness of the model. Random erasing is independent of the parameter learning process and can therefore be integrated into any deep learning-based object detection model. Focusing on detecting small-sized defects, RFLA is merged in our model solutions. RFLA is a label assignment strategy based on Gaussian receptive fields. This method utilizes the prior information that the feature receptive field follows a Gaussian distribution. It measures the similarity between Gaussian receptive field and the ground truth. Use a receptive field distance, RFD, and adopts a hierarchical label assignment, HLA strategy based on RFD for balanced learning of tiny objects. It aims to improve the detection accuracy for tiny objects. Assembly learning is also applied to strengthen the detection capability of our model proposals. As shown in equation 1, we use the mask voting to enhance the MAP metric for high scoring segments and employ soft NMS to improve the MAR metric for low scoring results. Equation 2 describes the process of mask voting, where the average of masks is calculated, using a threshold of 1.5 to obtain the final production result. When we executed experiments, different crop size of image for training were considered simultaneously. Each center crop shape corresponds to 5 resized shapes. Different combination possibilities are investigated in our experiments. So totally 5 methods are assembled as our entire solution to the competition, and the ablation study result also suggests us the best options in each method. So as we see here in table 1, swing transformer plus the CVNet V2 shows a better performance, definitely. And the table 2 shows the last 2 crop options improve detection results more significantly. And when we use RLFA to do the object detection for tiny objects, then we will say that the RLFA does work in this task. And also the selected data augmentation strategies in table 4 also show these strategies are pretty necessary. And especially in ensemble learning, swing S, swing B, and swing L are adopted. The last 2 crop options, namely 10 different combinations of crop and resize shapes, are utilized. Hence, there should be 30 models, maximum for the ensemble learning. Table 5 indicates that the best performance comes from the combination of 28 models and masks voting tool. As this slide demonstrates, various defects are well detected regardless of sizes, materials, and manufacturing processes. But as a matter of fact, we have attempted more data augmentation strategies. The strategies listed here are not recommended in defect detection task for the given data set. Of course, we would like to develop a one-stage detector as a more convenient solution in the future. And if we think the test data can be well leveraged, the result of defect detection could be much better. And so that's what we have done during this competition. We appreciate your attention. Many thanks.
Okay, so next presentation is from IE Vision and CysU team. Is someone on the call?
Yes, sir. Can you hear me?
Yeah, we can hear you. So can you
So,
share the screen and present?
so you just play the video I upload. Thank you.
Okay.
Ladies and gentlemen, good afternoon. It's my pleasure to have the opportunity to present our latest job about workshop on vision-based industrial inspection to you today. First, let's take a look at the results. We participated in the challenge 1, data efficient defect detection, and were awarded the most innovative award. We achieved 6th place on the leaderboard with MAP and Meyer scores of 0.396 and 0.593 respectively, and the final score of 0.494. In the following sections, we will provide a detailed introduction to the challenges we faced and the method we proposed. The experimental results will be presented along with the methods. Regarding the issues we encounter, they can be classified into the following categories. The first one, unbalanced labeled and unlabeled data. Each data set is provided with a limited set of training and validation data, as well as more unlabeled data for representation learning and testing purposes. Secondly, variability in products with 14 different products. Then variability in lighting affect the quality of images captured. And the variability in defects and anomalies cause distortion and blurring in the images, making it difficult to identify defects accurately. Last, background distractions. Presence of background noise, such as markings, texture on material, moving parts, or dust particles, can also interfere with the interpretation of images. To overcome these challenges, we developed a hybrid approach, which combines expertise, previous knowledge, and neural network techniques. We will describe them in more details in the next section. To address the challenge from unbalanced distribution of data, we provided the detection results by efficient teacher as supplementary pseudo-labels for self-teacher learning. We made a slight adjustment to the hyperparameters, combining defect detection tasks and the cascade structure of the HTC network. The teacher's output utilized the last bounding box output, and 3 bounding box heads were trained separately for the pseudo-labels. We only selected efficient teacher YOLO outputs with the scores higher than 0.5 for training, and outputs of lower confidence had a lot of noise. To address the issue of variability in products, we applied the YOLO series, Solo 2, Mask Gaussian, Mask to Former, Haber Tusker Cascade, and other algorithms on each product dataset. Subsequently, a winner-take-all mechanism was employed to select one or more algorithms that were most suitable for the specific product dataset, and their detection results were adopted as candidates for the final result. To address the issue of variability in lighting conditions and reflections, We employed the traditional image processing and data pre-processing techniques such as histogram equalization, gray level transformation, image filtering, image enhancement, and so on. We performed data processing and transformation of both labeled and unlabeled data to achieve better model learning and training performance, thereby improving detection performance. To tackle the problem of variability in defects and anomalies, we use data augmentation techniques, including geometric transformations, scale transformations, color space conversions, grayscale transformations, image enhancements, image cropping, image blending, and many other data augmentation methods. We did not only apply data augmentation techniques when preparing data for mode training, but also during testing and inference stages of the mode. We did not only augment the already labeled data, we also transferred defects from the labeled data to some unlabeled data for augmentation using specific techniques. We did not only perform data augmentation for just once, but rather conducted secondary or even multiple rounds of augmentation on the augmented data when necessary. This table shows comparisons of performance between the max-to-former algorithm and max-to-former with augmented training data. We can see that for most of them, data augmentation technique can improve the detection performance. There is an uneven distribution among the categories of samples in terms of quantity. The area of defects is often much smaller than the background area relative to the entire image. To improve this problem, this section applies InspectiON on the top of data augmentation method used in the previous sections to further augment the numbers of defects, thus balancing the differences in the quality distribution between categories and increasing the diversity of defects, ultimately improving the mode's ability to detect defects. This table lists part of data augmentation methods used for each dataset. You can check all the methods from the technical report if you need. To tackle the problem of background distractions, we introduced two new methods. Firstly, we used the InspectiON image augmentation technology based on local texture features to transfer defects characteristics from labeled data to unlabeled data with similar local background texture features. Secondly, we implemented test-time augmentation (TTA) technology to carry out multiple data augmentations during model inference and detection. We employed an ensemble method for multiple mode output and applied soft NMS on the individual image and the category outputs of our modes. However, we observed that the average classification confidence of the mode with superior performance on the evaluation set was lower than the mode with poor performance, which would surprise the results of good mode in the process of soft NMS, has consequently reduced the performance of mode integrated. To address this issue, we adopted a soft version of the winner-take-all strategy and used the highest performing mode as the main mode. We are grateful to the organizers of this event for giving us the opportunity to share our achievements. Although there are still many imperfect aspects in our work, we will continue to strive for improvement in the future. Unfortunately, due to visa-related issues, I am unable to attend the event in person. However, I'd like to extend my best wishes for successful and fitting conclusion to the proceedings. Once again, we would like to express our gratitude for your active listening. Thank you.
So that was the last presentation of track one. I would like to pause here if there are any questions on the data efficient defect detection. If anyone has any question for any of the presentations we had so far. If not, then let's move to the track two. So track two is about data generation for defect detection. And the first presentation is from lead tech SCU data generation team. Is someone on the call from lead tech team?
Yes.
Do you want to present or we would like to
can
meet
we
you?
just play the video for the
speaker?
It's having a terminal examination.
Okay, sure. I can play the video now.
Hi, I'm Ming-Tao Guo, presenting GAN and diffusion model data sample for defect generation at the first vision challenge. This is done by Zhao Jie, Ming-Tao, Guanyu, Zheng Jia, and Yan Li. First of all, let's introduce the data set for the competition. The training set consists of a total of 2,226 images. Among them, there are 341 annotated defect areas, 52 collisions, 43 instances of dirtiness, 194 gaps, and 54 scratches. Our approach utilizes two generative models, StyleGAN and Stable Diffusion. Let's discuss their pros and cons. StyleGAN can generate realistic visual images with high resolution, but it struggles with diverse and rich data sets like ImageNet. In contrast, the Stable Diffusion model is excellent at generating diverse results. However, generating high-fidelity images with this model requires additional post-processing techniques such as super resolution. To improve the diversity and fidelity of the synthesized defects, we modify both generative models. The StyleGAN-based model is transformed into a defect generation model, guided by defect shapes and positions, namely defect GAN. Similarly, we make modifications to the Stable Diffusion-based model using ControlNet, creating a model called Defect ControlNet. Due to the limited quantity of defects, we initially pre-trained two models using the ImageNet and the line datasets. Subsequently, we fine-tuned these two models using the defect dataset and merged the generated data from both models after fine-tuning. This is the network architecture diagram of the defect GAN model. The green area represents the StyleGAN, which is initialized with weights pre-trained on ImageNet. Additionally, we have added two encoders on top of the StyleGAN, namely the appearance and structure encoder. The structure encoder takes as input an edge map that contains the structure information of both the image background and the defects. During testing, we only need to place the defect structure in the background structure image according to certain rules to generate defects in different positions. However, this approach has a drawback. It does not guarantee the preservation of background color, texture, and lighting. To address this, we have added an additional appearance encoder to extract background information. Then we incorporate this information into the model through modulation and demodulation of features in StyleGAN. And for the loss functions used in training defect GAN, we primarily employ the conventional adversarial loss and L1 loss for supervision. Our defect control net is a modification based on Stable Diffusion. In order to enhance the model's generalization and diversity in generating defect data, We first trained the stable diffusion model using line type 2 image datasets. After training, we fixed the width of stable diffusion and focused on training an additional control net on top of it. Additionally, to provide background information, we input the background image and the texture description of defects into the conditional input module of stable diffusion. Both defect GAN and control net rely on paired images for training. This means we need an image without defects and a corresponding mask indicating the shape and location of the defects. The ground truth should be an image with defects that match the mask. However, obtaining such paired datasets in reality is a challenge. To overcome this issue, we employ an image impacting model called Llama. By using the annotated defect mask, Llama restores the background in the defect region. This repaired image is then used as input, while the original defective image serves as the ground truth for training defect GAN and control net in an end-to-end manner. After training, we perform separate tests on defect GAN and control net. The figure illustrates the results of defect GAN synthesizing 3 different defect types. The input depicts a defect-free background image, while the mask indicates the defect's shape and location. Both are inputted into the defect GAN model, and the output represents the synthesized result. The model generates plausible defects at the specified locations indicated by the mask. For more specific gap-type defects, we utilize traditional image augmentation methods instead of direct synthesis using the model. Further explanation on this will be provided in the subsequent discussion. Similar to defect GAN, we also utilize defect control net to synthesize 3 different types of defects. As shown in the figure, it can be observed that the defects synthesized by control net have significant visual differences compared to those synthesized by the defect GAN model. In ablation experiments, firstly, we explore the impact of generating data for individual defect classes on the MAP of the validation set. Each defect type is individually synthesized with 600 images, resulting in improvements on the validation set compared to the baseline. With a total of 2,400 synthesized images added to the training, the MAP increased to 0.245. It is worth mentioning that the gap defect is quite spatial, and it is difficult to generate direct using the generative model. Therefore, we only use traditional image augmentation method for the gap defect. As shown in the figure on the right, we reflective padding the original image to enhance the diversity of the data set. As shown in the figure, it displays the distribution of bounding box width and heat for the 4 types of defect shapes in the training set. From the figure, we can see that the gap defects have a distinct distribution pattern, where the heat is much smaller than the width for most of gap defect data. Therefore, we cannot apply simple data augmentation techniques, such as rotation, to this type of defect, as it may result in a significant gap between the gap defect distribution and the original data, leading to performance degradation. Therefore, we ignore gap defects in rotation and instead use reflective padding. In addition to the data synthesized by the generative models, we also test traditional image augmentation methods on the validation set. The augmentation methods mainly include rotation and reflective padding. As shown in the figure, the data augmentation methods of reflective padding and rotation are illustrated. The table shows the gain in MAP for these 2 augmentation methods on the validation set. It can be observed that by incorporating rotation and reflective padding into the synthesized data, the MAP increased to 0.267. As shown in the first table, we first merged the training and validation sets and synthesized 600 images for each of the 4 defect types using the defect GAN model. For the gap defect, reflective padding is used as an augmentation method. The MAP on the test set is 0.241. Then we further increase the number of images by applying 100 rotations to each defect type, which increase the MAP to 0.252. Finally, we apply 300 reflective padding to each defect type, which further increase the MAP to 0.264. Finally, we merge the best data generated by defect gain and control nets respectively, and find that the performance on the test set is significantly better than the two independent data sets as shown in the table. Ultimately, the MAP on the test set reached 0.293, and we rank first on the leaderboard. Thanks for your watching.
Okay, so next presentation is from team Dinar, and I think we can start.
Hello everyone, welcome to my presentation on version 23 challenge track 2. It's about data generation for defect detection. This is our contents. First of all, we achieved the second place on the leaderboard, and it indicates our method is very effective. First is the overview of today's presentation. I will introduce some basic information for you to understand track 2. And then we come up with a new framework from past few years industrial experience to do some data augmentation, data generation, and data selection. It is not only useful for the competition, but also useful in our industrial project. Let's have a quick overview. First of all, it's an instant segmentation task. Training phase is fixed, and we cannot change any detail of the training process. For example, training iteration is fixed in 12,000. It is very important for our task. We use some strategies to select more representative samples for training. Bad samples with low representative run auto training opportunities and cause bad performance at last. We use the masked RCN as our backbone. Our dataset consists of 4,500 samples, including 2,200 for training, 2,200 for validation, and 8,000 for testing. There are 4 different defect classes, including scratch, collision, dirty, and gap. There are some challenges for us to solve this problem, such as unbalanced distribution of defect samples, lack of defect diversity, lack of strategies for data selection. For example, we have 400 gap defects, and it is very easy to identify. And we only have 2 spatial collision samples on the product boundary. Defects with same classes will have completely different shapes, which causes long-tail distribution problems. Let's begin to focus on our brand new framework. It consists of 3 modules: data augmentation module, data generation module, and data selection module. You can easily understand each part by its name. Data augmentation module uses several data augmentation to provide more defect samples into the sample pool. You can see the sample pool here. We merge original data, augmentation data, and the generated data into the sample pool and select samples with Bayesian optimization. In our experiment, we use 4,000 samples as our training set, achieve lower performance, but select 700 samples, representative samples. From 4,000 samples, we'll have a higher score. Then we use the model to predict all train and validation image and find out escape and overkill samples. We then focus on the escape and overkill samples, and we use 4 different data generation methods to provide more effect samples. Guide diffusion and repent are very widely used for data generation tasks. Both of them are open source on GitHub. We fine-tune the code and upload by email. Scribble label is our easy and effective method to reduce overkill, which increases about 5% MAP score. We will explain it in the next part. And then through the generation module, we get more defect samples into the sample pool, and we repeat the operation circle 5 times and achieve final results. Here are some examples of different augmentation methods, such as rotate, random shift, copy paste, and mosaic. We find out analyze plays an important role in this task. We analyze the product result of the model compared with the ground truth and classify them into red, escape, and overkill. Blue boxes represent escape and the red boxes represent overkill. Green boxes represent red for sure. We visualize the predicted result 400 times. In this part, I will show you how we solve overkill problems. In first picture, you can see the region is easy to cause overkill problem. Whenever you repeat the picture 400 times for training, region proposal network, also called RPN, still recognize it as dirty defect. To explain this situation, we should know how region proposal network works. Mask RPN is a two-stage network, and RPN provides proposal to detect objects. If the intersection of a union, also called IOU, between proposal and ground truth is lower than 0.3, will be selected to train the model to ignore the region. And next time, RPN will not provide such proposals. And IOU over 0.7 will be selected to train the ability of the model. Between 0.3 and 0.7 will be abandoned by the RPN because it's very ambiguous. Pictures with no labels will be abandoned by the RPN because there is no ground truth to compare with. So the first picture will never take part in the training progress. In the third picture, we generate a single line on the overkill region. In the last picture, red boxes represent proposal and the green box represent ground truth. We can easily find the IOU is lower than 0.3, and those proposals will train the model to ignore the region. And then next time, the RPN will not provide such proposals. Scribble label makes a great progress in this task. We adopt different data generation methods according to different predict results. All the generation models are trained with original training date and augmentation date. This part is about our data selection. We use Bayesian optimization to optimize our training datasets because there are nearly 10,000 samples. And finally, we only use 4,000 representative samples to achieve better performance. The Bayesian evaluation dataset is different from the original validation dataset. We also add samples from the training dataset to guide the selection. Moreover, to ensure a balanced distribution of each type of defects, we enhance the defects with small quantity. At last, this is our results. We achieved second place on the leaderboard. The progress of MAP over time, we can see it increases from 18 to 28. The last picture is about training loss of final dataset compared with original dataset. We can see the final dataset is much more difficult to learn, and our augmented samples are very effective for track 2. That's all for today's presentation. I'm happy to answer many questions.
This is going to be our second last presentation for this track and for today. FS Tech Team. So it's going to be FS Tech Team.
Focusite Technology is a cross-industry machine vision solution provider, taking multiple applications of Pavlov's technologies as a core strategy. Be oriented to diversified industries such as consumer electronics, printing, agricultural products, and transportation, providing a machine vision system with appearance inspection as a main function based on independently developed machine vision technology platform. Focused technology assists customers in achieving intelligent product, thereby optimizing quality, improving efficiency, and reducing costs. The team members participating in the challenge competition come from the Research and Development Center. The team leader is David. The team members are Xu Long, Han Xu, Jun Wang, Xiao Xiao. Track 2 challenge dataset contains less stable data and sparse defect samples, which leads us to analyze the distribution of positive and negative samples systematically. Table 1 shows the distribution of the original training set. The number of OP samples are 5 times of the number of NG samples. NG samples includes 4 types of facts: collision, dirty, gap, and scratch. The quantity of dirty is the smallest, 43 cases, while gap has the largest quantity, 193 cases. The quantity among collision, dirty, and scratch are very close. Each type accounts for 2% approximately. The 5 charts on the left show the distribution of the location of 4 defect types respectively. The rectangles in the charts represent the bounding boxes of the defects, especially the distribution of gap type is regular. It usually distributed as upper part and lower part of image with a horizontal direction. The 5 charts on the right show the size distribution of mask areas of 4 types of defects. We can see that the areas of polishing and scratch are mostly small, while the areas of dirty and gap are very large. In addition, the distribution of gap is uniform. We first clean some ambiguous samples which have negative impact on the quality of training sets. Then we apply an augmentation policy on NG samples according to the previous analysis. P represents the probability of data augmentation. Here is the augmentation policy, including random rotation, random zoom, random flip, and random brightness. With the above augmentation policy, the number of samples of the training set was expanded to 11,000. We achieved 0.2164 based on this. However, we find that data augmentation methods still lead to a high false positive rate. So we apply local data augmentation, which only augments the specified OP samples. The NCP algorithm randomly copy-paste facts to the OP samples. However, the location of the facts is priori. For example, the facts always appear in gray area and will not appear in white or black area. So we use a binary mask obtained by twice threshold filtering to express the non-potential defect area. The issues of high false positive rate and significant ambiguous samples are addressed through data augmentation and data cleaning. Part of the facts are copied and pasted with non-potential defect area expression. With the combination of data augmentation and DNCP, we achieve 0.248 score. We consider the score can be further improved due to the lack of richness and diversity of samples. We attempt GAN methods by comparing various generative AI models. GAN2 ADA was selected as a primary network. GAN2 ADA removes the consistency regularization term from balanced consistency regularization while adding the data augmentation module before both generator and discriminator. The adaptive discriminator augmentation method can automatically select the probability of image augmentation. The selected probability can adjust image rotation angle, color difference in a specific range. When the complexity of features is high, the sample data augmentation module proved to be effective. It improves the quality of the generated image to a certain extent. However, in industrial scenarios, the scale of the dataset are small with low feature complexity, and the augmentation model has no obvious effect, which requires the model to make more adjustments to the features in a limited range. So we adopt mixed-out data augmentation, which is a good way to extend image features and enhance the robustness of GAN. After some attempts, we finally focus on generating OP samples, since the generated NG samples cause distortion. In this case, the diversity and quality of OP samples are enhanced. This figure shows the generated images. To further enhance the quality of generated defective samples, we adopt SRGAN, Super Resolution Generative Adversarial Network, to enhance the details of samples. With InspectiON, we can improve the fine-grained features and enhance the overall feature fidelity of the generated samples. This figure shows the model architecture of InspectiON we use in its competition. With GAN method, we achieved 0.256 score on leaderboard. However, GAN method is not a cost-effective method in terms of high training costing. After analyzing the subtypes of training samples, we believe that some subtype samples affect model performance a lot. Although there are only 4 types of effects in the training set, the subtype effects varied significantly in different backgrounds. To further analyze the impact of this factor, we apply clustering with statistical analysis to samples. The left figure shows the distribution of effect samples with different backgrounds in the training set, while the right figure is the statistics of various backgrounds. The bar chart shows the distribution of effects with different backgrounds are significantly different, and model performance are greatly limited by the imbalanced distribution of effect samples. In this challenge, the total number of samples of training set was strictly limited. We use subtype sample balance method to control the number of NG samples for each background. The left figure shows the original distribution of training samples, while the right figure shows the subtype sample balance distribution of training samples. We can see that OB samples and NG samples with different backgrounds are balanced in right figure. The score is 0.263 after applying subtype sample balance. We assemble the previous data augmentation DMCP, GAN, and subtype sample balance methods. Especially, we apply DMCP to more OB samples. We achieve the final score 0.27. The effects in the figure are generated by applying DMCP. Our main experimental steps are data augmentation was applied to NG samples after analyzing the training set. DMCP was applied to part of samples to alleviate the high false positive rate after ambiguous samples are cleaned. GAN method was applied to improve the richness and diversity of samples. Subtype effects were balanced to further improve the model performance. All above methods were assembled to obtain the final result. In this challenge, there are 3 key points worth investigating. Subtype samples of training sets have a certain impact on the performance of the model. The diversity of samples can affect model performance. In the case of U-short samples, the discrepancy of annotation can lower the model performance. Table 3 shows the MAP of each method. Baseline is a result of using original data, which has 0.172 MAP. After applying data augmentation, the MAP is 0.216. The DMCP method can further improve the MAP to 0.248. GAN helps generating more OB samples to achieve an MAP of 0.256. After subtype sample balance, the MAP reaches 0.263. We then apply DMCP and GAN to replace samples based on the results of data augmentation and subtype sample balance, and achieve a final MAP of 0.27. Thank you.
Okay, so the final presentation of the day. I appreciate who have survived till the end. I can count on my fingertips now how many we have here. I think Mung has something special for the remaining 10 people, right? No? Okay, so our final presentation is from CASLELIV. I think it's I don't know how to pronounce that, but
hello everyone, here is waiting to introduce you the most innovative solution for track 2. There are all members of our team. This report mainly includes the following 5 aspects. The performance of deep learning methods is higher related to the scale of adopted training sets. However, in the industrial inspection, getting labeled defect data is hard, expensive, and takes a long time. First of all, with the continuous optimization of production lines, Defective products become very rare and difficult to obtain. In addition, the labeling of high-resolution defect images is expensive. The commonly used traditional image augmentation methods have limited effectiveness. In summary, there is a lack of diverse data to train industrial inspection networks. The core of this challenge is to alleviate these industrial data problems. We need to expand the training set based on the given images. It is used to train the fixed master RCN. The submitted training set must be within 5 times of the original training set, and the ultimate goal is to improve the MAP of the unlabeled test set. Our solution mainly includes 3 key points. First, there are few real defects but abundant normal samples in the given dataset. We employ mass-guided defect generation adversarial networks to synthesize diversified new samples. Secondly, we need to choose the most suitable augmentation method for the detection network to employ the potential of high-quality samples. Finally, we carry out iterative experiments to find the most suitable synthetic data. Our synthesize method takes the requirements of high quality, rich diversity, and accurate semantic labels into account. First of all, we retain the details of the real normal samples. Secondly, we realize the independent control of defect shape, texture, and background, which can enrich the diversity of synthetic results in many factors. We generate defects at the specified position of binary mask to ensure the accuracy of labeling. We employ MDGAN as the synthesized method in the computation. In the input of the generator, random noise controls defect texture, binary mask controls defect shape, and pseudo-normal background controls normal regions. The BRM can modulate the real background information into the generator and returns the real normal details in the output. The discriminator judges whether the input image is real with defects in the designated region, and the DDM assists the discriminator to pay attention to local defect feature and improve the quality of generated defects. We have verified the effectiveness of MDGAN on formant and various products of MDTech. As can be seen from the picture, the generated samples of MDGAN can well preserve the normal backgrounds, and the generated defects are realistic-like in content and have accurate pixel-level annotations. In order to verify the independent controllability of defect texture, background, and the shape of MDGAN, we fix one factor and modify others, and the results are as shown in the picture. It can be seen that MDGAN achieves independent control of defect shapes, textures, and backgrounds in the generation of multiple products. Next, we use MDGAN to generate new console defects from the comparison between the generated results and the real defects. Our newly generated defects return the normal texture, have realistic-like defects, and accurate pixel-level labeling, which can be used to train mask RCN. Then the data optimization pipeline will be introduced. Firstly, we perform data analysis to facilitate subsequent data processing and data cleansing to avoid negative effects caused by noise samples. Then we employ data generation to improve the diversity of the training set. Data augmentation can explore the potential of high-quality samples. In addition, we conduct experiments to find the samples conducive to the mask RCN. We also balance each category of samples. We repeat this process multiple times to construct the training set. Firstly, we visualize the raw data size annotations. There are 4 defect categories and a good in raw size. The distribution of data size and the best testing performance on the validation set are shown in the table. After visualizing, we found that there are noise and unlabeled defect samples. These problems may have a negative impact on testing. First, samples with ambiguous labels may cause misclassification, so we move them to a more similar category. Samples marked as normal but with defects may lead to escape. and 2 weak defects may lead to overkill. When we delete these samples and the performance of the validation set after data cleansing is shown in the table, there is an approximately 0.8% improvement in MAP. In defect synthesis, we firstly match similar normal backgrounds for hard-to-detect samples and construct a test set for MDGAN based on the existing binary mask library, and this is customized by software. There are defect samples in the validation set, but don't exist in the training set, as shown in the picture. We obtain the similar normal images RN by SSIN and draw binary mask by AI-Pre to construct similar defect samples. As shown in red boxes, it can be seen in red that these hard-to-detect samples can be detected after adding synthesized defect samples. To further improve the robustness of mask ICNN, we explore various traditional data augmentation methods. The effects of these methods are shown in the pictures. Next, we verify the effectiveness of our paper. The performance of each augmentation method on the validation set is shown in the table. We conduct combined experiments and find that only combining rotation, translation, and horizontal or vertical flipping can significantly improve the inspection performance on the validation set. As gap defects are all horizontal, we only perform translation on this tab. MDGAN is trained for collision, dirty, and scratch respectively. Defect samples in train and VAL of console slice are used as training sets of MDGAN. We set the background pixel values in the specified region of the input binary mask to 0, replacing the pseudo-normal background used in the original one. To reduce GPU memory consumption, we scale down the size of original images. Training implementations are shown in the right. Based on the data optimization pipeline, we obtain training sets for each stage. We train the given mask RCN and use the test results obtained from the datasets with better performance on the validation set for submission. The compositions and the testing MAPs of each dataset version are shown in table. Firstly, the MAP of the cleansed dataset B0 is 0.17. After augmentation on B0, the B1 original dataset improves the performance by 0.03. By adding augmented MDGAN synthesized data, we obtain the B2 GAN, which increases the test MAP by 0.04. Adding synthesized unseen samples to get the B3 hard dataset, which shows only a slight improvement in test performance, possibly due to there are few same type defects in the test set. Finally, we add the cleansed and augmented data samples from the validation set and get the B final dataset, which achieves a test MAP of 0.26. In summary, in the explore process of data generation for defect detection, we conclude that explore the potential of high-quality samples suitable for the detection model is more favorable than simply increasing non-redundant samples. Otherwise, effectively explore the optimal augmentation strategy for the detection network is very important. We also need to find more efficient methods to mine high-quality samples. For industrial products with little or no defective content, improve detection performance by introducing knowledge of other similar defects through defect transfer is worth considering. That's all. Thank you.
So, any questions for track 2? Anyone? No. Okay. So I think I'll just take 1 minute for the closing remark. So, ladies and gentlemen, what an incredible journey it has been through this workshop. We have explored diverse areas from machine vision enabled quality improvement to efficient visual learning, imaging under challenging conditions, and data competition for defect detection. The knowledge shared and discussion held have expanded our horizons,
and inspired innovation. So let's carry this momentum forward, leveraging these insights to drive advancements in our respective fields. Especially the surprise visit from Andrew Yang definitely had a huge impact on this workshop. So thank you all for your active participation and valuable contribution. Last but not the least, a big round of applause to this workshop's chair, Dr. Mang Kao. So it was not possible at all without all the efforts that he has done for this workshop, and also for the entire team behind the scene. I think Shanku and Felix, they were not able to join this conference because of some visa issues, but I think we should also applause for them as well as all the other team members as well. That, yeah, everyone who was part of this. Everyone, yeah. Okay, so that's the conclusion for this workshop. So thank you all. Yeah.
Yes, thank you.
Yep. Yeah, hey, Joseph, are you at Apple Park? Yeah, which floor are you? Which section? Section 5. Okay, we should meet. Yeah, I'm also at Apple Park.
Cool. Anytime.
Yeah. Yeah, sounds good. Okay.